Okay, one, two, three. We're ready to start? Yep, okay, perfect. Good morning, everyone. My name is Maria Konovalenko. I'm a producer and a conference coordinator from the Latvian group. I'm thrilled to welcome you at the third annual Automotive Functional Safety Forum. I would like to thank all the speakers to their support and for joining us today and sharing their knowledge. Our sponsor for today is Tuvsud Rail. Let me also share a few organizational remarks with you. All networking coffee breaks will be held in the hall right outside. Restrooms are located on the right at the end of the hallway. Lunch will be served in the same room as the breakfast, behind the glass door. In case of emergency, please follow the green exit signs. And a 5-minute Q&A session will follow all presentations. If you have any questions, please raise your hand and the microphone will be brought to you. For all who joining us online, you can interact by clicking on the Q&A button and your questions will be answered in real time. In the agenda, you can find a list of participants, evaluation forms, and the speaker list. All presentations and the photos will be sent to you via link after the event. Your feedback is crucial for us, so please fill out the evaluation forms at the end of the event. Also, please turn on the sound on your phone if you haven't done it yet. And finally, I want to welcome on this lovely stage our chairman, Riccardo Vincelli. Enjoy the conference. Riccardo, the floor is yours.
Thank you. Okay, welcome. Welcome also from my side. Yes, this is the third year to have this forum. A bit of echo here, I don't know, hopefully you can hear me okay. Yeah, it's the third year of this forum, third year for me to have the honor to chair as well. So usually it's a very successful event. I hope also today and tomorrow. And again, as usual, the conference is for all of us, for you. So please try to interact as much as possible, ask questions. And we are not here to make marketing. We are here to talk about the technical topics, challenges, and also what we like. Hopefully, functional safety is our passion, something we like, and something we have the same pain. Because we know that everyone likes functional safety, but no one wants to pay for it. So what I keep saying is the best safe car is the car in the garage. But then we cannot sell it. And now we also have electrical cars. So with electrical cars, even the car in the garage is not safe. Okay. I guess many of you know already my name. My name is Riccardo Vincelli. I'm very active usually in conferences, also in organizing and chairing. I work as a director for the Functional Safety Competence Center in Renesas. And I've been dealing with functional safety since 20 years, something like that. Also very much involved in standardizations, not only ISO, but also IEEE and SIE, UL, all of them. But okay, you're not here for me. We have today and tomorrow on stage many different companies from different sectors, from really OEM, Tier 1, component suppliers, service suppliers, and so I think Lead Event managed to really get together a very nice group of presenters, so really many thanks for this. Hi. Yeah, okay, I got there. And In terms of topics, I mean, we have, again, today and tomorrow, different very hot topics we have today in the community. I mean, we are starting from the current approaches, so what we have today, but also moving to SDV, sorry, and also what does it mean for semiconductor. AI, I mean, now there is no activity with no AI. AI is now our reality. We need to see how we can cope with it. We have challenges for autonomous systems and safety, but also security. Open source software is something that, I mean, we will explore it today and tomorrow. Why? But it's something that is always coming more and more, like a bit AI. We cannot ignore it anymore. So open software is becoming also a reality for automotive, despite up to recently, this was a clear no-go. And then tomorrow we move into cybersecurity, functional safety, and how to harmonize, because really it's getting complex. And I will show in the next few slides. We have today what I call a jungle of standards, a jungle of regulations, something that if you are new to automotive, you're starting, where should I start? There are so many standards. Systematic faults and designing FMEA, that is a key topic because, again, most of the engineers today for safety are looking at what I will say maybe simple, because we can look with numbers like metrics, single point fault metrics, latent fault metrics, PMHF. Systematic faults actually is the biggest issue, but no one is looking to this because, I cannot quantify. So difficult to judge when the activity is completed, but it's very important. Architecture, component, systematic faults, so how to mitigate. Then we talk about the EV. Electrical vehicles, again, is something somehow imposed also by several regulations, but it's something becoming very important, yes, to consider. And then future directions. So I'll jump now straight into my initial opening speech here. And yeah, I think, again, if you want to look into functional safety, I mean, how many of you here are new to functional safety? Oh, great. All expert. So we can go home. We can stop here. Good. So I think, you know, if you look into functional safety today, you can select where do you want to stand. I mean, the conventional applications could be boring. No. You will see that actually there is also things to be done. But then there are the two trends that are starting really changing things, changing also what we used to think, and what before was unsafe, now is safe, we can do it. So things are changing, and also electrical vehicles. So for conventional applications, I will say the good points. The ISO 26262 today is widely adopted. So I think you can go anywhere, even university, everywhere in the world, everyone knows the standard, at least a number. Then the contents is something different. We are all focusing on how to make a safety low cost. That is the key point, because now, safety before was new, now it's not new. We cannot pay for it, so let's do cheap, and let's understand what we can cut. And also, what we found out is that the ISO 26262 is one of the key challenges, but it's only one. How to make everything together? We cannot have it just one process, and then you move into a process for security, and then something else. So how to harmonize, that is a key challenge. As a negative point, I still see a lot of misunderstanding. For example, ASIL decomposition. Something so easy, or at least it could be easy, something with so big misunderstanding. No one is thinking about ASIL is a parameter of a requirement. No, ASIL is the component. This component is ASIL. Then I do the composition, easy. No, it's requirements. At time too much checklist based with focus on numbers. As I mentioned before, we are looking all at the numbers, And then, oh yes, if I'm 89% I'm unsafe, if I'm 90.1 I'm safe. Okay. It's not like that. So we need to work away from this checklist mentality. Safety is not checklist. Of course, checklist standards are important, but you can have a full checklist done and still be unsafe. While you can have many points still unchecked, you can be completely safe. So you need to think about safety, not checklist. And still insufficient harmonizations. Now, if you're looking at what's happening in the field, we actually see a kind of back to basics. So many companies started to push for, many complex stuff, many fancy, like a control. We have now so difficult HMI in cars that if you want to have, you cannot use the mobile, but actually to change and switch on your, ventilation, you need, wait. So you see many companies now going back to basics. And even for the lights, now we all go for LED lights, adaptive lights, but actually you see many drivers at night don't want to drive anymore because the lights is really affecting their vision. Coupling this with computer vision, and then now you see regulations to try to change this as well. Now, of course, it's not functional safety like ISO 26262, and that shows that for safety, it's a bigger topic. It's not just faults. It's really, this is functionality, but we are providing functionality that actually is causing safety issues. But also we see new trends, steer-by-wire. So when I started many years ago, the X-by-wire was a nice term, but was something, would never happen. It happens. So now we have brake-by-wire, steer-by-wire. Now, if you're looking at the key relevant standardizations, standards, of course, this, what I mentioned, is a must. You need to know. And third edition is now already started, expecting 2027. So actually, 2 weeks ago, there was a meeting in Prague with many things discussed. I wanted to touch on this 8926 because usage of pre-existing software now will be integrated into the ISO standard. But it's important because you have always more software to use, open software, and so on. New language for software, like Rust. Rust is becoming also very important. And the guideline from SAE will be published soon. 2851 is a new trend because we see so many different standards and again a jungle. How to have this interoperability? That is what we are trying to achieve here. New approaches for functional safety for analysis, this STPA. This is also very important and is also starting for all industry, not only automotive, even if it's starting automotive. And SAE was leading the standardizations. Okay, it's not really functional safety standard, but the product liability is very important. I don't know if you know, there was this new directive that was started last year and now come to force in December 2024 already, and it's a kind of phase approach. And this says not only hardware defects, but even software defects are now in the scope, and including OTA and so on. Yeah, this also is a new standard for steer-by-wire. I wanted to mention because it's the first standard talking about availability. It's a new trend, so we need to wait, but it's showing the direction. Now it's starting a bit more interesting, ADAS AD. So most standards and regulations are now available. And we can say whatever we want, but AD is a reality. We can see already today across the market. But the negative point is there are still a lot of misuse, lack of robust driving monitor systems, ODD, control, user confusion. What is the difference between level 2 hands-off and level 4? I mean, probably here we maybe all know. But if I ask my wife, probably she will not know. So people are confused. Liability aspect, who is responsible? And I mean, I see ID is a reality as a positive, but it's also as a negative, because are we ready? And look at the news. We have Intel level 2. Yeah, okay, I'm starting with Tesla. No names. But you have several issues, and not only they're doing something that others are not doing, but they're doing even Mad Max. Yeah. But even Rivian, rally mode. Yeah, I'm better. Nissan also started with driver assistance. Tesla, again, some issues with, you can see the regulations and the judge are getting a bit more strict. Even in China, we had many issues with recalls. Then if we go to level 3, GM now is pushing to the level 3 direction. I mean, before many companies were saying, no, level 3 is just something in between. We don't do it. We jump to level 4. Now, level 4. Let's do level 3. It's probably easier. And anyway, you are responsible. And even the Stellantis started with a project for level 3, but now, unfortunately, even there, they said, actually, it's too expensive, so let's cut it. So some positive, some negative. Level 4, you can see here, I mean, so many, Waymo coming to London. After many things that they've done in the US, now they're coming to London. They begin offering freeway robotaxi rides. Toyota, e-Palette, also in Japan. In San Jose, a startup unveiled first consumer-focused, fully autonomous car. So that's now you can buy autonomous car next year. Maybe you cannot use it, but you can buy. And even in Berlin, here in Germany, is launching the largest pilot project for autonomous driving to date. So you can see here that, I mean, level 2, I will say, is the key today where most of the companies are. Yeah, there are level 2, and they are calling level 2 plus, level 2 plus plus, level 2 plus plus plus. Even if in TSI we said, no, there is no anything like that. So it's level 2 or level 3. Something level 2.9, level 2 plus, no, it's not real. But now they are also, in TSI, we are talking about introducing some technology ready as well indication. Because sometimes you have a level 3 car, but is it ready for really consumer usage? Sometimes they are more a pilot, but still in the streets. So there is a lot of confusion now about this terminology. But yeah, I mean, the focus today is a lot on level 2. But level 3, we had and is continuing to proceed. But level 4 also we see a lot coming up. And I mean, if you go to motorways in Germany, there are some level 4 cars driving there, even if we don't know. And you can see also on the regulation side, China is issuing ethical guidelines for autonomous driving technology because they were really complaining about many companies launching level 2 cars, ADAS, but then, yes, they can drive alone. So a lot of marketing that was not fair. And China is attacking this. So if you want to claim autonomous driving, you need to be level 4. Safe autonomous vehicles everywhere, so there is a US somehow committee or group that is pushing for safety first. California law aims to hold the driverless cars company accountable. Aurora now got approval for the warning device. So, you know, before we added this regulation, especially in the US, if you have an accident, if you're stopping, you need to put your cones around. And you have 5 minutes to do this from the moment. Of course, if you have no drivers, how do you do it? So to apply for this exemption was rejected. To apply again, after some fights, now they got it. And Belgium was completely against. Belgium was saying, no way. In Belgium, no autonomous cars. Now, yes. So if you go to the autonomous, to the ADAS AD, again, the ISO is the first standard, is a must, of course. Now we'll include also better linkage to SOTIF. This SAE standard 3016 with equivalent ISO standard is also very important. And again, it's not a technical standard, but it's just clarifying the levels of automation from 0 to 5. And this we are now working on the 5th edition of the ISO, or 5th edition of the SAE, or 2nd edition of the ISO, or combined SAE ISO, should be published soon, with some clarifications. SOTIF, again, yeah, that's what I was saying before. The ISO 26262 focus on faults, but even with no faults, you can be unsafe. So look at the light I mentioned before, the HMI, but these are simple examples. If you go to ADAS AD, you have a much bigger issue to solve. And SOTIF is addressing this. UL 4600, yeah, is something I've been working on this, and today also we have Phil Koopman will present. He was one of the, let's say, the father. It's a nice standard because it's really guiding you on many things you have to think. Regulation 157, I think it's important to know because it's the first attempt of a level 3 regulation, or level 2 plus. It's not really the level 3 same as the SAE standard because it's asking much more from the driver. He needs to be more attentive. And 5083, it was started with SAFAD, then with 4804, and now 5083 was published in March. And yeah, I think it's a nice standard, giving much more indications also of what to think. And the 2nd edition now is started as well. Or is starting. 8800, safety for AI, very important. And we also, I mean, this was published last year, end of last year, and now we have 2 new publications, new PAS, public available specifications, ongoing, to show some real examples. AI Act. I could also mention this in the previous slide, because it's not only for AD, ADAS, it's for everything, but here is where it started, really. And the AI Act, we will talk also, I believe, today and tomorrow, is giving some frameworks, what you can do, what you cannot do. So very important. But of course, many have the questions, okay, I follow 8800, so I'm done. No, there are many other things to consider. So unfortunately, all such standards are not a replacement. You can say, okay, I do this, everything's done. No. You have a jungle. You have to consider all of them. And unfortunately, you can see here ISO, SAE, UL, okay, community, ISO. Each one is using his own terminology, his own view. So, yeah, it's not so easy. And I also wanted to mention this, is the Road Traffic Remote Steering Ordinance. Was published in Germany in July this year, with effect from December. This is for the remote driving. So now I can stay in my living room or my studio, and I can drive the car on the way. So there are also some company, or at least one company in Hamburg, yes, that is pushing this. Okay, electrical vehicles. Again, here we have more standard regulations. ISO-compliant BMS is getting popular, but we still see issues of batteries fire, passenger getting trapped. And you can see here, I mean, we have many issues. Yeah, a bit everywhere in the world. And you can see here that some a nice example, I mean, this you can look in the handout, you can see some next example of different regions have different views on what is safe. And again, regulations, here you can also click on the handout, you can go to the link if you're interested. And if you're looking at the standardization, again, the ISO is everywhere, so sorry. But then we have it in 9868. This probably will be replaced, and we talk now about the other technologies. It's a new term coming into the ISO standard, is a framework. Other technologies is all like a battery and so on. Okay, so this was my introduction to scare you a bit on the jungle we have and the challenges we have, but also the interest field that we are working on. Good. I'm on, 1 minute. Any questions? 3 questions? No. Wait. So we have people online, so, okay, I wanted to ask you always to say your name, company, affiliation, and then speak on the microphone.
Check.
Okay, thank you. My name is Farzad Parsai. My company is Sand Microsystems. I like what you said at the very beginning, that safety is not checklist mentality, and that we have to come away from checklist mentality. And safety is safety, or what did you say? But we have to think about safety and not checklist. How would you convince people? I know that this behavior is quite far scattered in all industry. How would you try to convince people to come away from this checklist mentality?
Next questions. Yeah, it's not so easy. So, I mean, for me, I'm on the lucky seat maybe because I work as an assessor, and then I can also sometimes block projects or it is if I feel it's not safe, like it's happening less and less. But we can see, unfortunately, different views in different regions. Yeah, I don't want now to give specific indications, but you can see locations where, yeah, they want to understand the compliance to open the door and say, yes, I can use your component. You can see other regions where, yeah, compliance, okay, done. I put to my drawer, is everything done? Thank you, let's go. And that's, I also would like to say our colleagues here from assessor companies, let's be careful because we are somehow sometimes misleading some of the companies globally. A certificate is not enough. It's just a step one, but it's not enough. But many companies, they believe that this is all I have to do. Again, it's a starting point. It's not my target. But it's a community issue, unfortunately. If you want to do more, you need to think more. You need to understand. It's more time-consuming.
Thank you. Hi, I'm Helen. I'm from ARM, and actually I wanted to reply to your question, if it's okay. My presentation would be at the end. I would be talk about how we establish safety culture in ARM. I think this is, we are not selling safety culture. We are not selling consultancy in this matter, so that's why I would be more than open and happy to share experience around that and what we are doing. And for me, one of the biggest opportunity, and thank you, Ricardo, for organizing this, is really to talk together and share our knowledge on what we do here.
Yes.
Set up proper safety cultures, safety processes, and methods to work better in our companies.
I agree. So coming to conference like this one is a way for us to really understand and grow. At the end, safety is not marketing. Safety, I mean, people are trusting us to have products in the market. People can die. People can get injured. We don't make money.
So I would like to add here.
Okay, name and the company.
Sorry, I'm Alexander Matasch from Elektrobit. So I'm not as long in function safety as you are, just 15 years, but I heard exactly the same thing when I started, how get away from checklists in safety. One thing also having discussions with our quality people internally, quality people love metrics. And many people think safety and quality is the same. It's not. But many people think this, and then they think they can measure safety. So if we collect metrics and have thresholds, then we're safe. That's not how it works, but it's really a tough job to convince people that we really need to understand what the system is doing.
That's why in the 2851 we talk about dependability, because that is what we need to target, dependability, not only safety. It's a big topic. Okay, unfortunately I'm talking too much, so we need to now stop on these questions, but we have all day today and tomorrow, potentially even this evening. So we should really move on. And I would like to present the next presenter, or the first presenter, is, hopefully I pronounce correctly, so is Harikaran Venkitashalam from Iveco Group. So I don't have your bio here, but please, if you can introduce briefly yourself, and then let's jump. Thank you. Mr. This is the mover pointer.
So, do you hear me? Yeah. My name is Hari Venkatachalam. I head the product safety and security at Iveco Group. So, I've worked for 17 years in the automotive industry, worked across different roles and responsibilities related to system engineering, software development, and later headed the zero-emission vehicle safety for Iveco, where we launched 2 zero-emission vehicles last year. We are in the process of launching one more zero-emission vehicle towards the end of the year, and so on. So these are basically reflections from an OEM perspective, where I've gained some understanding of how to manage safety for software-defined vehicles. And these are some reflections from a very broad perspective. So of course we can go into the details if you want, but this is just touching the higher level of how to manage safety, given the fact that Ricardo mentioned about the jungle of standards, regulations, and also practices that we need to follow. And also given the fact that your electric vehicle that is parked in the garage is much more unsafe than your electric vehicle that is running on the street. So these were challenges that we faced in the last 2 to 3 years, and I will share some of my experiences based on this. So if you look at the evolving technological context, I mean, there is connectivity, which is that your vehicle is no more just an independent system by itself, but it is connected to the to other vehicles. It is connected to the infrastructure, whether it's charging infrastructure or traffic infrastructure, and so on. All these increase your interfaces. These are also potential attacks that could happen through these streams for cybersecurity, which could eventually influence the safety of your vehicle. So this is one of the aspects that you need to consider. Then you have autonomy. Ricardo already mentioned about the fact that there are a lot of standards and regulations coming in the way of autonomy, where you have, say, level 2, 2 plus, 3, and up to 5. And you have different levels of technology maturity that you have with respect to sensors, with respect to algorithms, which will also affect the safety of the vehicle, so to say. When it comes to the vehicle, it's becoming increasingly software defined. What does that mean? So when you look at the architecture of the vehicle, you are trying to centralize a lot of functions inside what you call as a zonal or a domain architecture. And you also have the tendency of OEMs to centralize the development of software within their house, which was probably not their forte, I don't know, 10 years back. Probably the amount of code that was developed in-house in an OEM was significantly low. There were small portions of algorithms that were used as some sort of a differentiator. And today, people see this as a huge differentiating factor to develop software in-house, and as a result of which, you have this kind of in-house software development. So when you in-source the software development, you obviously have a lot of challenges because there is no safety culture within the organization because for the software part of it, because obviously you're hiring software developers, some testers, et cetera, and then at the end of the day, you need to imbibe those qualities or probably impart those qualities into those people who you hire in-house, and then you need to bring in governance systems which take care of safety and security. So this is one of the challenges which are related to software-defined vehicles. And you can see that with electrification. On the right, you see one of the vehicles that we launched last year, which is the fuel cell electric vehicle that Iveco launched. Here, again, you can see that the powertrain is changing. The powertrain controls are changing. And the amount of safety measures that you need to have in a battery electric vehicle is significantly higher as compared to the combustion vehicles, given the fact that there are potentials for risk of battery fires. There could be also fires due to overcharging or deep discharge of batteries and so on. So all this is new world for the automotive. If we have to kind of have mass production of batteries, battery electric vehicles or hydrogen vehicles, which we would like to have by 2030, 2035, managing safety will become significantly harder as we go forward. And why? Because there are also industry factors that determine this one. That is that shorter development cycles are going to be the story. I mean, gone are those days where you had 3 to 4 years of development and 5 to 7 years of production and 15 years of operation and service. And gone are those days where you would have 100 different suppliers who would still provide. You would have a lot of software in-house and a lot of development that you are insourcing. So when you look at what are the key concerns that you have for vehicle safety and security, in order to not become redundant, I would rather say that most of these problems have been also highlighted by Ricardo in the previous presentation, which is more saying that self-driving cars are going to interact with normal human-driven cars, and there is going to be a lot of challenges related to this in terms of decision-making for driving and so on. Now, looking at why software is important for vehicle safety, here is a list of some of the recall actions that have been constituted by NHTSA. So, I mean, basically published by NHTSA and by different vehicle manufacturers who manufacture in the order of millions, so to say. So you can see that there is a lot of safety issues that are created by faulty software which is released without probably, maybe with beta testing, and then after that released into the market, and then after that not all corner cases are tested, and as a result of which you have these kind of scenarios of recall which could cost the organization in terms of millions. So how the fundamental problem here is that how the software world sees the vehicle. They see this as a mobile phone on wheels. So this gives the impression that you could just deploy apps as and when you want, and there would not be any influence in terms of safety or security of the vehicle. So this is fundamentally flawed in my view. This is my personal view. Some other people who are too deep into software would say it is still doable. I understand that, yes, you can deploy new features into the vehicle, but at the same time, to oversimplify this narrative as something which you can deploy on a mobile phone is probably a bit fundamentally flawed. And what comes out of it are challenging scenarios. No, if you start looking at the cybersecurity, there are new interfaces that I mentioned that are to the vehicle. So there are new interfaces that are hacked, like Bluetooth, cloud, OBD, etc., etc. There's also the rise of quantum computing. As you can imagine, that Google has now said that yes, quantum computing is a reality, and that post-quantum cryptography is going to redefine the way in which the security of electronic control units are going to be there. What that causes is that your ECU hardware, so when you choose a ECU hardware, you start development 4 years before the actual deployment. So when you dimension your hardware security module or something like that, that you dimension it for maybe twice as the size of what you want today. But in reality, what comes out of this is that the cybersecurity of the vehicle over a period of time gets compromised. On the functional safety side, there are obviously mismatches between goals that are defined by the vehicle supplier versus the tier 1 supplier who is providing these components. There are also, on the product safety side, there are things that are not fully standardized. For example, hydrogen safety has a regulation which is called the R134, but it is not fully standardized in the way that you can not determine what are the other consequences of, say, for example, a valve not functioning or something like that. So as a result, product safety as a domain is also emerging, where beyond functional safety, to ensure the safety of the driver, you would need a knowledge of electrochemical systems. You need to understand also, say, for example, how chemical processes work in, say, a hydrogen vehicle, so to say. And of course, the basis in the European market is obviously homologation and standardization. So the truck industry has come up with general safety regulations, which is also indirectly applicable for the passenger vehicle industry. It's called the GSR Step B, C, D. So till 2029, you have these regulations coming in. So recently, the GSR-B also mandates having cybersecurity on board, also having, say, for example, systems like driver drowsiness, blind spot information system, etc., etc. But the reliability of these systems, especially when it comes to, say, availability aspects or dependability aspects of these sensors, so to say, are still not yet at the level that we want to deploy, say, an active safety system. So for example, if you have a blind spot information system on your vehicle and you want to extend it with active braking, so this will mean that the detection of your sensor is highly dependable, more or less an ASIL compliant detection, so to say, whereas you see that your blind spot information system uses a radar. And if you drive through a construction zone which is full of metallic surfaces, for example, there could be a lot of reflection coming in from the external environment, which could cause the radar to be confused, and as a result of it, the dependability of the system is questionable. So these kind of challenges you would face going ahead while deploying these kind of systems. So for this, I would propose a framework which is encompassing awareness and values. There should be also alignment between the organizational units to achieve safety. You need to have a strategy in place for safety and compliance, and there should be execution and deployment and continuous improvement. To start with the awareness, you need to know all the plethora or jungle of standards and regulations that are existing. You should also derive, say, group standards, which are more aligned to these standards and regulations that are there, and it should be continuously updated. Another key aspect that we focus on is trainings from our organization, where we train young software engineers, electronics engineers to think in terms of safety. So there are a bunch of trainings at different levels that we do. And apart from this, we need to also espouse values of transparency, having a safety culture, allowing people to speak up if there are safety problems, and so on. Apart from this, on the organizational level, there should be a possibility for a vehicle safety head, or say, for example, somebody who is heading these kind of organizations, to be able to align at a board level to highlight problems related to safety and security, and to also align with the same counterparts on the supplier level, which is also a key aspect to get decisions done in an executive environment, so to say. So this strong alignment with engineering as well as also on the supplier side is critical for you to make decisions, quick decisions in the organization. As far as the compliance strategy is concerned, I would like to, there's a lot that is mentioned here, but the important thing, what we are trying to focus on is also component selection, because if you think about a truck, for example, you have 40 different ECUs, roughly 40 to 50 different ECUs inside your truck. So when you look at this, most of the damage is done when you choose the component, because most of the times there is a misalignment of ASIL levels, misalignment of safety goals, and then after that you are trying to kind of mix and match these safety goals from the vehicle level versus the component level, and there's always a confusion. And once you choose a component, then probably there is no incentive for the platform to invest more in terms of upgrading a component or something like that. So this is also some practical problem that you face when it comes to component selection. Of course, core processes and process and methods, all these kind of things are obviously there in compliance with ISO 26262, 21434, R155, etc., etc. Another aspect that we put a lot of effort in is to look at the validation and compliance strategy, which is more looking at how we test things, how we make sure that across different levels, so to say, at component system as well as at a vehicle level, to make sure that we are not doing double testing on one side, checking the same things that you check on the homologation side, but also to try to see what would be the sweet spot when it comes to managing different levels of testing that is there. And also looking at release and post-production management. So one of the key aspects that we are working on is to liaise with, we have a set of people called product safety forensics, who essentially go deep into an accident, try to find out what went wrong with an accident, what could have happened, etc., etc., and they postulate these theories, which help us to actually design systems better in the future. So this is also something where we use accident research as well as field data analytics. Apart from this, we also have laid out guidelines and templates inside our organization. So when it comes to execution and deployment, there are some examples of risk management, there are examples of tool qualification, etc., which you can deploy on the software side, which can be of use for software-defined organizations. And last but not the least, you need to have a continuous improvement of safety and compliance framework, which is basically feedback, a lot of learnings that you have from the field, from your people, to be able to improve the safety management system that you have over a period of time, so that you accommodate new regulations, new standards, and also measure the effectiveness of the safety strategy that you have implemented. So at the end, the target would be that you combine disciplines across cybersecurity, functional safety, and also vehicle safety, so to say, component level safety and system level safety, to integrate and have a holistic approach towards managing the vehicle safety, which combines all these disciplines and also talks about end-to-end delivery, which includes right from the point where you select a component to the point where you deploy this vehicle into the field and measure the feedback from the customer side and then feed it back into your development. So this is a kind of a circular model that we are trying to develop inside Iveco to bring different experts with different expertises together to manage the end-to-end safety of the vehicle. With that, I come to the end of my presentation. Thank you very much and wish you a nice day.
Many thanks. We have time for one or two questions. Don't be shy. Also offline, remotely. Okay, no questions. Still too early.
Thank you.
Well, I will ask you a question. So what do you think what is the biggest challenge right now across all the aspects you reported?
I mean, the biggest challenge is bringing an organization which was previously producing vehicles, combustion engine vehicles, to think about problems which are probably not thought about from a powertrain angle, also from a cybersecurity angle, because most of the times people think that cybersecurity is just passing the R155 homologation test. No? So it is just a process. So if you do set up a cybersecurity management system and homologate it, and then follow the cybersecurity management system and then execute it, then you're fine. But in reality, if you look at cybersecurity as well as functional safety, and plus also look at other aspects of safety, like battery safety, for example, like thermal runaway reactions and stuff like that, to be able to make the organization think about safety in a holistic perspective. This is the biggest challenge. It needs awareness and values. You need to bring in, say, new regulations, new group guidelines, etc., to really bring them onto the same level, so to say, and to coordinate it end to end, meaning to say right from the point where you select a component to the delivery to the customer, to have safety coordinated in the right way. So this is essentially the biggest challenge.
No, I agree. Again, safety and dependability is the DNA of a company, and not only company, but also supplier, customers, and so on. So you need to change it the way you're operating, and safety is not a wrapping paper you put at the end. You really need to think all the challenges together. Oh, okay, one question here.
1, 2, 3.
Thank you very much for your presentation. Enjoyed it very much. I have a question.
Can you again name a company? Your name and company. Name and company.
Umang Chemyan from ZF.
Yeah.
Yeah. I was wondering about the point you said, culture and values. So that's really good that you bring that up. I mean, that's not it's not in every presentation and so on when you talk about safety, but I think it's the same way. But do you have a kind of a limit when you say, okay, now it's okay, or how do you measure value and culture?
So when it comes to, say, imagine you have a real problem. Say, for example, you find a problem on the field. So how does your team react to it? Not just your team, but this one. This would be a reactive approach. But what we are trying to do is to see, are we putting many checks and balances in the system? Meaning to say, while selecting a component, for example, do you really go through the due diligence process where you check for safety alignment, making sure that the safety team is a key stakeholder, checking whether the component is the right one. That could be one thing. Another thing is that you consider safety requirements right from the start in terms of safety of intended functionality as well as also the FUSA requirements, and making sure that the test coverage at the end is reported as a key criteria for the release of the vehicle, so to say, that the amount of test coverage that you have, the kind of corner cases that you test, the amount of problems that you are solving in due course of time, and to also ensuring that many people, for example, I work with different departments where people have to come up and say, okay, this problem is there in spite of the fact that it is too late, in spite of the fact that it does not make for them life easier. So this is when your safety culture is really working, meaning to say that they're ready to do the right things even though it is painful for them for a short period of time, say for example. So this is where I would really measure saying that, okay, your safety culture is really good. No?
Yeah, I agree. And by the way, in the third edition of the ISO, there will be a bit more of these, not only safety culture, but also safety policy and so on, because it's something that really is important.
Just one more point. So one engineer could potentially stop production of the vehicle, or say, for example, if you can really influence the decision to push the SOP or something like that, then you have a strong safety culture. Till that point, you're still peddling with the idea, but you are still not there. No?
Okay, many thanks. Okay, next presenter is Farzad Parsaye, okay, from Descend Microsystems. Yeah, also 25 plus years of experience in previous roles as at University of Berlin, Philips, NXP, AMS, so many companies, and is involved in development of several analog mixed signal RF integrated circuits, and also MEMS sensor. Experience of functional safety and quality, and yeah, I think I'll give you the floor. Thank you.
Thank you, Ricardo. Do you hear me well?
Yes.
Oh, I'm far enough. Okay, so you made the introduction. I start with the presentation. So the topic is functional safety in modern ASIC and semiconductor development. So I'm not going to introduce you any inventions, but just talk about some typical problems that we have in the ASIC and semiconductor industry. So to give some points to have fruitful discussions, hopefully, during these 2 days together. This is my goal, actually, why I'm presenting this year. So let me see if I can change it. Yes, actually, we are all here to avoid this. So functional safety is essential for ensuring that people do not harm, that vehicles do not harm people. And what I'm going to talk about today is some essential topics of my talk are like the growing demand for safety critical semiconductors in the industry, that safety influences the entire ASIC life cycle, and that, to my view, deep technical expertise in semiconductors is quite essential. And I will talk also about some challenges in automotive analog mixed signal or RFICs. So, in fact, with my presentation, I'm addressing this topic of functional safety from the component level. Many of you might be on a higher level, on software or vehicle level. Here, we see what happens in the component level. So, the growing importance of semiconductors in automotive safety due to the rise of ADAS, electrification, automation. We have something like more than 100 sensors nowadays in cars, and it's going to be something like 200 in the next years. And the semiconductor complexity is also increasing in the cars. And the functional safety is no longer limited to system integrators. It's now also a semiconductor design responsibility. So here I have a graph from Yole Development. They are a marketing, very well-known company that make market forecasts. And their forecast is that the semiconductor market in the automotive industry is growing by a factor of 2 from 2024 to 2030, from 68 billion to $132 billion. So, and there is a strong automotive market pull for ASIL ready sensor interfaces. So what are the advantages of chip-level integration for functional safety? It increases the reliability because we have fewer components. We have more integrated into the chip. We have a lower failure rate and a higher MTTF. And this improves also safety, and it lowers the probability of failure on demand. And also risk is reduced here because we have simply less components that may cause failures, so like wires, solder points, and also the packages are less because less components we have here. And it mitigates the systematic issues. I remember, I think Ricardo said in his presentation that systematic issues are one of the biggest issues, and the semiconductor development follows actually very highly disciplined and mature process. This is inherently there for many years already, and this can be also quite useful for the for avoidance of systematic issues. I myself moved once from a semiconductor company to a system integrator company, and I realized how much I could contribute to the procedure, to the development procedure, because I brought so much knowledge from the semiconductor industry into this system level company, and there were a lot of knowledge, and it is actually the most advanced industry that we have, and it's quite useful what we can learn from semiconductor industry for functional safety. Okay, we have wide use of ASICs in the automotive safety industry already in use, so there are many ASICs already there, like sensor interfaces, real-time signal processing, smart ECUs for ADAS, like collision avoidance, adaptive cruise control, then for electrified powertrains, for like battery electrical vehicles or plug-in hybrid electrical vehicles and battery management systems. There are already many ASICs developed from many companies, or connectivity and vision systems like cameras are very important part where many ICs are developed for cars, and they must be also safety prone to safety issues. TPMS stands for tire pressure monitoring systems for cars. There are also many companies that develop ASICs for that. Then Hall and inductive sensors for positioning. I will give you later an example for this. And last not least, also LiDAR and radar, and also AI and machine learning is also coming. So what matters in safety critical ASICs? It's important to care that safety critical ASICs must meet very strict performance, reliability, and safety targets, and that we have to be aware that small variations at the device level can have system level impact. And some key issues that we may have in ASIC, just to give you an idea, is just like linearity, gain, offset, power consumption, chip area, power supply issues, noise, different types of noise we have on ASIC that we have to master well, oscillation, crosstalk, and also dependencies on process, voltage, and temperature. And we have also some typical failure modes on ASIC. They must be understood well, so that if we understand them well, then we can conduct right measures to avoid them or to mitigate them. Some typical failure modes are like PLL, clock jitters, or unlock or frequency error. Especially PLL is quite important because it generates a clock that is distributed across the chip, and it can cause these kind of errors that can be scattered around the chip. So we have to care about those. Also VREF, the reference voltage on chip is quite important because also the reference voltage is also distributed to the whole chip. And if this guy is wrong or is noisy, then you have noise all over the chip and you will get issues. And power supply noise. This is also quite important because obviously you supply everywhere with your power supply. Then we have also stability issues, open, shorts, logic error, and many, many, many others. But the first three ones are quite important because you may get these kind of cascading failures, yeah, that can come after each other. Or you do also a very interesting analysis. It's called dependent failure analysis. Yeah, it's a big topic also in the functional safety analysis. So the deep technical expertise is really here a key requirement for functional safety of ASICs. Understanding of semiconductor physics, design trade-offs, and failure mechanism is quite inevitable. And many people like the safety guy, IC design person, system engineering, verification, analog experts, digital, what I know, the test people, packaging, they all have to work quite well together and understand what the issues are and to avoid the interfacing issues, the interfaces between the people. This can cause lots of issues that we should care about that. So safety influences the entire ASIC development flow. Semiconductors are playing a central role in embedded safety into engineering automotive technologies. Automotive driving so introduces extreme safety requirements and challenging semiconductor reliability well beyond the QM, so the quality management standards. So it must be considered from, the functional safety must be considered from concept to production. So everywhere we have things to take care about. And it's not just a verification step, it's a life cycle culture. This is important to know this. Okay, this is here we see a typical ASIC product development flow, starting from feasibility study, architectural design, specification, system level modeling. Then we go normally to schematic design, layout, post layout, manufacturing, testing, packaging, and then supply to market. This is what we have, the conventional ASIC development flow. Then here are some activities that we normally do for functional safety. Some of them, especially the first one and the second one, HARA, which stands for hazard analysis and risk analysis. Here, this is done mostly by the OEMs or also the tier ones. But, okay, from ASIL determination, maybe the ASIC people, they get the ASIL already determined, but the real work starts with safety goal definition on system level and on chip level. We need also to define the safety goals. Then we go to functional safety requirements, concept, and then technical safety requirements and technical safety concept, which goes really to the hardware and also software requirements and development of circuits on transistor level, so to say. And all these brought over the normal ASIC procedure, development procedure, we get a lot of additional activities that we have to care about. Starting from consideration of safety mechanisms already at the beginning, then safety requirements, preliminary FMEDA is quite important, very, very important to do it already at the beginning. and not at the end of the project. Then you realize something doesn't work and you have to go back and do redesign. Fault injection simulations and extensive design reviews have to be done. Layout, even during layout, there are several measures to take care about. Then ensure reliability, traceability. Then during the wafer test also, and testing, we have also many digital test procedures that we have to provide, like error correction code, watchdogs, cyclic redundancy, and so on. Also during packaging, the moisture sensitivity is quite important. Temperature coefficients is important. And go to market, but very important, the field feedback from the market is very, very important. Many people do not care about this. So we have to see what happens in the market, what goes wrong, and to flow it again into the procedure and to bring in the improvements. And also for the failure rate calculation. There are normally some documents available from some companies that all follow this with some theoretical numbers, but the best is if you see what happens with your process in the field and to have a feedback and to gather your experience and numbers from there. So the V model, as we have it in ASPAS, we can have it also for ASIC. I drew it. It's also similar things that we have from on other levels. We can also have it for ASIC. So some challenges in automotive, analog mixed signal and RF ICs. Analog, especially the analog and RF faults are often non-binary and parametric, making the detection even more harder. And environmental variations like temperature, aging, EMI, so electromagnetic interference, they affect also the safety behavior. Tools and metrics for analog fault coverage are still maturing. And a possibility, I'm still myself thinking about, maybe some are realizing it, is to run the safety analysis and verification on block level. So to certify a block, IP block, for example, on safety, and to make it more reusable in other chips. Because we have it that many blocks are always used for different chips, and if some blocks are already analyzed for safety, then it might be better for time to market to use a safety IP, a safety certified IT, so to say, for new developments, making the costs to be limited a bit. Here, one example of an ASIC for a Hall sensor. Low-cost Hall sensors, CMOS Hall sensors are widely used in automotive proximity switching for positioning, speed detection, and current sensing. Here we see the signals. So the red one is the noise, and the blue one is a very weak signal which is coming out of the Hall sensor. Then it is amplified, everything amplified, and then we have a chopper that brings the signal into the lower frequencies, and then the noise can be filtered away. So, So this is the way how roughly a Hall sensor ASIC works. And important topics there are safety goals. The safety goals are like gain, offset, and delay. So you set them as safety goal for the chip, and you have to care that in all cases these the limits are set, so to say. And there is a lot of engineering work here necessary to do. Just as an example to give you an idea how an ASIC looks like for Hall sensor in this case. Okay, and the challenges for automotive. Oh, now I go back here. Let me go. Oh, No, this way, sorry. Okay, another case study for failures that we can have is aging effects of transistors. Aging of transistors can be the root cause of several failure modes, causing issues like too high or low output voltages, which can cause some failure on the top level, unacceptable offset voltages, incorrect gains, slower speed. So one must understand the root cause, exactly how this happens, in order to be able to mitigate it or avoid it, to prevent it. So there are three main root causes for aging. What is hot carrier injection if you have a high voltage applied on the drain source, or if we have high temperatures, we have bias temperature instability. Electrons can diffuse into the oxide region and change the threshold voltage of the transistor. Or if we have a high gate voltage, we may get some traps inside the gate region. And so time-dependent dielectric breakdown can happen here. And here, in a nutshell, the golden rule would be here to minimize, for minimization of most transistor aging, to use lowest possible voltages, use effective thermal management, and ensure clean and efficient switching transitions. All of this is important, is the art of reliability and safety engineering to achieve all this without compromising the performance. This is what is it really about. Yeah? And my last word is here, deep technical semiconductor expertise combined with the functional safety know-how is essential. And just to summarize my talk in the last 13 seconds I have, as vehicles become smarter and more automated, semiconductors are used more extensively than ever, making their safety absolutely critical. To meet the growing challenges, we need strong safety processes and deep technical expertise in semiconductors itself. And uniting these these disciplines paves the way for the next generation of safe and reliable automotive systems. Thank you very much for your attention. 20 seconds more.
Okay, we already have a first question here.
1, 2, 1, 2.
Good morning, Vincenzo Sacco from S-Cube. So I wanted to ask a question about how do you see the mission profile evolving in the era of autonomous driving? When I started this job many years ago, the typical mission profile was 2 hours per day and a few night starts and day starts. If you go to San Francisco now, you see way more cars, running around 24 hours per day. And yeah, so I just wanted to pick your brain how you see the mission profile impacting the design of a semiconductor component in this new application area.
I have the exact numbers not in my mind. I can look at it and give it to you later, but it is something.
Yeah, but my guess is that, especially for legacy product, right, which has been designed perhaps for less aggressive mission profile, how is this going to evolve?
Yeah, this I cannot answer at the moment. I have not the numbers in my mind. These are mostly given by the customer and are somewhere in the documents. But if someone else has this, then I would also like to hear.
Yeah, but it's true that with the extended mission profiles, you have new challenges. So what is the lifetime of your product, your component? Before we could estimate with a good confidence, now you have a much more variables that we need to bring. So that's why predictive maintenance or other aspects like that are becoming important. Last question.
Milia Tasaver from Robert Bosch GmbH. I want to ask about these case studies are mainly for the basic chips, for basic ASICs. For some complex chips, we need to use, for example, ASIL and non-ASIL part at the same chip. So how do you ensure freedom from interference for such kind of chips?
This is a challenge to think about, and this is also a topic to address. So that blocks may have impact on each other. Actually, I do also, my main work is consulting. I work with many semiconductor companies, and this is one of the things that I also always talk with them and ask the engineers to run simulations and to exactly do this kind of analysis that things can have impact on each other. Even it should not be non-ASIL relevant. Also the ASIL relevant parts, they have also some cross talk and cross connection. And this is exactly one of the biggest topics that the engineers need to consider, and that must be part of their development. This has been already always. I was in the past in the mobile phone industry and was developing chips for mobile phone, and even at that time we were doing this kind of analysis, and now it's more severe.
Yeah, it's a big challenge, this, yes. Not only safety related, not safety related, but the multiple ASIL combined within the same component due to cost pressure and so on. So, okay, many thanks.
Thank you very much. Thank you.
Okay, next presentation will be co-presented. So we have a Dr. Roman Ksemian, Head of Safety Center of Competence in ZF. And together we also have Dr. Martin Hahn, that is a principal software expert in the Safety Center of Competence. So I'll give you the floor straight.
Thank you very much. Is it working with that? Yeah, okay. Yeah, first of all, thank you for the introduction and also for the interest in our presentation. I'm very happy that we are here today at the Automotive Functional Safety Forum, because I like to talk about safety very much, but I try to limit my presentation to, or the part of my part of our presentation to 10 minutes. It is about safety isn't in the process, so that's a bit different than what you had in your conclusion right now. You said, okay, safety is also processes, but it's not only processes, and it's also in the content, or more important is the content at the end. There's also, now it's working. We also have a different number than you had before in your presentation, because in trucks it might be less than in passenger cars. We are talking about 150 control units around in a normal PAS car today. And that's also somehow clear if you just think about an example like the side mirror. So the side mirror in the past was just a mirror. Now it's a small monitor, and it's a camera, and it's also a small control unit taking over the job from just a mirror. So that shows how the complexity is increasing also. So we get more control units. We have 25 gigabyte per hour transferred in a standard PAS car today. So that's more than many of us have in the mobile contract, right? And you have your mobile phone. In Germany you have, like, I don't know, 16 gigabyte or something. So that would be quite quick gone. And that also goes then to, or is leading to new server-based vehicle architecture, so that the architecture itself is not so complex anymore, but of course the functionality is still there. So you have other problems, you have new architectures in the semiconductors, then in the microcontrollers and so on, so there is a lot of things going on, and that's just showing that the complexity is increasing all the time. Also the code is increasing. At the moment we see in a standard PAS car, experts say it's around 150 million lines of code. But if you also add ADAS functionality or ADA functionality, autonomous vehicles, then it can easily go up until 500 million lines of code. That shows that it is really exploding somehow. The complexity, the functionality is getting more and more and more. And also the huge variety we have, as said, with a side mirror. That's just an example, but there are a lot of systems that you can order or you don't order them. So it's up to you. So also for us as a tier one, it's always not so easy. We have a huge variety as well. We do not know if our systems have to deal with a digital side mirror or not, but we also always have to be prepared for that. And that also increases then the number of the variants we have also for testing, for example, for analyzing, and so on furthermore. So the complexity is increasing, and also the analysis and the methods we use, the safety methods, they also have to cope with that. Yeah, we also have to follow that somehow. So we have new failure modes, more failure modes, we have interdependencies. We now have to analyze also system of systems, so interaction of one system with another, might it be there, might not be there. So that's always an additional challenge that we now face. We also see that we have new analysis methods available already, like the SDPA, most of you might know it. So it's that was somehow said to be like the answer also for autonomous vehicles. We also try to do that, but we see that that's a good way, a good step in one direction, but it's not helping for all the problems in our point of view. So also the safety analysis need to get better now, and we also need to work on that. The safety standards themselves are also becoming more complex, sometimes harder to interpret, and then you have also new standards, so like the 8800 for artificial intelligence, and now you have different standards. We have SOTIF also as another example. So how do they interact to each other? Some is described in the ISO 26262, for example, how they interact, but of course it cannot be done for all the standards. But in general, we have a lot of standards now. We have more standards which we have to fulfill. Going back. So if you're looking at the project has a lot of process requirements. So for example, starting on the left-hand side with the experience-based, what we know, how we developed our products always in the past. So that's, of course, something. Then we have customer standard requirements. So customers also request from us to use this and that analysis method, or to also fulfill this standard. They have own group directives, which we also have to fulfill. Then we have the state of science and art. We all know that we are all also active in science somehow. Also company internal standards. For example, ZF has a long history in safety and also in quality, so we have a lot of internal standards which we fulfill. Special technologies, for example, if you have a LiDAR, then you also have to take care about eye safety. So there's another regulation for that, then it also comes into the game. And of course, just regulations like in the US or European regulations also have an effect on our processes. So the trend is that we have more and more process requirements, more process steps, more work products that we shall bring to guarantee a safe product. For example, before the ISO 26262, we already made use of the IEC 61508, so that was then already something that had a lot of new process requirements, also SPICE and so on. Then the ISO 262 came into the game, then with second edition and so on. So we have a lot of new process requirements, additional process requirements coming from SOTIF, for example, it's endless. So, and we see it's always getting more and more processes. So that makes us at the end slower and slower, because we have to do more work products at the end, more requirements to fulfill and so on. So that makes us more and slower and slower. But as said before, it was also on the slide what we have seen, the time to market is decreasing, so we should be quicker at the end. So that's somehow a conflict that we see. So we have more requirements, more work steps, more workload, but less time for that. So that's definitely a challenge. But it is still important to stick to safety. So it is critical. We want to be safe. We need to be safe. That's, of course, a must. We see also the importance of the content quality. That's then the other side. So the true safety lies not only in having such processes, but really also doing solid analysis, realistic assumptions, That's very important. Also, the role of the processes is, we know that processes are important on the one hand. On the other hand, we also know that they are insufficient alone. So it's not only about, in the last line, tick in the box, for example, yeah, we have all work products available. It's that the content is the right one. So of course we can have a fault-free, short one, which is then completely nice, but it's not reflecting the reality at the end. So that is more important, that it really is, the product at the end is safe and not only the processes. We see a need for innovation because of that, what I've said before, that the time to market is having a great pressure on us. So we face that these challenges, we need innovative ideas. For example, Martin will then focus on also the market observations of what we have in other market segments, for example, or in other safety disciplines than ISO 26262. Also innovative methods, that's a bigger part where we think we need to focus on. So for example, over-the-air updates and update capabilities. So it might be possible to have a little risk when going into operation, but you can monitor it and update your system maybe. So that's a bit of risk balance. Also, model-based safety analysis would be something, or is something that we are discussing at the moment heavily, and where we as the Center of Competence are working on. Then artificial intelligence to support us in the safety analysis, so as generative AI, so as a tool for development purposes. But you could also use AI also for failure detection, so you can monitor your vehicle with artificial intelligence. Is it behaving as it did before, or do we have a slightly deviation? You can also use AI for that. And digital twins is something that we at the moment do not have too much in our development, but I think that could be done more, also for the safety purposes. At the moment, we are always thinking, okay, the digital twin might be something critical. Does it really reflect the reality or not? But at the end, I think to do something against that conflict that I've shown before, that would be a good way maybe. So innovation is the key in maintaining the high quality that we have for safety with a reduced effort. And with that, I would hand over to Martin.
Thanks, Roman. Hi, everyone. Thanks for being here. Okay, through the couple of slides which Roman shared, we learned that systems get more complex, and also the safety analysis get more complex. And now the question would be what to do. So, because we learned also in previous presentations that development cycles are around 3 to even 5 years until you get a car on the road. One of the topics is maybe thinking, how do others cope with the situation of increasing complexities, right? And so market observation as a source of innovation would be the one of the to-dos. For example, in the medical field, there you don't really have the capacity and the possibilities to do extensive tests. Of course you test, however not with the number of patients you desire to test. Also in aviation or rocket science, you cannot build the same amount of samples in airplane facilities like you do in the automotive industries with ECUs. And also new standards like ZOTIF. Actually, you are forced to go on the road with a system where you cannot fully estimate all the use cases and scenarios the system will be coping with, right? So maybe in these fields we find a couple of topics and methods which we could apply in our domain as well. One of the examples would be model-based system engineering. The basic idea behind this is to increase the amount of simulation or to extend the amount of simulation while reducing the amount or effort in the actual physical build-up of samples. So here you're increasing the system design, so the model-based system design, down to your actual nearly hardware design, and then you are able to have an early integration. You could also generate a fault tree analysis on the basis of your model. You can perform FMEAs or functional hazard analysis while still being in your system or in your model. Sorry, I'm confused with the pointer, which is strange. Which leads us, while in these areas you're in your system model, which gives us the opportunity to use the same model in this area here, which is in verification and validation with the digital twin. So here you have your model-based system engineering. You could then perform also safety analysis first on your model, and then of course validating these analysis on your hardware and software, your actual physical hardware and software. And then also using basically a virtual representation of your real system as a source of validating or starting to validating your system. This gives us the opportunity to have a very early detection of faults during development and the validation of system mechanisms without actually physical testing. So nowadays, if we build ECUs or systems in real life, we have a vast amount of testing effort, right? And this is really necessary. However, if we could increase the effort in the simulation or in the virtual field, we might be able to use that for also virtual tests in the virtual environment. Because our gain is to speed up, to gain efficiency, to have shorter development cycles, and maybe that's one of these possibilities. Of course, AI is now all with us, all in our hands, and which also gives opportunities in the field of safety management. And maybe not only opportunities, but also challenges, because it's something like a black box nature. You don't really know what's the artificial intelligence doing. If you're putting AI into a product, the training topic needs to be freezed once you release it, because otherwise the output is not deterministic anymore. So we have a lot of potentials, opportunities. However, we need to use them right. We could, for example, automate the fault detection and diagnosis. We could enhance and see if the test scenario and the test coverage is sufficient. So AI could be used to analyze large amount of data and maybe to generate summaries. That's what I think AI can do most efficient and most effectively. Of course, we need to consider regulatory aspects. So the 2622 was not, of course, designed for AI, but their new standards are approaching. In the domain of validation, AI could be a very good source of optimizing and making topics more efficient. These are the opportunities, however, combined also with, of course, challenges. As I said, if you're dealing with Automotive, you're forced to get on the road while not having the full coverage of all the use cases your system will be coping with. And there, over-the-air updates could be used also in the safety domain. Of course, rapid safety fixes could be an opportunity, continuous improvement. You could scale up your rollouts if you wish, or also integrate the digital twin to have their increase in efficiency. Of course, while doing that, of course, they are out there nowadays as well. we have to deal with some kind of challenges, because how to verify these updates? So verification and validation is somehow a challenge. We have to face cybersecurity risks, regulatory compliance, and last but not least, we need to ensure that all the vehicles that need actually an update or a safety fix, that these updates are actually performed and done. So maybe some cars don't have internet connection for 2 weeks or so, which we don't know. Right. Concerning AI, there's, I think, a fundamental question which I would like to raise, because AI offers, of course, opportunities, but also risks. And if we talk about ISO work products, which we saw also on a previous slide, you know that with HARA, FMEA, and all those work products, they clearly could be generated by FI, by artificial intelligence, of course. However, is that really what we want? And also safety assessments. It's kind of easy to perform a safety assessment on work products with AI. However, we favorite an AI-assisted, because the safety argumentation behind all those work products is, I think, more important than the actual work product itself. So systems need to be safe and not necessarily only being generated. Which brings me to the conclusion. Standards are essential, very important, need to be essential. However, we might desire and anticipate to look for alternative methods and to apply these methods to gain speed, efficiency, and to reduce the amount of time which we need for a development cycle. Okay, thanks very much. And
Okay.
Hello. My name is Kostas Andriotis. I'm from Nidec Automation. I think my question goes mainly to Roman. It's a system-level question. So I like a lot your innovative approach of this, and I'd like to ask on that. Have you considered simplicity as the innovation solution to complex things that we try to achieve? I mean, nowadays in semiconductor area, they are performing a lot of efforts to put systems on a chip. And therefore, that may trigger the simplicity in a system level as an approach. That may be something to consider as reducing the time to market. And that is questionable for you. It's something that you consider as an innovative solution for the future? Because I see a lot of complex things to do, and a lot of things to cover. But that's something that we see happening. Is there another way to get there? I simplify things, or it's out of...
I'm not sure if I got the question right. So you mean if we can simplify our products?
Yeah, the system. In a system level nowadays, can we simplify things?
Yeah, somehow yes. I mean, parts of it are simplified already. I think also the architecture that I've shown, the server-based architecture, is also something that should simplify at the end the whole system of systems what we have, because you have less wires and so on. So that's basically less data flow also through the whole vehicle at the end. So this is one step in that direction. For more simplification, of course, we always try to do our products as simple as possible in order to have them cheap at the end also, with less parts. I'm not sure if that is really possible to do the systems more simple as we try to have them already.
Okay, online, do we have someone online? No? Okay.
Hey, I'm Alexander Matausch from Electrobit. First one comment saying to the application servers, making it more simple. We built one, they don't. It just shift the complexity. But you said said about AI. So how do you separate between AI running on the target, where this PAS 8800 is applicable, and AI used during development? So in the slides, it was a bit mixed to me, but how do you do this in your company?
I mean, the easiest thing all of us know is like ChatGPT, so or Copilot. So at ZF we use Copilot, for example. So we already make use of that. So if you prepare a presentation, for example, not this one, of course, this one is really done completely with our own brains. But you could use it, of course, also for presentations or for speeches, or if you prepare me, I don't know, some stuff. So as we use it also in private life. So for that we use, of course, AI already today, and you can also use those AI tools or those agents. Then we also build agents that help us in development. For example, we have a prototype for FMEA failure models and so on. So this is what we thought about when using AI during development. And the other one is, of course, what you said also in the field. So smart sensors, for example, is also something we are discussing, or we are having projects with. Then we have AI also in autonomous vehicles and so on. So that is basically the difference.
How do you verify them? What I learned about ChatGPT and so on, don't ever trust them.
Yeah, that's true. Of course, tool qualification is then also a topic. So that would be the way we are doing it.
So, okay, unfortunately, last question, and then we need to move. Sorry.
Yeah, I think that will be anyways continued in the coffee session there. My name is Claudius Jordan from ModelWise. Talking about AI and about how to use that in the development process. Last week at Safetronic, there was an intelligent comment about the burden and all the requirements in terms of increased requirements and increased checklists that we need to follow for making the product safer. And it was basically engage brain and keep brain engaged is the bottom line of all of them, right? And I think that solves a lot of the problems that you mentioned. My question that I wanted to come to is, you're talking about AI, and I think the burden of today's ChatGPT era is that everyone thinks AI is only those chatbots. Which other ideas do you follow, now that you also mentioned the digital twin, the model-based safety analysis and those kind of things? There was AI also before ChatGPT. Do you consider that as well in your developments?
Sure. Sure.
Yeah. And if so, what sort of, let's say, reasoning that is not ChatGPT based do you use?
Of course, there was, or AI is not ChatGPT or Copilot. And combination between AI and model-based system engineering could also be thoughtful, but I just didn't want to mix up the topics in the slides. So generally, yes, that's possible, and also applied. I don't know if that answers the question.
But okay, maybe we can talk a bit more during the break and in the evening. Okay, many thanks. Yeah, sorry, I cannot give the microphone to everyone, but we have time later on. Okay, do we have Phil? Yes. Hey, hi Phil.
Hello.
So I don't know if I need to introduce you, but Phil Koopman is faculty emeritus Carnegie Mellon. He's internationally recognized expert for autonomous vehicles. I think you should know him very well. What can I say? Was one of the father, or is the father of the UL 4600. And he also received the Industry Legend Award in 2024 for Self-Driving Industry Awards. So, Phil, floor is yours.
Thank you. I'm sharing. Oh, there it is. Okay, great. Hi, everyone. Sorry I can't be there in person. I'm in the US, but good. It's still morning for both of us, so good morning. Thanks for having me there remotely. I'm going to talk about embodied AI safety for 25 minutes, and then I guess we'll have a break, but I'll be back for a panel, so there'll be more time for Q&A at that point as well. So let's see if I can get this thing working here. Okay, there we go. Let me talk about the motivation for embodied AI safety. So first of all, embodied AI is AI added to what you might have called an embedded system before. So there's an actuators plus compute, and in particular, the type of AI I'm talking about is machine learning-based AI. Per the previous discussion, this encompasses chatbots, but also encompasses end-to-end machine learning and all the other things. And the question is, why would you use AI? Well, if you're on a robot, you need to do perception tasks, and those resisted the efforts of computer science. I remember getting my first classroom lesson as a student taking an AI course in 1981, and they talked about perception then, and it was terrible then. And machine learning makes it work, so that's pretty cool. Natural language interface, again, I was working on natural language interfaces back in the 90s, and yeah, okay, but it was pretty clunky, and machine learning just makes that really easy now. And dealing with unstructured open world environment, which are all things you really want robots to be able to do. And machine learning makes it possible to do those very high percentages, not 100%. That's the rub. Now, if we have a toy robot or something that really has no ability to affect the outside environment, setting aside all the ChatGPT psychological health issues, really how much harm can it do in the physical world? But if you give it a hammer and tell it to start beating on things, now safety becomes much more of an issue. Physical safety becomes a real issue. Physical AI means physical safety. And so you start getting questions like, how safe is safe enough? And where is the accountability for harm if it does something wrong? And how do we instill trust in the technology? So what I'm going to do for the next few minutes is talk about expanding everyone's horizons about how they think about embodied AI safety. For folks in the automotive industry, you've probably heard of positive risk balance. If you work in this area, the notion that you want to be at least as safe as a human driver if it's a self-driving car, or at least as safe as a human operator. If you're reading medical images, you want to have the same error rate as a human reading medical images, and so on. That only is the beginning. So there's two parts here. The first are the skill sets, and the second part is the types of challenges that arise. But let me start with just some background to make sure everyone understands this. Computers are not necessarily safer. People will say, well, human operators make mistakes. Human operators drive drunk, they drive distracted, therefore computers will be better. Well, anyone who says that must never have really used computers and watched them make mistakes too. Computers make mistakes for different reasons. We call them software bugs, right? Or hardware failures, but they're not perfect. Computers make mistakes too. But just to make sure this is graphically illustrated, here is a Waymo robotaxi running into a utility pole. Now, you can see, if you look carefully, you can see, let's see the pointer. No, the pointer's not doing anything interesting. So if you can see at the base of that utility pole, there's a little piece of grass, and there's a utility pole. It turns out that inside a robotaxi, you have to tell it which things are okay to hit and which are not. You don't want it to be afraid of that little piece of grass and say, you can't hit the piece of grass. So it says, all right, there's an object, it's like a little shrub, that class of objects is okay to hit. And somebody had programmed in utility poles to also be okay to hit. So it saw the utility pole and says, it's okay to hit, just like that piece of grass, and it hit it. Why was this not discovered in testing? Well, you can see there's no curb around this utility pole. It's in a parking alley. And what had happened was it was programmed not to hit curbs, but it thought utility poles were okay to hit. And this is the first time it had chanced into being able to hit a utility pole not protected by a curb, and it hit it. Was it drinking? No. Was it distracted? No. If this were not a Waymo, if this were a human vehicle, you might have supposed that's what happened, and you might be right. But this was a software defect. Here's a picture of a cruise robotaxi running into the back of a bus. The short version is it had been programmed that all buses were 40 feet long, measuring from the front bumper going backward. This was a 60-foot bus. So it saw the front of a 60-foot bus. It knew all buses were 40 feet long. It measured 40 feet back and said that 20 feet, whatever I'm seeing, must be a hallucination, so I'm going to run into it straight up software defect. So it turns out computers that do embodied AI are going to have software defects. And if you don't believe me, there's plenty of photographs of stuff, weird stuff happening. They're going to have software defects. And so now the question is not, are humans bad? The question is, are computers less bad than humans? So to understand that, to understand how to get that safety equation right, you need 4 concepts. The first one is about safety engineering, concept number 1. Now, I'm talking to a room full of people who probably know about this, so I'll do the short version. But depending which audience I talk to, there's one of these 4 concepts or more that they don't know a lot about or are weak in or don't really consider. And the point I'm going to come to is you need to do all 4 concepts for safety engineering. Oh, I'm sorry, for embodied AI safety. So safety engineering, it's all about risk mitigation. You identify hazards and risk, and you mitigate the hazards and validate mitigation. In the automotive world, it's HERA, right? But here's the takeaway. If you're not actually creating a list of hazards, you're not doing safety engineering. So if you run around and you have a self-driving car or you have a robot and your plan is to test it for a few thousand hours, and if nothing bad happens in a few thousand hours, you must be safe, and you've not written down a list of hazards and checked that each hazard is actually mitigated, you're not doing safety engineering, you're just messing around. And that's important because we see a lot of folks in the robotics and embodied AI world who don't understand this and just mess around and say, well, haven't killed anyone yet, must be safe. There's some technical areas, so safety engineering isn't about redundancy. Redundancy is a tool that you use when necessary, but safety engineering is about that hazard analysis. And you have safety standards for engineering rigor. I did a picture of someone on a rope. It turns out there are 2 ropes because ropes break. And every piece of gear you can see on the internet, there's a safety standard for how you build it, how you test it. It's really quite an evolved, mature area of safety. The design assurance beyond just testing, when you test a piece of rope, when you stretch it, it causes failure to the rope. So you cannot test a rope to near its breaking point and use the rope ever again. So you need some sort of consistency in design process, manufacturing process, and batch testing. And it's very sophisticated, the same kind of stuff you would see in automotive, the same kind of stuff you would see in other areas. You also need safety culture and independence. So this is safety engineering in one slide. There's a recorded version of this talk, the hour-long version on the web. And if you ever need to explain safety engineering to someone who has no idea, maybe this slide, recorded version of this slide is a starting point. Moving on. Okay, cybersecurity engineering. I'm not going to do all of cybersecurity engineering, but I'll point out that security is a problem. If the security attacker can compromise the safety, you've got a safety problem. What you often see in cybersecurity is people say, well, I'm doing encryption, so I must be secure. And they have not paused to ask what does secure really mean. And the issue is for embodied AI safety, security is less about confidentiality. The right turn signal is on. Everyone knows you're going to turn right. Why is this a secret? It's not a secret. Encrypting that doesn't really help anything. What you care about is integrity and availability. So if you're encrypting your data traffic between a vehicle and a traffic light, you're encrypting it to keep it secret. Nobody cares. What you need is making sure that no one's modified it and to know that it's authentic, which are different properties that don't necessarily require encryption. So the embodied AI emphasis is on safety, integrity, and availability. The way I like to look at security attacks in the cybersecurity area for embodied AI is that they're malicious faults. So if you have a safety case, a structured argument supported by evidence that the system is fit for purpose, what a security attack looks like in terms of a safety case is that there's a fault missing from the hazard analysis and you're going to introduce the fault. Oh, we didn't think about stop signs that have been altered, manipulated, covered by snow, had white tape painted on them. We didn't think about modified stop signs, so I'm going to introduce that fault and try and trick the vehicle. We violate safety analysis assumptions. There's an assumption that a certain thing will be rare. Well, the attacker's job is to make it not so rare. And an important thing to note here is the adversary often has physical access. When you're looking at traditional IT security, they assume the machine is in a guarded machine room and nobody can get at it. And that's not true of an embodied AI system. So you see attacks on vehicles where people are tapping into the CAN network by pulling out a headlight or breaking off a mirror or drilling a hole in the body. And so there's some additional security, traditional security things to worry about involving, a person can attack it, or if they're trying to compromise a secret password, they can buy one and reverse engineer it. So those are additional considerations. The fourth area you have to know about is machine learning concepts. I'm going to do the super short version, but the idea is you feed systems lots of data and it learns statistical properties. It does not learn facts. It does not learn structure directly. It just learns statistical properties. It generates statistically plausible results. Now, if you have a lot of data in a very large machine learning model, you can do really impressive stuff. There's different flavors like classification. Is it a car? Is it a person? And for those of you with kids who've seen Mitchell's versus the Machines, there's an animated dog that looks really weird, and a plot device is the robots get confused. Is it a dog? Is it a pig? Is it a loaf of bread? And they decide loaf of bread. And this illustrates in real life the important thing. If a machine learning system says that's a person, it's not saying it's a person. What it's saying is the thing I'm looking at is more statistically similar to people than other things I've been trained on. And that difference matters. The reason is if it doesn't know what a person is, it just has a bunch of examples. If you don't look like an example, you've got a problem because it does not know you're a person and it's not going to stop for you or react accordingly. There's generative art where you start with some random noise. And this is the simple version, of course. You start with random noise and say, well, I want a picture of a cat, a black cat drawn in the style of Picasso. And it statistically says, well, that's about 3%, I'm making up numbers, 3% catness and 1% Picasso-ness. And it randomly perturbs the pixels, and it says, oh, that one's now 4% catness and 2% Picasso-ness. I'm going to keep that one. And it just hill climbs randomly till you get a picture that looks plausibly like it was a black cat drawn by Picasso, but it's not authentic. It just statistically matches those kind of works. There's LLMs, large language models, and foundation models, ChatGPT. And what they do is predict the next likely output in a sequence. They do amazing, amazing work, but it is just predicting next likely output in a sequence with very, very deep, very, very sophisticated statistical analysis. Now, here's the important thing to keep in mind. It's all statistically plausible, which is different than true. Is it artificial intelligence? No, it is not. It's not artificial intelligence. It's not intelligent. It's statistical models. Some people would argue that statistical models are an approximate simulation of intelligence. It's an interesting discussion we're not going to go further on, but there's an important way to look at this. Back a long time ago, there was the Turing test. Hopefully you've heard of the Turing test. Turing test is that if there's a person and they're typing into a computer terminal and there's a thing on the other side of the terminal, if the thing can convince the person that the other thing is also human, it wins the Turing test. Well, it turns out we've known since the 1970s this test has a problem. There's a program called ELIZA with a Z. Go look it up if you haven't heard of it. The ELIZA program was a very hacked up set of heuristics in just traditional programming. I remember seeing the source code back in the 70s. And what it would do is it would pretend to be in a conversation and it would fool a small fraction of people some of the time. And what has happened over the years is an increasing number of fractions of people are fooled. It turns out that the Turing test is not a great test of intelligence because none of these things were really intelligent, but they got better at fooling people. The Turing test turns out to be a great measure of human gullibility, of whether you can trick a person into thinking the other thing is intelligent rather than actual intelligence. Okay, let me take a stop here. We've done 3 of the 4 areas, but this is a really important thing. You've all seen the V. You're at a safety conference. You know about the Z. You know about the V. Let's talk about for a minute why the V really works, because it's important to clarify this, and this really helps with machine learning. On the left side, you trace the requirements to the implementation. You do some validation across the top that each level of requirements is traced to validation, and this is V Process 101. But the important thing to keep in mind is testing never proved anything safe just by testing anything complex because it takes too many tests. So when you test in the V for safety, you're doing tests that trace back to specific things on the left-hand side. You're not testing everything. And the reason this works conceptually is the engineering rigor on the left-hand side. So ACLD has a high expectation of engineering rigor, C, B, and A not as much. The engineering rigor on the left-hand side has set an expectation of correctness. And so think of it as a Bayesian prior. If you have a high Bayesian prior expectation of correctness, then you need less test evidence on the right-hand side. So the higher prior expectation, the less test evidence you need, and that's why the V works without exhaustive testing. But the problem is when you put in machine learning, it breaks the traceability from the left side to the right side. I have some requirements. Okay, cool. I have a list of scenarios. Okay, cool. I train the machine learning on whatever data I have laying around. So I didn't say I trained it on scenarios. I just trained it on whatever I have laying around. There's no expectation of correctness. It does what it does, and the testing is there to see what did I build, as opposed to confirming that I built the thing I thought I built and that the engineering rigor is there. So machine learning breaks the chain of reasoning from the left-hand side to the right-hand side. Now you can backstop this with process, and that's why we have ISO 5083, ISO 8800. We have those kind of process standards in, but they're still maturing. But that's why machine learning is so challenging, is because it breaks the causal relationship between engineering rigor on the left and the ability to test with very few test cases to confirm a strong prior expectation of safety. Okay, the fourth area is humans and AI safety. So we're going to have inherent limitations as supervisors. So people are bad at supervising complex technology. They're terrible at it. They have a thing called perception response time, is how long it takes them to respond. There's a thing called the ironies of automation that lengthens the perception response time. And people suffer from automation complacency and bias. Those are all well-known psychological things, but folks who build computer systems aren't necessarily that well informed about this stuff. But the idea is, if something weird happens and you have to react to it, and it's high probability of killing you or something like that. And hey, by the way, this thing has behaved well for, I don't know, for the last 1,000 hours. And what do you do about this? Well, people are terrible. 10 seconds, not enough. It's more like 40, 50 seconds. And so I'm running a little bit long on time, so I'll make sure I get to an interesting end. Effective automation gives you ineffective supervision. So that's the thing. Effective automation gives you ineffective supervision. And when you're looking at your cell phone is not a lack of moral fiber. It's what humans do when they're bored. And expecting people to act differently is being unreasonable. They're going to look at your phone unless you actively prevent them. There's some serious ethical and legal issues. I haven't had time. I'm not going to have time to go into the ethics, but who's responsible for the embodied AI misbehavior? It has to be the manufacturer, because people are not going to be good at supervising these things. The manufacturers cannot like that. They can fight all they want, but in the end, 5 years from now, 10 years from now, the manufacturers will be responsible for embodied AI misbehaviors, whether it's a car or a robot or anything else. And blaming humans for being imperfect at watching boring automation won't make it safe. It is just a denial of basic human nature. There's a thing called a moral crumple zone strategy, which is our plan is to blame the people when the technology fails, and that doesn't give you safety. It may give you some protection from legal liability, but it won't actually make it safe. Okay, so I'm going to stop on this slide, but this is an important one. If you know those four things, you have to avoid risk hotspots. The important thing is safer than human operator is only the starting point. You also have to consider things like specific unsafe behaviors, risk transfer onto the vulnerable, harm due to embodied AI negligence, avoiding negative externalities, compensating for others' mistakes, personal and psychological safety. I have a whole hour-long talk on YouTube where I go through these things in details, and I think some of this I may have talked about last year, but it's really matured in the up to now from a year. Let me give you a hypothetical example that sort of mashes all these together to prove to you. If you thought that Well, I'll use US numbers, which is worse than Europe for sure. In the US, about 40,000 people die every year from automotive mishaps. And there's a lot of fatality rates in other areas like medical. I mean, a lot of patients get lost, many from avoidable mistakes. So depending where your embodied AI is deploying, there are problems. And you could say, well, if we're as good as a human driver, if as good as a human physician, if we're as good as a human equipment operator, then it must be okay. But let me give you an example from automotive about why that's not going to work. Let's say that hypothetically, you could take 40,000 fatalities down to 20,000, and engineers' first reaction is say, well, you cut the fatalities in half. That's got to be a win, and we don't care about anything else because we saved 20,000 lives. You may say that, you may think that as an engineer, but what if out of those 20,000, every single one of them was a person who would not have died if it was a human driver? Because, for example, all 20,000, this is hypothetical, this is over the top, this is to make the point. All 20,000 fatalities were a child in a marked crosswalk, and the robotaxi ran through a red light and killed a child in a crosswalk without stopping. All 20,000. Nobody's going to sit still for that. They're going to have a problem with that. Now, I didn't say that's what's going to happen. What I said was there's more to this than the total number because societal acceptance also matters. And they're not going to like that you ran a red light to kill someone. Why did you run a red light? They're not going to like that only children are dying and nobody else. They're not going to like that only pedestrians are dying and not people in the car. Those are all going to be problems. So risk hotspots, particular areas of risk that concentrate on a certain victim demographic or associated with certain behaviors are not going to be acceptable, even if, in theory, you're just as safe. So I'm going to stop right there. I'm going to point out that this talk comes from my newest book, Embodied AI Safety. I have a couple older books, and I'll switch over to Q&A.
Thank you, Phil. So potentially one or two questions. Okay, one here.
Yes, hi, thank you. Ioannis Sorokos from Fraunhofer IESE. I assume, based on what I heard in your previous talks, is that some people advocating for end-to-end AI control of vehicles are maybe not looking at realistic a vision, perhaps. But what are your thoughts on this?
I think end-to-end AI is controversial. I'll give you the short version. There are two points. The first point is the way I expect it to work is end-to-end machine learning will be much superior, faster, easier to get going for the first 90%, or even the first 99%. That remains to be seen. And so it's going to take fewer people. You can get on the road. You can do things. If whatever you're building, whatever robot you're building, you can get it working 99% much, much easier because you're not labeling data, you're not building the boxes, you're not handwriting all the glue code. But I like to say there's the first 99% and the other 99%. The other 99% is going to be hard because edge cases and exceptions and context-dependent specifics are going to be very difficult. You can't run a line of code saying, oh, if you're in New York City, you're not allowed to turn right on red lights, but everywhere else you are. You're going to have to go find training data that says, well, it's in New York, and it has to infer the rule for itself. Now, there are hybrid methods you can try, and some folks are doing that, but I expect end-to-end machine learning to be very difficult on the edge cases, and I expect the explainability you're seeing, oh, it'll explain what it's doing. How do you know it's not just telling you a bedtime story that's uncoupled with the actions? You don't know that unless you do something special. So validation is going to be harder, and edge cases are going to be harder, is my prediction, and we'll see how it turns out.
Okay, okay, one last question here.
Melih Atasever, again, Bosch GmbH. In today's systems, we test a device with an application software. It does not change until we update it. But however, in AI system, we will test a device with a certain time and release the product in the market. What happens? Decision-making process has somehow changed with a self-learning and feedback mechanism of AI. How can we challenge it?
Well, what I hear about for safety critical operations today is that once you release the machine learning to the environment, it is not going to change. Now, let's talk about deep learning and things like this. Once you fix the model weights, there is no learning in the field. So if somebody says, my Tesla learned how to do that, that's ridiculous. The Tesla didn't learn anything until the new software version came out. So right now, there's an opportunity to revalidate before you deploy new software. If you have a large foundation model, large language model, and you're putting out sophisticated prompts, and the prompts are changing its behavior, the stricter question is, how can the recent experience change the new experience if it's using it as a prompt stream? That's an interesting question, and it's a good reason not to use that kind of technology in safety critical applications, because if you can get wildly different behaviors based on prompt elements that you don't control that are put in by the environment, then I don't know how you would say that that system is safe. So that's a good concern, but it's a little narrower than all machine learning. It's only for machine learning that has a feedback loop that changes behavior based on what it's seeing outside.
Okay, so I would like to stop here. So again, thank you, Phil. So we have now a short coffee break, but then we are back here again with Phil and others. So please be on time to start 11:15. Thank you.
Can you turn on okay. One small announcement from our side. Those for you, it's to those who were late. So if you could just come to the registration desk and place your signature, because I saw some people were coming in. It's just for our information. Thank you. And don't forget to fill out the evaluation forms. It's very important. Thank you.
Sorry.
Er läuft in der Timer-Runde. Okay.
1, 2, 1, 2. Okay, guys. Can you take your seat? Okay. Can we start again? Do we have a Phil again? Is Phil online? Okay, perfect. Okay, you can take your seat if you want. You can sit. So, yeah, we're going now into a panel. Okay, so a panel about ensuring AI safety and ethical decision making in automotive systems. We have again Phil. On top we have Dr. Max Walter. He's a principal key expert functional safety at Siemens. So he's not really automotive guy, but today you are wearing automotive hat. Or he's bringing a different view on the topic. And on top we have Helen Buchomensky, okay, Director of Global Functional Safety and Compliance at ARM. Good. So thank you for joining. And again, I would like to start with maybe one question from my side here that you can see already, but then it's a panel. So I really would like also you guys here to interact. And I also would like the people online. I know we have around 8 to 10 people online. Please raise your hand, your digital hand, and ask questions. Okay, the first topic is about explainability. I mean, we are talking about artificial intelligence. Phil already gave a nice talk about the issues and challenges. And one is explainability of AI-driven safety decision. Do you want to comment on this? Maybe let's start here.
Yes, thank you. So first of all, Ricardo, thank you for the introduction. And I want to emphasize again that I'm not from automotive industry, but from factory automation. But of course, in many aspects, we have similar problems. We have things that can fail. And we want to use AI. For example, in the factory automation, one good example for making use of AI is saws, like a buzz saw. And they are nowadays able to detect if you move your finger into the buzz saw, and then they are able to stop the saw. That is something we would not be able to solve 4 years ago without AI. So then we have, of course, the challenge also to make these things safe, because the person who's using the saw has, I think, the right that we do everything we can to make this system as safe and reliable as possible. And now the question about explainability. I think it's an interesting question already, because that shows that when we design safety systems today, we always assume that we understand how they work. That's how traditional systems engineering works. Yeah? So of course, if we create a system as an engineer, we assume we understand how it works. And I think this is not necessarily the case when we talk about AI. So typically we don't understand how it works. Yeah? We train the AI system, and after that it does what it should do, maybe not to 100%, but maybe 90% or 95%. But typically we don't understand how it works, how it does that. We can observe that it does or not, but we will not understand how it does. Similar as biological systems. If we look at biological systems, we also don't understand how they are doing that. We can try to figure this out, but it's different from things we have created by ourselves in classical engineering. Now the question is, do we need to understand these things to come to the conclusion that they are safe. So if I am using a bus in the morning, I'm relying on the bus driver, and I do that, and I have the trust in the bus driver, although I don't have any idea how the bus driver is actually working. So I trust the system which employs the bus driver. He has to have, of course, a driving license. They check this driving license in periodic intervals and so on. So even if I don't know how the bus driver works, I trust this. And this is, I think, the question: can we do that for AI or not? And I think explainability may be one part of that, but I think we will not be able to fully understand AI systems. And even if we could, then somebody else would come with the next generation, which has higher performance, even safer and so on. And then we can start again. And this, I think we will never be able to fully understand that. So we have to live with the fact that we cannot understand it and nevertheless use it as a safety device.
Yeah, at the point, okay, if I can comment, then maybe also Helen and Phil. In the case of the bus driver, okay, you cannot understand, but you are the user. You are not responsible. So if something happens, finally, you are not the one going through liability issues and you have to justify. In the case of the AI, and we are the responsible developers, so we are the responsible in assessing that the product is safe, I think if we don't understand, we have a gap. Now, of course, knowing what we don't know may also help us to make a decision how to make it safe. But I think the examples maybe are a bit different. For me, you need to know what you know. You need to know what you don't know.
I agree, yeah. No, it's interesting. Thank you so much, by the way, Ricardo and Phil. Your presentation was fantastic. I'm still thinking about many of those ideas. In ARM, we started to play, as everyone, with AI in our safety life cycle. And one of the things which we started to work, and I'll talk more about this in my presentation as well, is how this safe for safety AI should look like and what should be those requirements. And what we try to do here is, as Ricardo just mentioned, right, we do want to know what's happening there. I thought we cannot control everything, but like you create a deterministic model, you want to create boundaries and put everything which is unknown, stochastic, on the side, but you want to create some clarity on of determinism of what you can control. So a few things which we do, for example, would be to set up very clear rules for AI to follow, and define very clear workflow for AI to follow. We also make those rules and those workflows very transparent to users. So for example, if we run our AI assistant, it's not so, for example, if you just use ChatGPT today, and by the way, it happens to me always. I stopped using ChatGPT at the moment for emails because, for example, you would put your text and ask ChatGPT, can you make it a bit better? And it would make it a bit better, but then it would replace one word with another word. So last week, it changed a word, let's do it together, in my text, to let's accelerate the work, which leads to a bit of escalation with the people who got it. I didn't mean to use the word accelerate, right? But AI thought it would be a nice word. So I stopped using AI for those things, but what we do in safety life cycle, we really define to AI what to check. We also apply static analysis where we can, right? Because everything which can be done by static analysis, it's like a waste of energy, time, efforts to use AI for it. But also it really helps us to get proper responses, reduce this hallucination, right? So for example, we were discussing also on the coffee break, when I ask AI to check if my tailoring of safety standard to my project was done correctly, I would make sure that AI would not give suggestions. I would make sure that AI would not do consultation, but more act as independent reviewer, which activates human judgment. So this is what I do. I want to activate human judgment. I want human to be smarter by using of AI, not because AI would tell them what is the right thing to do, but ask the right question to follow and think about the problems which AI may spot. right? But this is how we control it. And what is happening there is as transparent as possible to users who are also part of this development of those tools.
Anything you want to add, Phil? Or we go to the next question?
Thanks. I think the reason we need explainability is because statistical proofs of safety are impractical. So you can watch a bus drive on time 100 times in a row, and that tells you it's a pretty good bus, but it says nothing about if you literally die if the bus doesn't show up once a year. That's not enough data to know, right? So that's the issue. And so we want explainability because intuitively, well, if it can explain what it's doing, then that gives us insight to reason about safety. The pitfall here is that explainability is not necessarily telling you what's really going in. In my talk, I said that the LLMs, chatbots, are not intelligent. They're just good at fooling us into thinking they're intelligent. And the risk is having an explanation system fooling you into thinking it's explaining when it's just making stuff up. There may be no correlation between what's happening in the explanation in unusual cases, which is where safety lives. I think explainability can be really great for debugging bad behavior. If it's right 9 times out of 10, that's still a win for debugging, but no one ever got safety by taking a terrible system and making it less terrible. And so the real issue is how do you get ultra quality to life-critical safety? And I don't think explainability gets us there. I think it's just another tool for debugging. The way I recommend approaching this is that, as I mentioned, machine learning breaks the V. Well, what's the answer? The answer is to not try and trace code or detailed behaviors through the V, but rather trace the safety case through the V. If validation is there to prove the safety case has integrity, then you have a complete link back to the left side of the V. So you're not trying to validate the code, you're trying to validate the safety case. And if you look at it that way, it fixes a lot of these problems, and explainability certainly can be a part of that, realizing it will be imperfect as all machine learning is.
But I think as a community, we need to realize that AI is enabling things that in the past were not possible. I mean, in the past there were I saw some videos about suspensions. Suspension using AI was great comparing to conventional suspension because it could really predict. But the point again, how much do we want to push the envelope? When it's okay to say, yes, I can use AI, and when no, the risks are not acceptable. Do you want to comment on this?
No, I'm still thinking, I think it's super related to your question, Ricardo, to what Phil just said, right? Because if our safety case is safe, right, so we can use AI, right? I really want to hear more how it's all related to those cases, and it would be very interesting to see how it's proven in the future, right? But I would say I fully certain and that we all will have AI everywhere, right? So it's all coming. I don't think there would be any case where we are not going to have AI.
Yeah, I think we need AI, but we need to use it safely.
Yeah.
So I think here we have to distinguish between the cases where we're using the AI during the runtime of the system, like AI-based vision systems, or AI systems which are used in the development life cycle. So maybe let's focus on the development life cycle. If we use LLMs here, there's, I think, one flaw which hasn't been mentioned yet. So LLMs work, they read a lot of text, and then they try to somehow understand it in the training, and they give you an answer based on your prompt, only based on the text they have read. That's how human scholars worked 500 years ago. So if you had these scholars before or in the Renaissance, they were scholars, they had read a lot of text, and they tried to conclude from all this summary of text when they were asked something. Nowadays, especially we as engineers, we know, of course, that will not work. You have to do experiments which are reproducible, and you have to, and we are doing that in safety. We have this validation, we do the experiments, we do testing, we do material testing, and so on, software testing. And an LLM alone cannot do that. No? So they can create code, but most of the time nowadays they are not able to at the same time generate the test code and perform the test. So they have to be embedded into a process where humans are also involved, and the overall process will then guarantee the safety. And of course, this is something we can now discuss. Should we empower the LLMs to be able by themselves, more than they are today, to also create and execute the tests or any kind of validation? And they are not doing that at the moment, but I think if we want to give them more trust, we have to empower them to do that.
But it's happening as well, and I already saw some examples how you can, as part of the workflow, have self-validations, and also after AI runs, it can run self-checks and improve it. So it's there, it's coming.
At the moment, it's giving you an answer, it's giving you a link without being able to check whether the link actually exists or not. It claims that it exists, but if you then ask, you find out, no, it is not even able to check it. Yeah? It just assumes that this link should be correct.
If I can add to this, the 2 points. One is, if you're going to use AI, you have to ask what's the cost of failure, because it is likely that it will fail on edge cases. It'll fail with low frequency, high severity things. And if the answer is the worst case is affordable, then go ahead, use AI. But if the worst case is catastrophic, you've got a problem, because you have to validate that rare high consequence events are handled, and machine learning being statistical, that's what it's worst at. Statistics are terrible at high severity rare events. And that's a fundamental challenge. In terms of LLMs, the catch with LLMs is saying, I'm going to have a person who's going to check the output, is setting that person up for failure, because people are terrible at that. And so that's why you see lawyers and judges filing court cases with fake references, is because they were in a hurry, they got complacent, and calling them bad people doesn't stop the next lawyer from doing it. We now have multiple lawyers, multiple judges doing this. Believe me, they've all heard the stories, but they still do it. Telling someone not to do something that human nature says they're going to do is never going to fix the problem. So that's really, if you're asking people to have superhuman behaviors, you should not be using AI, because you're going to fail.
And also probably a common misconception we have nowadays, that computers do not make many mistakes. Once they have been programmed to do it, they can repeat it without errors, and that is completely untrue for AI-based systems.
There's a reason that was like my second slide. Yes, I agree.
Okay, we got one question here.
So Alexander Matrosch from Electrobit. Actually, I would like to make this a little bit more complicated. Even you just mentioned you use AI to create tests and things like that, which is nice. But with the agentic systems that are coming up at the moment, there are already ideas of automating the complete development flow, from development to testing and iterating, and just having a human orchestrating this.
Good
and
luck.
On top of the explainability we had before, comes now that here we create a system which is highly complex by itself. So even without AI. So the question is, what are the ideas to control this, to understand this, to make sure that the outcome is still sensible?
Yeah, I would say it's similar to what we do today if we have a process which is done by humans, right? So you create some documents, then you have to do some review by different humans. So if you're now in the position of the manager, so the managers, I'm an expert, and the managers trust us experts, but they don't understand what we are talking about. Nevertheless, they have ways by setting up processes so that they, in the end, trust the team of experts or the bus drivers. So if you are in the position of the manager of the bus fleet, so you have to trust your driver, and you set up some kind of processes to do that. And I think if we are using AI in our safety process, development cycle together with humans, because probably at the beginning it will not be fully AI. We have to enforce these processes. The AI has to document its decisions. That does not mean that we understand the AI itself, but we understand the output of the AI. That's important in this aspect. And there must be tests which are repeatable, so I can now check by repeating these tests whether they give the result the AI has told me. Yeah? So it gives me a test script which I can then run by myself. Question is, will I do that for all the tests? Probably not, but for some, or at least for some, for checking it, and so on. So I think that is important. This is, I think, the explainability of the outcome is something different than the explainability of the AI model itself.
It's interesting, and I hear you, Alex. It's also, you know, sometimes people ask me, so what will happen? We won't have more software developers, everything would be done by AI, what people would be doing. So there's always this concern, what we will be doing. And I was also thinking, for me, it was very difficult to start using, for example, Waze. I really like to use maps. I really like to read maps, and then I don't think I can read a map today, so I feel like, but I become very addicted, right? So I don't think we can really navigate today, or how many of you really use maps and not using Google Map or Waze or tools like that. I think in terms of technology, at the end, humans would play very significant role in the era of AI, and we are already playing. It's maybe a bit not clear today, but you know, this concept of our goal in ARM is to reduce 80% of our work in function safety using automation, not only AI, but automation and in general scalability. And people ask me, so we will have 20% of work, does it mean that we will need 20% of people and everyone else going home? And I don't think so, right? Because what I think will happen is that 20% of huge value which we provide as human, with our human intelligence will become 100%, right? So we will accelerate our productivity, we will accelerate our ability to deliver, and we will be so much more smart in few years and able to check and prove the quality of AI, so not only trust, but also check what's happening there, and we will have those tools. So I really see how we all accelerate, and again, this word, using AI, and become even better, even more productive, even if AI would do the work from A to Z, from starting development, defining maybe even requirements at some point based on some use cases, and running the tests and self-creating those tests.
I think
sorry, Phil.
I think the notion of using AI to accelerate, to amplify people is interesting. I think the word trust came up, and I think trust is really critical here. If you are doing a process with people, you are trusting that the people are trying to be honest, to be truthful, and to execute the task correctly. They are imperfect at that. And so you need process checks and validation and things like this to catch mistakes and to pull out the 1 out of 100 or whatever the number is of people who just don't care about their job. But you assume that people are trying to do the right thing. LLM chatbot foundation model-based technology does not care if it tells the truth. It literally has no concept of truth. It has the concept of statistical consistency. And so people say this term Frankfurtian bullshit, right? And it's used in a clinical sense, which is it has reckless disregard for the truth. It just cares about consistency. So if you're trusting LLM-based technology to come up with a safety case, for example, how do you know that it's actually being diligent? You don't. It's just making stuff up. This is why you get references that don't exist. And I was just quoted in an article saying something that I didn't say, and I wasn't even mentioned in the article at reference at all. It was Missy Cummings, and it wasn't me. And they quoted me as saying the headline, which I never even saw till then. It just made stuff up, but it sounded totally believable. So the catch you have with using AI as an assistant is having trust in it to not just make stuff up, which is what it does now. And if you're trusting something that's just random garbage, how do you expect to get the acceleration? So it can be used, but establishing trust is really important. It isn't explainability that I care about, it's trust that I care about.
Yeah, I agree. And okay, moving more into AI in a product. So, I mean, can we say, we discussed this morning about a checklist approach, that many engineers like to have a checklist. So can we say now, if I'm taking the new standards, 8800, 5083, I can check my list and everything is done when they're using AI? What do you think about this? So are the standards we have right now providing the right tools to use and to enable the usage of AI, or we are still at the very beginning? Controversial question.
To answer it quick, I think we are still at the very beginning.
So I think we're at the beginning, but there's another nuance here, which is that the point of the checklist is not to check the boxes. I've heard horrible stories of safety processes where they they photocopied the checklists and just printed them because it saved time in not checking the boxes. And the point of checking the boxes is not to check the boxes. The point of the check the boxes is to encourage you to do the mental thinking process associated with the box. And so how do we trust that the LLM has actually done the correct process behind checking the box rather than learning, oh yeah, I'm going to check the box, and that way everyone's happy.
Yeah. Now, we discussed this morning, Phil, about this checklist approach, and we really said we should move away from this. Checklist is not for safety. Of course, it can help to understand, did I miss something important? So it's really a good checklist, or even something like a UL 4600, is help you to go through a process systematically and be sure you don't forget anything. But it's just one step.
So let me be specific here, because I used to drive submarines for a living, and we used checklists, and checklists literally saved our lives, okay? They are very useful in the right context. But the important thing is checklists are not there to prove you did something. Checklists are there to prevent the very well-known human failure of mistakes by omission. Mistakes by omission are 10 times more frequent than mistakes of commission, and checklists help with mistakes of omission. That's all they do. They don't prove safety. They prove that at least if you are paying attention and diligent, that you were forced to think about something, which has value. But if the point is to get the checklist done, then you have no value at all.
Yeah, I fully agree with this. And I also think that when we talk about boxes, it's really about safety culture, which was raised here already today. I truly believe that in the era of AI, safety culture would be even more important than before AI. We should be much more diligent. We should much more thoughtful. And it would be difficult, right? Because AI makes us a bit lazy. Right? It makes it a bit lazy. It's very easy to trust this, this very smart model which talks in this amazing confidence and gives you all those facts which you just check them and realize they completely don't make any sense, right? It would be much more difficult for us to be disciplined and think. And safety culture is about let's think, let's not do things automatically. So fully agree. Checklists are very, very good, but we should not follow on the checklists. We need to learn, maybe to think in a bit different way in this era of AI.
I agree with that sentiment, but let me push back very gently on one point. Everything you said is right, but I'm concerned about the language, because if you say that someone's lazy, it's like a moral judgment. And I would instead say that AI takes normal human nature, which is predisposed to doing the least effort possible, because that's what humans do, and enables and encourages us to follow normal human behavior. And the reason is telling someone not to be lazy has never fixed anyone who's lazy, at least that I've ever met, right? You need to give them a supportive environment where they are incentivized to do the things they need to do. So if we make this into a moral, which I know you didn't intend to do, but I'm just an important point. If you make this into a moral judgment of people that only bad people will fail at AI, everyone will fail at AI.
Everyone, I fully agree with you, because this is our nature. This is fully our nature.
Exactly
and
my point.
I use this word, right, because I feel
that's fine. But I think it's important that everyone understands that this is the point, that human nature is here.
Thank you for clarification, yeah?
Well, and thank you. Great discussion.
Okay, we have one question here.
Yeah, let's say with the reduction in the development time, how...
Can you just say, sorry, name a company?
Yeah, Chaitra from Continental or Aumovio. So with the reduction in development time, how can it can be possible that because we train AI in the way we want, so it is quite possible that the AI is trained to show that everything is done right, but in reality it is not. So is there something that proves that the model itself, which is checking the whole process or the development cycle itself, is right? It can be that some, let's say, train it to be wrong, but to show it's right.
Yeah, I think we need something like that. Yeah? So you can, if you let the AI create the test scripts, for example, for your software, you have to make sure that the test scripts have indeed been run and not just created and then filled out by the AI, okay, no errors. Yeah? So you have to need the evidence that your test scripts have really been run, that you have measured the coverage and whatever the criteria are for the process, and you cannot just do it by trusting the AI. You have to, it's like if you have human researchers, they have to document the experiments they made, let's say, for example, in medical areas, yeah, they have to store the data of the experiments and so on for future reference. So you can be sure that in fact this has really all empirically measured. And I agree, nowadays typically somebody signs, yeah, and says, okay, I have done these tests. Of course, it's not enough to ask the AI to sign something, yeah, because they will just do it, yeah? Even if they, as Phil just said, yeah? So we cannot trust them. They will always go the easiest possible way, and they find out, okay, I can sign it without actually running the tests. They will do it. So we need somebody, some protocol, which is then done by a non-AI entity, yeah? Some classical software, which really proves that these tests have been run and the result was the desired result.
Okay, we move next. Yeah.
Gordon Egger from Fraunhofer Applied Research Center, Connected Mobility. One comment there is data sets. From my point of view, we need generalized data sets for testing so that respectively the companies test using the same data sets. And those data sets are nowadays based on the measured data and then by virtual realities changed scenarios. So the question is data sets. What is the importance of data set? How can generalized data sets be generated and then applied and used by industry? That's one comment I have or question. And the next is a real question. I mean, we're talking a lot about hybrid models, not forgetting what we know over a system, not forgetting that we could once upon a time solve the differential equation and describe a system. So that we implement hybrid, so knowledge into AI to reduce the amount of data sets is for me clear. And then we can run systems, or how can we run systems based on AI by safeguarding them with hybrid, so with analytical system, with knowledge-based systems.
If I can start, the issue with standardized data sets is the AI will learn the data set. So we're seeing AI programs scoring really well on various lawyer and medical and knowledge tests. And it turns out it's because they found copies of the tests and memorized the answers. So that's the catch. If you're going to test AI, it has to be variable, unpredictable data because it is not testing whether they memorized answers. You're trying to test the generalization from the data they've seen. So you can have standardized models, standardized parametric scenarios, but a literal standardized data set is the worst thing you can do because it'll learn it. In terms of trying to just figure out having comparison with an analytic model. I've done a lot of work. There's an idea called safety envelopes, where you have a traditional system that bounds the behavior of the AI. And that can work really well, but the things that we need AI for the most, like perception and prediction, the reason we need AI is we don't know how to make an analytic model. So creating a safety envelope for the most important AI tasks is difficult because we don't know a second technique. You can do approximate bounds, you can do partial bounds, but that's still a very tough area because we don't know how to make that other system. And putting two machine learning models and voting them runs into the diversity question and the fact they'll always have different answers. So that's a really sticky area. People have looked at it, but it's a really hard area.
Thank you.
Okay. Hi, it's Siavash from Avial in Italy. Well, my question is regarding extending ISO 21448, SOTIF, covering also the use of AI in the process. I mean, we have the SOTIF standard that is supposed to address some insufficiencies in the design of ADAS system for automotive. How do you think if it could be extended to identify insufficiencies during the process and during the use of AI or assisting of the AI when we are going to compile a checklist, for example? How it could say that that intended functionality that is compiling that checklist is trustable, the result is valid. Could it be an idea to use it as a guideline, also to cover what is not going directly in the automotive, but the work behind it? Would it be working?
It's interesting to hear everyone here on the panel on that. From my perspective, and maybe I feel, Marx, I really want to hear what you think, but I think AI is a challenge in general, not only for automotive, right? And I think every industry at the moment trying to understand what does it really mean for us, right? Every industry. There are multiple standards at the moment in development, like 42001. There is another standard for safety tools. There are standards for cybersecurity, how to protect AI, and lots of work happening everywhere. So I think this is a huge opportunity also for all of us to learn from each other, because those checklists, of course, automotive, we more care about safety, right? But every industry wants to get correct answers. Every industry wants to build this trust. Every industry wants to think what is the role of human and what is the role of artificial intelligence in this. So interesting times, I think, for everyone who are working on standards those days.
Yep.
So I would add to it, there's a reason my book is Embodied AI Safety and not Automotive Safety, because everyone else is having these problems. But the scary part is everyone thinks automotive has already solved these problems because robotaxis, and that's really scary.
I have to explain that to my managers about once in a month. Yeah. So why can't we do that? All these robotaxis are already doing it. Why do we still have these old school laser scanners in the factories?
Okay, unfortunately we are out of time, so the last question, but let's try to keep it a bit short. Yes.
Yes, so again, Vincenzo from S-Cube. So I think here, it's a segue to what the colleague just asked. I mean, we see that everybody's basically experimenting with AI and trying to basically introduce AI as part of the safety life cycle. At the same time, we see a vacuum in the standardization. I mean, we see that ISO 262 edition 3 is due published in 2027. And I'm sure there will be no mention about, using LLM as part of the safety life cycle, right? So we see really a vacuum right now, and my impression is that the state of art is moving much faster than the standardization itself, whereas the standardization should basically capture the state of art technology. So yeah, I just wanted to ask your opinion about how to deal with this divergency between the standardization and actual industry practice.
Yeah, and I will also add a third layer: regulations, because even the regulators, by definition, they will earn much less salary than people in the industry, and they will probably invest less and they will know less. So What can regulators do to also enable or block? Okay, try to keep it short, please, but if you want to comment.
I just want to comment on that, and I think this is not new. Has always been the case. And the safety standards are always behind the current state of art of technology, and I think that's a good thing because that means if you are innovative, you can do things which are not in the standard and solve the safety problem in a way which has not been done in such a way. And what is important, of course, is that the safety standards and the regulations, they define the requirements, what has to be done. No? For example, what kind of risk reduction is necessary, but they don't explain or they don't demand how you solve it. Yeah? And this is, I think, something we are doing. Sometimes there's still maybe a little bit too much information on how to solve things, and I think that is something which will then generate progress because you can then use AI to fulfill these requirements in the safety standards and do it maybe in a more clever way, and so finally improve the processes.
I fully agree. And,
No, please go ahead.
Okay, no, just briefly, I fully agree. And one of the ways I decided to act on this, I recently joined ART1, which is UK committee for those standards development across industries, also safety. And I think this is what we should do, right? Because to support this industry as developers, we must contribute and help regulators to set the right processes and standards in place.
So let me provide some UL 4600 experience. So UL 4600 is not a standard for how to make AI safe. It's a standard for how to explain to people that you did make it safe. And that's how we got away from some of the technology dependence, because the safety case technology is much less volatile than machine learning technology. So it's a framework to explain it. So that's one thing we did. But the other thing is Underwriter Laboratories allows yearly updates of standards, unlike ISO. And that's another reason with UL. However, an ironic twist is that the manufacturers have recently said they want the standard to stop changing. So UL 4600 is not currently being changed every year because the manufacturers said to stop changing it. So just because the technology is changing and people complain, oh, the standards are out of date, well, it's not the fault of the standards. The industry doesn't actually want it to change. It's a much more complicated situation than just standards are slow and bulky. That doesn't have to be true. Manufacturers actually want it to be true, it turns out.
Yeah, that is a really key issue. I mean, whenever you're changing the standard, even the ISO 26262 from second to third edition, is a huge effort. An organization like ISO kept saying, you need to follow change management. Do we get a change management from the ISO standard? Or what has been changed? What is the implication? No. Everyone has to do a huge amount of job to understand now what should I change. Okay, many thanks for Helen, Max, and Phil to be on stage. And yeah, thank you. Okay, so we move to the next presentation. Again, we have two presenters. We have Sandra Torchiaro, just easy to pronounce for me, Functional Safety Manager and Technical Lead at AVL, and also more than 15 years experience in functional safety across different areas. So welcome again. And then we have Savash Ashlani, Functional Safety Manager, again AVL, and yeah, also expert in many years, over a decade of experience on functional safety for automotive and also including cybersecurity. Okay, the floor is yours.
Okay, so thank you, and yes, I'm happy to be here today. I mean, it's really, really good to meet all these experts and talk about all this innovative topic. So let's introduce our presentation. I will give an high-level introduction, what is the scope of our work, and high-level description. Then I will leave the word to my colleague Savash. So, as already said, today several times for the automotive industries, the introduction and the increasing of number of autonomous driving function is generating new challenges, new safety challenges, because such a function are relying a lot on complex sensor devoted to perceive the external environment, internal environment, and complex algorithm like fusion algorithm or machine learning, as we said already, that need to interpret this data perceived by this system. And of course, to apply ISO 26262, to be sure to develop such system free from a reasonable risk is not any longer sufficient, because it's just not fault that can cause hazardous behavior due to misbehavior of this function, but we have to think about function insufficiencies and performance insufficiencies caused by this complex, let's say, function, sensor, and algorithm. And this is why the SOTIF safety of intended functionality standards, also the ISO 21448, sorry, is becoming also a crucial standard that is somehow complementary to the ISO 26262 and is guiding during the complete development, as you know, everybody, starting from the specification and the design through the very crucial verification and validation phase until the operation. And in the past years, with my colleagues, we faced the challenge to somehow meet both of the target of ISO 26262 and ISO 21448, and we recognized that it's possible to make synergy between the two. As I said, these are complementary standards, and there are many common points that give us the possibility to synchronize such development. And today, we are going to explain to you how to make synergies between functional safety and SOTIF development. What are the key challenges in integrating these two processes? And additionally, we will try to give you an insight on a use case, so how we applied this integrated methodology in a real case study, let's say. Yeah, here more or less what is the agenda. I will not go longer on this, but as you see, we will focus just to be clear on this phase, let's say, for the functional safety standard concept phase, and for the SOTIF standard more on the design specification, hazard identification, and then measure definition to cover the function insufficient found out. And as already said, there are several points of contact between this phase in the different standards. In particular, here, I mean, we have listed some terminology that is different in the two standards, but at the end of the story, it's pointing to the same topic, like, for example, item definition primary function, and in the functional safety standard, intended functionality into the SOTIF. When we have a functional operational condition in the ISO, in the SOTIF, we talk about ODD, operational design domain, and so on, you can see here. So one of the main points of contact, a similarity in process, for sure, is during the hazard analysis and risk assessment phase, where we can, synchronize and integrate in one work product the identification of the hazard by functional safety with the scope of risk risk estimation, but at the end we can also look and identify the hazard more due to function insufficiencies with some difference because for the ISO 262, as you know, we have to look to severity, exposure, controllability, so we have to estimate, determine the hazard that become the starting point for the complete development. When instead for the SOTIF, we just focus on controllability, severity. Okay, is this a case controllable? No, then this is SOTIF relevant. Is causing an harm? Yes, then it's SOTIF relevant. And in this slide, we try to make, let's say, a visual description of what are the zone of overlapping between the two standards and the two development, and what are the difference. We will show to you the methodology that we have defined. We defined this as a spiral methodology, but it's nothing else that to say, to describe what is the natural SOTIF process way to work in loop to reach a reasonable freedom from risk. I will then hand over the word to my colleague because he will give you more in detail description.
Yeah, thank you, Sandra, for the explanation. So now we come to the challenge of the integration of the SOTIF and functional safety together to see how we have tried to integrate them and in one, let's say, development cycle, achieve the work products of both of them. So from one side, we have the V model of ISO 26262. In the other side, we have the SOTIF that requires some loops and some iterations. What we defined or how we tried to work was a spiral model that there is a V cycle and this V cycle is repeated. Particularly regarding this approach, we start with the item definition in functional safety and the SOTIF design specification in 21448. So we are more in the center of the spiral model. Of course, these work products are not the same, the activity is not the same, the SOTIF could be even more extended, it could have even some kind of countermeasure, safety mechanism inside. In the FUSA we cannot have it, but that is the start point for the first loop. Starting from that one, the HARA is a very good point to have synergy between this safety analysis and activities. We will have a look inside it. Then we have the definition of the safety goals in functional safety and SOTIF acceptance criteria. These are both the target, the high-level targets that must be met in vehicle level. These are the place that they can be jointly defined. And if we look in the spiral, at the beginning in some iterations, we could skip still some work products, still generate something high level and detail them down. For example, as the next activity, we can define the functional safety strategy together with the definition of the insufficiencies in a specification for SOTIF. They meet each other there. When we move further, the FTA approach, qualitative FTA approach to still identify some let's say, faults that could happen in the vehicle level for functional safety, and some insufficiencies from output insufficiencies, performance insufficiencies still in vehicle level, but in SOTIF. Then when we continue, we develop the functional safety concept, and in the other side, we define the improvement measures for the SOTIF. More or less, in the exit, we come to the technical safety concept and the detailed improvement measures, and then it goes for the validation verification. It is not the scope of this presentation at the moment. We said that the HARA is a good point for jointly perform analysis according to both standards. As we see, when we have the malfunction, hazardous event, and it could lead to the harm in ISO 26262 if it not be controllable. In SOTIF, we could have misbehavior, hazard, and the rest. These two are very correlated to each other. We already know that the source of that malfunction in functional safety is fault, but in the SOTIF it is the insufficiencies, and that insufficiency in particular condition together with the integration, the triggering condition, it leads to the misbehavior. In the SOTIF standard, we could have different levels of abstraction. Actually, in all the developments, it could happen. And in the vehicle level, we talk about the hazardous behavior, like unintended steering. Then what would be the cause of that unintended steering? It could be some issues in the sensing, plan, or act, like no detection when we are in the functional view, or incorrect trajectory in the planning, or incorrect actuation when we are thinking about acting in functional view. In the technical view, there could be more detailed insufficiencies, let's say, that perhaps the range of the radar that we are using in the vehicle is not sufficient, or maybe the processing capability of the camera has not been sufficient, or perhaps the torque that it can apply to the steering has not been sufficient. We have different levels of abstractions. How we can analyze the hazard from top level to down level, it is what we, for that one, we define the methodology. Starting from HARA to identify the hazardous behavior, it is more or less clear. We defined an inductive analysis. By that one, we start from the top level and go into the functional level and the technical level and deep inside the vehicle. By help of that one, it's possible to define the measures. And also when we come to the technical level, we can define additional use cases that perhaps they have been those unknown scenarios. But how? Let's have two definitions, two considerations before starting. One is regarding the insufficiencies in the vehicle level. The insufficiencies in vehicle level or in the specification could directly lead to the hazardous event. But when we come to the element level a little down, we could have some idea like what we have the cascading failures in ISO 26262. When insufficiency of one element could lead to the insufficiencies in other element, it could lead to output insufficiencies and so on. Or sometimes we would have different insufficiencies that are combined together and lead to a hazardous event. Like we have multiple point faults in ISO 26262. Let's consider that we have a functional insufficiency in vehicle level. Now we are going to identify what could cause it. The idea is something like a FTA and help of some keywords. That the keywords are many times used in the HARA or in FMEA approach. Now we have tried to use them in this way, that we think about three types of insufficiency. One insufficiency could be lack of input, another one would be incorrect input, and the other one processing that is not sufficient, processing incapability. If we could have these types of insufficiency, it could lead to output insufficiency. The output insufficiency could be input insufficiency for the other layer. In this way, we decompose each insufficiency to three reasons and go down to the system from functional view to technical view and so on. How much can we go down when we come to the trigger condition? In the triggering condition layer, we cannot have incorrect input. What does it mean? The sensor cannot have incorrect input. The sensor perhaps may not be able to process that input, but the input is from the environment and the environment is correct. If we have a sensor that produces wrong output, it is because of its lack of process capability. In that point, perhaps there is a parameter that we have missed also in the input. It means that we have an unknown scenarios, and it is where we define new use cases. So if we come to a level that we say that something is not considered in the bottom level, that is unknown scenario. So at the bottom level, we have the lack of the input and processing incapabilities. Let's have a quick look at the example. If in the high level, we would have incomplete or wrong lane change. What would cause it? Perhaps the vehicle has not been able to identify its position or calculate its position correctly on the lane. And the question again is, what would cause it? What would be the root cause? Do we have considered that in some cases cameras cannot provide the input because they cannot see the lane? Or perhaps the camera could not produce the input. The camera, for any reason, does not produce a valid input. Yeah, if there would be, it's very simple, a snow or some dirt on the lane. Or maybe the driver is using that function somewhere there's no lane, or somewhere that it should not be. The function would be designed for the highway, but the driver is activating it somewhere out of the ODD, and it's a misuse. Have we considered this type of misuses or the, let's say, triggering conditions? This is from one side. Or are we in the cases that the camera could generate wrong output? Yeah, it could happen. I just move quickly because we do not have so much time. Yeah, it could be incorrect output or inaccurate output by the camera. That would be other type of the insufficiency. For that one, we would have, for example, some old lines that are remain on the ground and the camera has detected them wrongly. Or in some cases, we would have a camera that is not able to process very well the environment. There could be also some extreme case that could be tested. So if we would have those wrong lane changes, what could be done? The vehicle in the L2 plus system need to take the control to the driver. And in that case, the driver should be ready to take that control. Is the driver ready to take the control? The DMS functions come here. So we have to guarantee that the driver is ready to take the control. It means that we introduce a new function. If we introduce a new function, then this new function goes to the HARA and it requires to be analyzed in all the system. So we have to revise the HARA in that spiral model. And in order to do it, we should again see all the inputs and outputs of that function. So it's when the spiral model is repeated. Okay, so we would revise the HARA with all the inputs and outputs. We are more or less in 1 minute. And we know that these changes are happening in the SOTIF and in functional safety. In functional safety, when we talk about change management, change, we know that change there is, but it's a kind of exception. We follow the V cycle. If there would be change, we need to go back. But in the SOTIF, we know that the change happens because we identify new functions or because we modify the existing functions. So these changes are systematic, and we should be completely ready and have a good methodology to cover it. What could be done here? We have defined a kind of flowchart to analyze the root cause of the change and the impacts. If we define a new function, we could have, of course, new hazards. Or if we modify a function, the function would be the same, but it would be modified, like when we have the unintended steering, or in the next loop, we have unintended steering in the specification or out of the specification. It is the same hazard with different let's say, with some modifications. In the other side, we would have also the change in the environment, in the scenarios. When we added DMS, in DMS, from one side, we add new functions, but in the other side, we are changing the exposure time for which the driver would be attended or not attended. So it is, again, another route for the impact analysis. We have kind of flowchart and a kind of toolkit that is developed to guide us through the change management. that is foreseeable from the beginning. Okay, I tried to be very quick, and yeah. So we talked about the spiral model as the method to combine SOTIF and FUSA together, the inductive analysis to identify the insufficiencies hierarchically in the system, and the change management that must be foreseen because we have the loops in the system, and it needs to be systematically guided through the development. Okay, yeah, we are. Thank you. Right. So.
Okay, again, questions. And again, do we have someone online? Otherwise, I don't believe it we have people online, except Phil. Okay, one question here.
Hi, Ioannis Sorokos from Fraunhofer IESA. Thanks for the presentation. How do you connect what you presented to a scenario-based decomposition of the ODD, and how do you use this in tandem, or do you use this at all?
Yeah, actually the scenario-based ODD is where, in the HARA, exactly, it's where it meets also the functional safety. There we have the scenarios for both of them, if I completely understand you. And the scenarios are the scenarios that cover both functional safety and SOTIF. If you mean the use case based, eventually, yeah, in that case, we derive the scenarios from the use cases. But in the HARA, exactly, it is where we address the scenarios for both SOTIF and for functional safety. So the scenarios enter into the HARA for us.
Yeah, sorry, I meant more like, do you have a specific management approach for handling the scenario catalogs, for example, or this is something you treat informally, or how is the process?
No, of course we have such, let's call it catalog. Of course, for SOTIF application, you know, I think better than me, the validation of, okay, I covered all the ODD, it's something that you build up during also the validation phase. You have to drive miles to understand if you have considered or not considered all the complete ODD. And of course, this is learning. And yeah, let's call it catalog. You build up and improve this catalog experience by experience, let's say like this. Huh?
And I could add the comment that we also took the advantage of the Pegasus. The Pegasus approach was also good help for us for the scenario analysis. Yeah.
One more question here. Maybe the last.
Hello, thank you for your presentation. I'm Alek Prajapati, also from AVL UK. So good to see your presentation. My question is about integrating the unknown, unsafe scenarios that you identify and taking them back to HARA. So it's about, so when you take the unknown, unsafe scenarios and take them to HARA, so should we reconsider the malfunctions that were identified from ISO, from functional safety? Because you are taking the SOTIF results into HARA. Because it is possible, like you said, a change in function can lead to a change in hazard. So,
yeah, of course.
Yeah,
we look
exactly.
At that.
Here, yeah, if it goes back, yeah, when we have the change in the scenario, we could have also some new scenarios there. And if we would have the new scenario, then we need to take it into account for the new hazardous events.
So you can generate new hazardous events, yes. And then you have to evaluate that hazardous event from both sides, SOTIF and functional safety side, yes.
Yeah. Okay, thank you.
Okay, thank you.
Thanks.
Okay, next presentation is again virtual, online, and we have Espedito Rusciano. Are you online?
Yeah, I'm online. I hope that you can hear me.
Yes, yeah, we can.
I hope that you can also see me now.
Okay, not yet. Okay, now yes.
Okay, great.
Okay, hi, nice to meet you.
Yeah,
So,
nice to meet
Esperito Rusciano is a program manager at the European Commission Joint Research Center. So, yeah, it's nice to have again the European Commission also here with us in the conference. And yeah, I think I'll give you the floors directly so you can jump in your presentation. So, again.
Yeah, thanks. I'm going to share the presentation. I think that I need to share the entire screen because we had some problem, but I hope that will work in any case. Give me just 1 second.
Yep.
I hope that works. You will see the presentation in presentation mode now.
Yeah, not yet here, but yeah, okay. Just wait a second.
Yeah. In the meantime, I want to apologize with all of you that I was not able, to join in person. I hope that in the next edition I will be able also to join in person.
Yep,
I don't know if now works the presentation mode.
Yeah, we
you-
can see. Okay, floor
Okay.
is yours. Thank you.
Okay, thank you. I'm Esperito Luciano and I work for the European Commission for the Joint Research Center. Today, the presentation will mainly focus on the evolution of the regulation of automated driving system and how this will be linked, and is linked with automotive practice like the functional safety, but also the SOTIF. This is basically the intention of such a presentation, and I will explain a little bit more the concept of multi-layers, continuous safety assessment, and the link again with the functional safety practice. Let me start with the agenda. I will start with really a quick introduction about the Joint Research Center, and then we will move to the regulatory framework, the activities that the GRC is supporting at the European level, but also at the United Nations level. And then we will move with some details about the concept of multi-pillar, but I would like to say also multi-layer approach. That is the approach that currently is used for the validation of automated driving system. And then some aspect about the system thinking, the safety case, and the monitoring of the safety performance, that are three main elements for the validation of automated driving system. And then, yes, for sure, there is the Q and A. Let's move, and I will try to be really quick about the GRC. The GRC is part of the European Commission, and we basically provide science, we provide basically research that will support the policy development of the European Commission. We have 11...
sorry to interrupt you.
Yes.
Your voice is very noisy. Could you try to check maybe your mic? Maybe, I don't know.
We'll try
some noise.
Yeah, I don't know why.
Yeah, now it seems better.
Now it's better?
No.
Okay.
No.
I don't know why. It's a pity. Still, you cannot see me. You cannot hear me properly.
Yeah, we can hear you, but yeah, there is some noise on the audio.
Yeah,
okay,
not sure.
let's try.
Okay, I will try to maybe to speak loud, but I still think the problem will remain. Anyway, I was talking about the European Commission and the Joint Research Center.
Hello.
We basically...
Hello. I apologize. Maybe you can use headphones with the microphone.
Okay. Let me try to do this. Don't have it probably here in this moment. Yeah, because I'm in a meeting room. Yeah. Sorry, I cannot use, in this moment, the headphone. It's a bit... Let me try to see whether I can... Yeah. So it's not working now. Yeah, sorry, I cannot use now the headphone. It's a pity, but I'm not... I don't have now the possibility to... still, the sound is really bad.
maybe we can try to quickly connect to the conference through the phone and try the microphone from your phone.
Okay, maybe I can try in this way.
Should we potentially swap the presentations and
Yes, I think that would be...
then
Okay.
while you have tried to fix the problem? So,
Sure.
yeah,
Okay,
sorry,
so-
maybe we swap the presentation while you try to fix the problem.
Okay.
And maybe we go now with the case study from Phil Schleiss.
Okay, sorry.
Here. Is okay?
Okay, perfect. I will try to fix the problem.
Yeah, will be okay also for you to switch
Oh,
to
yeah, no
presentation?
problem. Yeah, okay, perfect.
Okay, so Phil Schleiss is senior safety expert from the Fraunhofer IKS. Okay, great. Thanks a lot. So maybe, yeah, let's go already straight.
Thanks a lot. So today's topic is SOTIF and AI, how these two things fit together. I think we had that a few times today already. So let's jump straight in. So one of what we want to basically do is answer the question, is our system safe enough? And the way SOTIF approaches this is basically telling us that we have to see that the residual risk is smaller than the acceptable risk. But how can this be done? Measuring this sounds difficult, and I would like to discuss with you today why it's actually so tricky to make this statement with a high confidence. If we look historically, why have we not got this problem in ISO 26262? For random hardware faults, 26262 requires us to have hard quantitative measures. But for everything systematic, be it hardware and software, 26262 has got this nice solution by using the ESIL level to have a decouplement of actually determining residual risk versus actually just following, increasing the rigor in the development process and having enough independence in the development process to then indirectly make this claim that the residual risk is smaller than the acceptable risk. But now you would wonder, okay, why does SOTIF now require this hard measurement of facts? And that could be due to the fact that for 26262, we had this assumption we know everything about the system. We know how to define the functionality that it's safe. And when you look at automated driving or even ADAS functions, we can't really make this assumption anymore that we can completely define safe behavior. So we have to look into this. And this main problem is actually, the underlying problem is a lack of knowledge in being able to define safe behavior. We had this before in the previous talk as well. Functional insufficiencies was the keyword there. So let's have a look into this. Where do they come from? So when we talk about automated driving, the first source of uncertainties, lack of knowledge, comes that we're operating in an open environment. We can't detail out every fact of what we're doing, what can occur in the field. Then we use quite sophisticated radar sensors, LiDAR sensors, camera-based with AI sensors. There's noise in there as well. We haven't got a perfect perception of the world. And to deal with these two issues, what can we introduce? AI, because AI shows, at least in the majority of cases, to actually deal very well with these situations, data-driven approach. But we get a new problem into our safety argument, and that is that sometimes the AI just misbehaves and we can't really explain why it's doing that. So on the one hand side, we're pulling in a new technology to help us deal with some uncertainties, but on the other hand, we're getting new uncertainties into the system. So this is a model that's also used similar in 8800, but there's also other classification schemes to uncertainty. So next to that one, you can also think about how much or how can we quantify the level of knowledge we've got in the system. And there's a quite common model that tries to differentiate between aleatoric uncertainty. That means you can actually have a real mathematical, often statistical model of your lack of knowledge. Then there's epistemic uncertainty, where you can maybe name a factor. So for example, you can name if an object that I can't drive over appears in front of me, this will have a certain risk associated with it. And then there's these black swan events, so stuff we've never thought about before, which is sometimes also referred to ontological uncertainty. And the interesting part is, if you've got absolutely no clue that such an event can occur, then it can't be managed in the system itself. Then you basically need help from outside. Whereas as soon as you can name it, you can build mechanisms into the system itself to deal with this uncertainty. This classification scheme will come in handy a bit later, but let's look forward. So what's the big challenge? So this picture shows or symbolizes a perception, or actually the entire decision hierarchy of an automated vehicle, for example. And what you see is there's multiple channels in the system, maybe LiDAR, radar, camera-based. There's processing, which can be classical algorithms or machine learning. Then there's sensor fusion. And at some point, the information gets aggregated more and more until you've reached a piece of information where you can actually make a safety-critical driving decision on it. And for that decision, we basically have to make the statement if the risk stemming from this decision is lower than what is acceptable. And there's multiple techniques as well to determine what acceptable risk means. The major problem there is if we look at the ML models, machine learning models we're using somewhere down in the architecture of the system, if you get a 99.9% accuracy of object detection, the AI engineer will be very happy, top performance. If we're looking at what acceptable risk means on system level, then we're talking about maybe one incident, one injury in billions of operating hours. So that's quite a few comma positions apart, these two. And the only way to basically break down this very strict number onto performance level of MI models is by using all types of redundancy, be it multiple ML models in parallel, be it also using times, sampling multiple times, using different sensing modalities. But to actually be able to multiply these, I would call them failure rates or probabilities of these individual components, we need independence. If they're not independent, we can't reduce this number. And as you notice quickly, okay, having two ML components run in parallel is maybe not the same level of independence as having a radar and a LiDAR-based system running parallel. So there's different levels of independence that we also have to consider in this type of calculation. One solution forward, a bit of a theoretical idea here is to, when you try to measure the performance of a machine learning component, then you could just take the average accuracy over all use cases, but then you run the big danger of that certain specific cases the ML model might be very bad in these cases, but very good in the other ones. So on average, it might have a high accuracy, but there's very problematic cases in there. And one idea actually, Phil Koopman introduced this concept of micro-ODDs, and we tried to spin it a bit further, is to not have one operational design domain, but basically split the operational design domain according to all factors that could systematically influence the performance of an ML model. And this is what this odd-looking cube shows you here. So basically, you've got an n-dimensional space for every factor that could systematically influence the performance of the ML model. And basically, then you've got cubes in this n-dimensional space. And these hypercubes, basically, you would measure the performance of the ML model for each one of these hypercubes individually. That's what these green and black dots shall symbolize here. And then in some of these cubes, you will have very good performance, and in other ones, very poor performance. So for example, if in a camera-based perception, object detection, if you've got very poor lighting conditions, you will also expect the performance of your ML model to be worse than in perfect lighting conditions. This is quite, if we would really manage to get there, then we could have a statistical argument about each one of these cubes individually. But actually being able to make this claim that we've really considered all systematic dimensions is very tricky. And if we look at 8800, for example, they introduced this concept of what they call safety-related safety-related properties. You can also call them kind of secondary metrics. So instead of just measuring the performance or accuracy of the ML component, there's also a lot of other things you can measure: robustness, and quite a few other attributes you've got in there. But 8800 doesn't give you the answer how you should actually, how good these values should be and how you should use them in your safety argumentation. And one way to use them would basically to back up your statistical argument. So by having a certain level of robustness or whatever, we've got a higher trust in that our accuracy measurements we had on the previous slide in this one hypercube is actually trustworthy and actually reflects reality and is a real statistical argument. That you could even spin further. So my colleagues are working on this as well. So you're seeing this measurement of the performance of an ML component isn't a single value, but it's getting more complicated because as soon as you've maybe got uncertainty regarding your data, regarding the model, regarding the environment, that weakens this kind of statistical claim you're going to make. And if you then go up your assurance case and try and, what you basically see at the end is at the top level, you won't have a single value of what the residual risk in the system is, but it will be an expected value with quite a broad distribution that is more to be expected. So what I want to stress here a bit is this idea of not thinking in a single value, but actually there's quite a lot of things we can't perfectly determine. And this would bring us basically to this picture. So what do we see here? On the one hand side, what I just mentioned, the residual risk. The more we improve the system, the more the residual risk moves to the left-hand side. And now the question comes, when is safe enough? And to do that, you also have to look at what acceptable risk actually means. I checked in the program, I think actually the next talk after the lunch break is exactly focusing on these techniques, so there will be all the details there. But there's different techniques to determine acceptable risk. What's maybe important to stress is as well the granularity we look at there. So we had, I think Phil was mentioning that before as well, like if there's certain situations, I think they had the crosswalk with the child example, if the system always fails there, it won't be acceptable. So basically you, for each individual situation, have to say you're better than the reference system, be it the human or whatever, instead of just having an average value over all driving situations and then maybe being better than the human is maybe not sufficient, but actually you need other granularity. Similarly, who's affected? If you actively get into a self-driving car and you know it's risky, you at least implicitly somehow accept that you're prone to a higher risk of injury than a complete involuntary bystander, some pedestrian, that never made any decision to accept self-driving vehicles. So there's also a big discrepancy there. And so we see basically it's not comparing one value against the other value, but this actually, to actually make a statement or a claim with a high confidence that the residual risk is smaller than the acceptable risk, these two areas basically nearly have to be overlap-free. So this has to basically be completely free of overlap or nearly to make this statement with a high level of confidence. And managing this is tricky. And one solution forwards, we had this today as well from ZF, for example, is this idea that we actually have to do some monitoring in the field as well to be safe. And one last model that I would want to introduce here, you can think, at least except for end-to-end based systems maybe, but in a more AI components being in a more component-based approach and composed in the system, you can think in a type of onion model as well. So an AI component, maybe it's not seen certain data during the training. So out of the perspective of the AI component, if this occurs in the field, it's a completely unknown. But the system encompassing it can use multiple techniques, redundancy, out-of-distribution detection, other types of plausibility checks built around it to detect, okay, the output of the ML component is actually incorrect. And so that way, you basically turn an unknown into a manageable known unknown. You can spin this further. So there's maybe other factors that violate assumptions in your assurance case. What happens? In the AI subsystem, you maybe can't manage it, but maybe you can install monitors in the system. For example, you made assumptions about, I don't know, the maximum curvature of a road on a motorway, and at some point you detect there's a stronger curvature than you've ever argued in your safety assurance case. So at that point, if that's a simple monitor that you can implement, that you can also automatically basically generate out of a assurance argument and install in your system. And as soon as this triggers once in the field, you know, aha, okay, this was a case that could invalidate my safety argumentation. And then you know, okay, we have to do something here. And the last and worst case are basically when an accident happens, and only after the fact investigating, okay, an accident happened, what went wrong, how can we prevent this in future? And if we don't find that quickly enough, you have recurring accidents happen. So 737 MAX, I think, being the prime example here in the latest time of the same root cause causing multiple accidents from happening. And the big question is, if you don't just start at the accident level, but you actually start logging smaller incidents earlier in the system, the risk still stays contained. You can push an update to the system early and prevent these reoccurring risks and accidents from happening over and over again. And yeah, the SWOT model, the big question is actually, maybe we'll hear this in the next talk that it should have actually been before this one as well, is what regulations actually require. So what's the minimum here? I mean, you notice the more you log at a lower level, the more expensive it gets. So finding the proper balance here, how much we have to log, this is what's safe. So that's one big challenge of the future. And looking at the time, we will just come to the summary. So what did we see? So basically, main takeaways I would say are residual risk versus acceptable risk are not hard numbers, but they're distributions as well, because there's a lot of uncertainty in trying to actually determine these two numbers. And we see more and more need for monitoring in the field. So SOTIF as well as 8800 have got this continuous loop already in the standard. And at least from hearsay, I've heard that also in the newest 26262 discussions, there's the topic of in-field monitoring also being discussed. So I think the standards reflected, plus some regulations that maybe we will hear of now, I think, on top of this. So, questions?
It's okay? Okay, yes. Question already here, one, yes.
So my name is Hariharan Venkatachalam.
Wait. Try.
Can you hear me?
Yeah.
My name is Hari Venkatachalam. I work for Iveco as head of product safety. So it was quite interesting that you say continuous safety engineering. What are your thoughts on actually making it more subjective, so to say? Because on one side you talk about performance indicators, but in reality, if you think about certain scenarios, say for example, certain drive scenarios, each time your system is going to take a decision based on the scenario that it is in, right? So what are your thoughts on using, say, subjective evaluation of the safety scenarios versus KPIs, which will indicate much more, say, standard values, so to say, in this case?
Yeah. Can you elaborate on the subjective?
So, for example, if there is a reaction, say, for example, you have a blind spot information system, and there is a radar which is detecting something. Under normal circumstances, your performance is okay, but when you drive through certain areas, the performance comes down. So, for example, assuming you want to have an active braking system on top, then your performance goes down in general and does not ensure the safety of the vulnerable road user or the bicyclist in this particular case.
Okay, understand.
So in these kind of scenarios, before we introduce standard measures which could put potentially be just giving you some number which you cannot judge what is the threshold at which you say, yes, it is safe, or no, it is not safe, to coming to starting off with a subjective evaluation, and then after that, probably using that subjective evaluation to determine what would be the threshold that you want to have.
Yeah, I understand. So I think this also matches quite well with this like splitting of the ODD a bit. So for the parts of the ODD that your performance is good enough, you're happy, and for other topics, okay, now maybe there are poor lighting conditions or whatever, maybe you have to build something around it. So you detect, okay, I'm in this part of the ODD, I know the performance is not acceptable, so maybe I deactivate the function completely or I reduce the maximum velocity, topics like that to bring the risk down. And if your in-field evidence shows you then slowly that it could work, then maybe you can slowly increase it. So a bit of this shadow mode idea could be used there as well. So I guess that's like the two key elements to it.
Okay, maybe last question, and then we need to move on.
Hello. I'm Kostas Andriotis from Indec Automation. Working in industrialization, we got used to failure analysis and distribution. So I see that you've talked about getting data and creating a model based on that. I think that is a nice approach, and it's going to come, okay? However, have you considered the latency in applying the model in real-time applications with the extent that the real-time applications gets in time? They're going to be evolving any time. So it's basically like chasing our own tails. What's your comment on that?
Good question. That's, yeah, so this real-time aspect we didn't really consider until now. Yeah. It's a good point.
We do in large time.
Have to think about that.
Okay, let's move. Thank you. So, are we okay now with the next presentation? Going back to the we have which one?
Yeah, if you want, I can present if the sound is fine. Otherwise, we.
So, we try?
Yeah, I mean, I can try to present if the sound is fine. Otherwise.
It looks okay now, yes.
Okay, perfect. So, sorry again.
Okay,
we'll
just give us a few seconds for the presentation. Okay, perfect.
Okay, perfect. And sorry again. I hope that now works fine, the sound.
It's okay.
Okay, perfect. Great. I was providing, information about the GRC, the Joint Research Center. We are part of the European Commission. We basically do research in order to support the policy development of the Commission. And we are divided in different directorates. Each of them is covering different aspects. My directorate is mainly, focusing on energy, climate, and mobility. And we are spread in different areas in Europe, in 5 member states. I'm currently working in Netherlands, in Petten, but most of the team that is working on mobility is based in ISPRA. Let me provide few information about what we do. I was mentioning that we support the policy development of the European Commission, but basically we cover the entire EU policy cycle. We start to do research in order to identify the needs for policy, but then we also support in development and drafting the policy itself, integrating also the different aspects of the policy development. And then we evaluate, this policy and the impact and the effectiveness of such policy. So in few words, we do science for policy. we are independent. It means that basically we receive budget from the Commission, but we are completely independent from private, commercial, and also national interest. We work and we support more than 40 European Commission policy departments. So basically, our purpose is to develop independent evidence-based knowledge that will support the policy. This was just to provide few information about the GRC. Let me start now with the presentation. Small disclaimer, whatever I'm going to present mainly represent, the personal opinion, but cannot be considered as the position of the Commission. I will start with the regulation. I already mentioned that in this presentation, I will provide an overview about the evolution of the regulation, in particular with focus on automated driving system. And this is the starting point of today. We see more and more that there is a different approach for the policy development, for the regulation. In the past, we are mainly having traditional regulation that were compliance or prescriptive, in the sense that basically they were defining pass-fail criteria. But we have seen that this kind of approach is not really working when we move to automation. The regulation for automation and for automated vehicles is taking a different approach. It's mainly performance-based, or what we can call also open regulation. Mainly this kind of approach is based on defining safety goal, performance goal, that will have some benefit in terms of flexibility. They are open to innovation, but at the same time also lead to some challenges. So the ambiguity, the need for having a proper safety assurance, and this is why it's important really to rely on practice like the functional safety, but also the SOTIF. We see more and more a shift from design compliance to performance outcomes. So in general, with this kind of regulation, there are a lot of benefits. For instance, they are open to the innovation because having a requirement that set just the overall safety goal are open to the innovation. They are able to cover different kind of use cases. In general, if we look to automated driving system, we'll cover all possible level of automation, are based on different approach for the validation, what we call the multi-pillar approach. So the use of different validation methodology in order to ensure a more comprehensive validation of the ADS, and also rely on something that was also mentioned in the past in the other presentation, on the monitoring, so the evaluation of the capability and also of the performance and the safety over the life cycle and also during the operation. But there are also some risks from using this kind of approach. They are much open to the interpretation, so require to have proper interpretation. So there is also a bit of lack of experience from the regulator side, but I will see also from the manufacturer to use this kind of approach. And one of the possible risks is also the lack of an harmonized implementation. So different way or different approach can be used to apply and to implement this regulation. And it's also important, this kind of aspect, if we look not from manufacturer, but if we look also from the assessor point of view to ensure harmonization. And the other risk is also, the possibility to have a bit of lack of transparency. The kind of approach for the validation could be maybe slightly different, and the way of information are presented could be slightly different. So I do believe in general that we have the possible mitigation measure for all the risk, and in general we have a positive balance from using this approach. But then, what is now happening? So basically we see that for automated driving system, the regulator will not longer anymore dictate, what should be the right test to do, which kind of test, because this will be also not sufficient to ensure the safety. And also because automating driving system, so automation in general, are strictly dependent on the kind of design and use case, but also on the operational design domain in which the system is supposed to work. So what is going to happen? That there is a new approach to draft regulation. So manufacturer basically, and this is an important aspect, will and need to take care of the entire safety management, need to provide the risk assessment based on the safety goal that will be defined by the regulator, and then will show through argumentation and evidence how these goals are achieved. This is the approach that currently is used for regulation concerning automation, automated driving system. I would like to provide an overview about the status of the activities that currently are under development or were already developed at United Nations level, so worldwide level, but also at European level, where the GRC is strongly involved to support, the Commission. We have started, I would say even before, but in the 2019 to develop guidelines for defining functional requirement for automated vehicle, but also validation method. And this, guidance led to the definition of what is called, multi-pillar approach. I will provide, few information about, this multi-pillar approach, but what we can call also, new assessment test method. So a new way to assess the safety of automated driving system. During the year, we have seen different regulation enacted, entering into force. From the 2020 and 2021, we had the regulation for level 3 system, automating lane keeping system, where the GRC was also strongly involved, and we also produced a performance model that currently is part of the regulation. Then, in the 2022, at European level, the European Commission enacted a regulation for level 4 system, what we can call fully automated system. And then moving to the 2024, we had also now a regulation for DCAS, so level 2 system, driver control assisted system. So basically, we are covering level 2, level 3, and also level 4 system. At the same time, there is also the need, we have seen the need for a global harmonization. And this is why the Commission and other countries are working to have a general legislation that will be worldwide applicable and will cover the automated driving system. Today, I will provide few information about these activities and upcoming regulation that will be finalized by next year. Just a quick overview about what is happening and what is the current status at European level regarding the legislation. At European level, we have currently a framework that basically is covering all the level of automation. It's based on the slide that I presented just before. We have a level 2 system, the DCAS. Just few information about the DCAS. Is basically a system in which the driver is still in the loop, but will allow, a large kind of operation, including, hands-off operation. And then we have the level 3 system that still, can be still approved in Europe. That basically is an automated system, but still require the driver to be available, even if the driver should not be always engaged. And then we have the level 4 system. That is basically fully automated system in which the driver is not present, even though it's important to mention that the current regulation that we have, that's an European regulation, is just limited to few use cases, so hub-to-hub operation, robotaxi, and automated valet parking, and also allow the entrance into the market just to small cities, up to 1,500 vehicles per year. This is the reason why at European level and also at international level, there is a work now at international level that we are doing as a commission, we are supporting as a commission in order to draft a regulation that will be worldwide applicable. There are currently at UN level 2 groups that are working in order to draft a regulation that is called UNR. It means for the countries like Europe in which there is a type approval, but also a regulation that is called GTR for countries where there is the self-certification. An example can be United States. And there are basically two groups. There is one group that is called ADS Informal Working Group that is drafting the safety requirement. And there is another group that is called ADS Workshop that is mainly drafting the procedural aspect. And this regulation will be adopted by the 2026 in June. What does it mean that? And this is why I think it's important to mention this, that basically we have already finalized all and mostly frees all the technical requirements concerning this regulation. And there are two aspects that is important to mention, two main principles that I think is important to mention of this regulation. One is that this regulation is mainly performance-based, so this is mainly linked to what I have presented up to now. And the second is that it's based on the concept of multi-pillar and multi-layer approach and the continuous monitoring. This is where I would like to focus, the last part of the presentation. And you will see that there are countries from all around the world that are participating and also chairing this group. And this is important because we'll support the harmonization of regulation concerning automated driving system. Let me move to the general overview about such regulation, and then we will focus on the multi-pillar part. We have basically four main components in this regulation. The requirements that are targeting the vehicle, what we call ADS requirement. Requirements are also targeting the manufacturer, so mainly concerning what is called the safety management system. I will provide a few information later. And then there is the compliance assessment that will basically provide information about how the compliance to these requirements should be demonstrated for the manufacturer, but also for manufacturer requirement, but also for the ADS requirement. And the last part that will close the loop is that there are requirements also for covering the operation of the system, so for the monitoring aspect. I think it's really important for automated driving system to cover not only, the pre-deployment part, but also the post-deployment. So the monitoring of the safety over the time. Let's now move to the multi-pillar, I would say also multi-layer approach. The first aspect is about, the requirement. I think it's important to clarify that in such kind of regulation, we are covering basically three kinds of requirements. Requirements that are process requirements, and these are mainly related to the organization, to the concept of safety management system that each organization must have. But also requirements that are covering and are defining threshold. In this regulation in general, we use, two main concepts that define in some way the threshold. One is the concept of competent and careful human driver, and the second is the concept of free from unreasonable risk. These are basically two thresholds that need to be fulfilled. How this will be done, then it's a bit, I would say, much more complicated, but it's at least the kind of threshold that we have in this regulation. And then there are also, requirements in terms of measurement, so specific scenario and specific performance that the ADS must fulfill. Another aspect of the requirement is that basically this requirement in some way, because we are defining this threshold in a really general way, this can evolve over the time. So basically, with intention to really achieve what is one of the goals of the Commission, the Vision Zero. The other aspect is the concept of the multi-pillar and also multi-pillar approach. You will see that basically there are different blocks that work and are integrated all together in order to ensure the safety of the automated driving system. We have audit as a pillar, we have the testing, the real world test, the track test, and the simulation as a pillar, and then we have the monitoring. And all together is linked to the concept of scenario, the use of scenario in order to fulfill and to evaluate the capability of the system. Now, how will work in terms of validation? We will start with the safety management system, and I would say this is also linked to the concept of the functional safety of the FUSA. And then we will move into the safety case. Again, there is a strong link with the functional safety part. After that, there is the confirmatory test. Okay, the manufacturer basically will provide, its evaluation of the safety, but then the authority need to do some tests in order to confirm the evidence provided by the manufacturer. At the end, we have basically the in-service monitoring and reporting. So the evaluation of the capability, the safety, and the performance of the system over the time. Quickly, this is basically in much more detail, the different building blocks. We have the safety management system, that is the first block, and the audit of the safety management system that will be linked to the process that are covering the life cycle of the ADS. And then we have the safety case. The safety case basically is targeting the automated driving system, so the vehicle itself, and need to demonstrate the compliance to performance requirement, what we call, DDT requirement, user requirement, but also to the functional safety, to the SOTIF aspect, but also the cyber and the software. And not only that, but should also cover the test environment and the credibility of the test environment, and also aspects like, the generation and the use of scenario for demonstrating the safety. And this is the second main element. And then the last element is the monitoring and reporting. There are two aspects. One is the monitoring of the fleet, of the performance, and then the reporting when something maybe is going, when there is an occurrence. I will provide a bit of detail about what occurrence means in the last slide. But you will see we have three main blocks that will be the main aspect of this regulation. Moving now, and this basically will rely on the concept of safety as a process that I mentioned, that will be basically the safety management system. And then we have aspects like measurement and threshold in the second block. And then with the monitoring and reporting, basically we are covering, all three elements of the safety process, measurement and threshold. Now, let me provide, few information about some concept. The first concept is the safety management system. Why it's important? I think that when we look also to the functional safety standard, you see that there are aspects regarding the management system, because this is, I will say, the precondition to ensure that there is a proper safety culture and there is a systematic approach to demonstrate the safety. That I will say having good process and strategy is the precondition to ensure the safety over the life cycle. And we have seen, and this is also the reason why, this kind of management system was included. If we look also to other sectors, we have seen that there is an evolution of the safety thinking that led to an improvement of the safety. Moving from the technical factor, so just the vehicle or maybe the tools and equipment, moving to the human factor, so interaction between the vehicle and then the human, led already to an improvement, but then moving to organizational factor, also to evaluating the process and possible deficiency to the process, it led to an improvement of the safety. In the current regulation, we envision basically four main elements for the safety management system. The policy that basically set the foundation, also the objective to be achieved, and then the risk management, so how the hazards are identified, how the risk basically are controlled, and then the assurance also to ensure that over the time the safety will be maintained, and then also the promotion, because in this kind of regulation we are not just ensuring the safety is maintained, but we want to also look to the possibility of having a continuous improvement. This is also an important achievement. This is one of the building blocks. Let's move to the second one that I think is even more close to the functional safety aspect. It is the safety case. We do expect the manufacturer to come up with a safety case that will consist of basically three main elements. One is the system description, so what is the system, for what purpose is designed to, and then the safety concept, basically what are the measures that are implemented to ensure the safety. And there we have also provided a way to structure the safety case that through claims, argument, and evidence. Everything will be part of what we call, the safety case. I would expect also the manufacturer to do a proper review, an independent review of this safety case. You will see, and this is why it's important, that this kind of concepts are really related and linked to practice that we use also for functional safety, but also for SOTIF. This is why I think is even more important now the link that the regulation is making with standard practice that are currently used in automotive. Briefly, what we have in the system description, I will try really to be quick. We have the intended use of the ADS, so the description of the operational design domain. But we have also information about, how the system will work. For instance, for instance, the fallback aspect, the transition, what are the user, what are the possible mitigated, risk condition, how the failure and the fault are managed. There are basically all the aspects that will serve to describe the system. And then we move into the safety concept. So how the risks are basically, how the hazards are identified, how the risks are addressed. And also for that, in the regulation, we require, to use bottom, for instance, and top-down approach. We also ask to clarify and to demonstrate how the hazards are also detected during the operation and are addressed. What are basically the kind of safety relevant object that the system should be able to deal with. The difference between the operational design domain and what is called target operational domain or expected condition. So you will see, I will not, explain and provide, information on all the bullet, but I think what is important here to mention is that the approach that we are using is much close to what is currently in the standard. So we will see that the use of standard will be more and more important to fulfill and to demonstrate the compliance with these regulations that are performance-based. The last point I think is important to mention in my presentation is the third building block, that is in-service monitoring and reporting. So we want also the confirmation of the safety over the life cycle. And if something, new is discovered, this should be also, shared with the authority, but also with the entire community, with the idea that the safety and the overall safety can improve. Basically, there are two aspects of this in-service monitoring reporting. The monitoring, so is the overall data collection that a manufacturer will do, but also the reporting. So when there is an occurrence, when there is what we call a safety relevant event, this should be reported in different way. Critical occurrences that are the ones in which there are accidents in general with fatality or with injuries, or where there is a sample of airbag deployment, that should be reported immediately. But then we have also other kind of occurrence that we call significant occurrence with less severity, but still important to be reported. And then other occurrences that are still important will be mainly reported in a sort of periodic way, in aggregated way. But this is important really to improve the safety of the entire, we'll say, ADS community. Just to finish, what you see that the approach that we are using is really an approach that is trying to close the loop. We have started with the safety management system, covering the organization, the process of the organization, that will help, to ensure the safety over the life cycle. So basically from the concept till the commissioning. And then we have the safety case that maybe mainly will cover the pre-deployment part, so the entrance into the market, and then we have the ISMR part that is covering the post-deployment, so the operational part till the end of the service. Just to conclude, just some takeaway from my side. You will see that there is a shift of the regulation from prescriptive approach to more performance approach. This will be based on the multi-pillar approach, and you will see that the risk assessment will be the key main element that in the approach that the regulators and the regulation is taken will be based on three main elements. Safety management system that will create the safety foundation, the safety case for the risk management and the risk assessment, and then with service monitoring for the continuous assurance. I will say that with this kind of approach, interpretation will be fundamental, and the use and the link with the standard will be critical, and functional safety, as well as SOTIF practice, will become crucial for the compliance to the ADS regulation, and in general, I will say to ensure the safety. With that, I have concluded, and thanks so much. I'm open to any question. Thanks.
Thank you. Okay, so we are out of time, but maybe one question we have here. Okay, maybe two questions. Okay, and we can skip lunch.
I have two questions, very brief. I don't know if the answers will be also brief. Okay. No, so the first very brief, my name is Cristiano Novello and I am with Cadence Design Systems. So the first question is, in your AVS legislation slide with the time scale, there was presented an L4 regulation that happened before the L2 regulation. That's, for me, a little bit counterintuitive. Maybe you want to explain. You gave a couple of ideas. I don't know if they explained that. And secondly, similar to what is done, for instance, in the medical industry. Do we have a database, or are you thinking about having a public database of this field returns, field intelligence returns from the system? Because the general ideas are fine, but then we need to go to the evidence. Thank you very much.
Yeah, thanks so much for the question. I will try to be quick due to the time, but I will be happy, to further, elaborate if is needed. Concerning to the first question, yeah, you are right. First of all, from my slide, you have seen that the regulation for level 4 is a regulation that is just applicable in Europe. It's an European regulation. Doesn't mean, anything, but at European level, based on the initial information available, the intention was to start covering and providing a regulation that was allowing the manufacturer to approve systems that were fully automated. In the meantime, we have seen from the market, from the industry, that it was needed, to cover and to some aspect related to level 2 system that were not yet, in the regulation. We have seen, that the market was asking for having, basically this kind of regulation for level 2. This is why at UN level, then in a later stage started a work, to cover basically driver control assisted system. We already had, some regulation covering level 2, but not what we can call level 2 plus. And I think it was important because it was covering also, some aspect really important concerning the safety, related mainly the interaction between the human and the machine. That is a topic that is really, really relevant. And I think with the DCAS regulation, we are now approaching and addressing in the proper way. Now, moving to the second question about the database. This is really a great question. I think we are discussing about the database since the 2019, and you have seen you have mentioned the medical sector. Actually, I come from the aviation sector, where there is also, this repository. There is a system that is called, a CAR system that basically will collect all the information concerning the occurrence. I will say that now there is some discussion, and it's possible that a working group will start soon in order to create and develop a worldwide repository system that will collect all the information coming from the in-service. I do see that is needed really to fulfill the in-service monitoring and reporting, objective, because one of the objectives of the in-service monitoring is really to share what happened to the entire community and learn from what happened. And we can do that, by creating a repository system. It's not there yet, but we see that there is, the intention at European, but also at worldwide level, to come up with something. I don't want to call database, but a repository system to share information and to learn from what happened. I hope that this answers to your question.
It does. Okay, last question.
First of all, congrats for your presentation. And I am Francesco De Rosa from Art Germany. I have a question. I understood in the last slide that you have in plan to create some harmonized standard to cover the regulation. If it's correct, my interpretation, are new harmonized standard, or you have in plan to use the current functional safety standard that shall be harmonized?
Yeah, thanks for this question. Maybe I will be a little bit more precise. This regulation I mentioned is performance-based, is an open regulation. So it will be complemented by an interpretation document that will provide information about how the compliance to the regulation can be achieved, what we call acceptable means of compliance. And this will be not binding, but will support an harmonized approach to the implementation of the regulation. What I was trying to say is that we are not thinking to develop new standard. We would like, and that is at least my personal point of view, we'll rely on the current standard to explain that the use of some standard can be a good way to show the compliance to the requirement. Okay, this is basically the intention. It's not, and this is not what we do, because we will work on the developing regulation and not standard. But I really think that the use of the standard will be an important, way, and we need to make a clear link, regulation and standard, to ensure the compliance to this new regulation. Thanks.
Thanks. Okay. Okay, so thank you again for your presentation.
Yeah, thanks. And enjoy the rest of the conference. Bye.
Next time in person, hopefully. Okay, so we go now for lunch. Please be back here by 2:19 so we can start on time. And we have, yes, we have the lunch, and then you got some network as well, but you have enough time. Thank you.
So then I have to finish. Nein. Aber gut, wenn du welche hast. Aber da wäre ich überrascht, wenn du welche hast. Mein Gott. Boah. Kann das nicht auskalten. Mein Gott. Classical Martin.
Okay. Okay, welcome back. Hopefully you had a good lunch. That, by the way, was sponsored by this company, SGS Turf.
Ja.
So many thanks for being the sponsor. And okay, let's restart. I know it's difficult after lunch. Hopefully you had a good coffee. Okay, next presentation is from Alexander Grimm. He's from SGS Turf Zar. And yeah, he's been changing across different companies. He's been in Continental, in Vitesco, and now at SGS Turf. So, well, I'll give you the floor. Thank you.
Thank you for the introduction. Hello also from my side. Welcome to today's conference. Today I want to talk with you about how to define safe enough and deriving acceptance criteria according to SOTIF. A few words to SGS TÜV Saar first, and the office where I'm working at is a global competence center. The headquarters are located in Munich. We have more than 90 experts on the planet, and we offer several services like assessments, audits, training, and so on. So before we jump right into the presentation, I also want to make a disclaimer that when I talk about safe enough, it's safe enough to comply with the standard. This doesn't mean that it is safe enough for your company in a way that the acceptance criterion will lead maybe to a specific accident rate according to a specific method mentioned in the standard. This can comply to the standard, but maybe this accident rate can still be too expensive for your company and it's still be not acceptable. I can only relate to the example of the 40,000 accidents and you lower them by 20,000 and each of those 20,000 is a kid. So and even if you have applied such methods, this doesn't mean that it's maybe safe enough for your company. So it's all related to ISO 21448 and the methods from that. The example which I will show is based on limited data sources, and it's highly recommended from us to use a lot of more information on your developments, and you always have to provide a clear rationale for your data selection, why you choose a specific data set for your development. Please keep this in mind when we go on and head to the example. So, a few words to the agenda of today. We will start with a short introduction about three of the methods which are promoted by the standard, the MEM, the GAME, and the ALAP. Then we will head to the topic what accident data can teach us about SOTIF. Not everything is maybe relevant for your development based on the accident data you want to take into account. And from domain to decision, deriving then an acceptance criterion across an ODD on a specific example, and then we will close the presentation with a short summary. Okay, so let's start with the methods, which are some of the methods which are defined in the standards 21448. And I would start with the one, and I have to do an additional clarification that we in SGS TÜV, we think that game is widely used similar to MEM as we think it should be applied. So maybe you will identify some similarities to our approach, which you would consider as the game or GAMAP method. And for us, when it comes up to the interpretation of the standards, humans are no technical systems, which lead to our interpretation that if you compare the current accident data for deriving your acceptance criterion, then it's more related to MEM than it is to game. And the MEM method fits, the applied MEM method within the ODD aligns way better with the description within the standard of the EN 50/126 part 2. And now let's go on and start with the first method, which is described in the standard, which is the ALARP method, as low as reasonable practicable. This is a method which by its name itself mentions that it's highly related to the company resources. That means that the more resources you have, the more testing you have to do is practical for your company. Lower resources would then mean that you have a weaker acceptance criterion because a weaker checkup for your acceptance criterion. And it does not ensure low risk of harm, let's say sufficiently in our point of view, because in brief, this kind of method saves money and not lives and is not recommended at all from us to be applied to set up the state-of-the-art development. Let's continue with the game method. I'm hesitating to pronounce it because it's a French expression, this abbreviation, so I let's say, prefer not to say it in French because my French is really bad. The game method itself is set up in a way that it compares your current development with a similar or with a previous system in the field. And the most available current accident data does not reflect the ADS functionalities. Keep this in mind. So here we are comparing systems, and we do not have enough data available currently to compare different ADS or assisting systems in the field. This method is therefore identifying hazards and define requirements systematically and shows which parts need to be improved according to the Sense Plan Act model, because as soon as you compare two different systems items, then you can use the accident data in the sense that you can allocate the reason for your accidents to Sense Plan and Act. But based on the issue that this kind of method needs data which reflects system behavior, your product behavior, the current available accident data maybe does not show this kind of information. So therefore, we recommend from SGS TÜV this method when you have comparable data from the field. Currently, we see also from our customers that they have already assisting systems in the field which have not implemented SOTIF yet, but they already gathering measurement data from the field. So by time the situation comes from the OEMs that they get more and more information from their already existing systems in the field, which makes it reasonable to use this method and to use the opportunity to allocate the reason for the accidents, for the issues to Sense Plan Act model, so you can clearly identify which part of your products need an improvement and which not. Then let's get on to the method we think is currently the most reasonable which can be applied currently. This is the MEM method. This is the minimal endogenous mortality method, which is based on the overall fatality rate on Earth for us persons, which is specified as 2 × 10⁻⁻⁴ fatalities per person and year. And yeah, the ODD mortality harm rate, if the ODD mortality and harm rate is stable, the overall mortality rate will also stay stable, and this leads to the interpretation of us that you can use the current accident data which can be gathered in the field to derive an acceptance criteria, to derive an incident rate, accident rate, which is currently reasonable, representing what is already accepted by society, because the current accident date which is ongoing on this planet is more or less the one which is already accepted by society. And this means that the ODD mortality harm rate will be your acceptance criteria you may apply for your development. The method itself also adds the information that injury rate or with major injuries or minor injuries can be used and calculated in a way that they can represent the fatality rate. So even if you have different data available about fatal accidents, about major injury accidents, then you can use all those numbers and take into account to derive your final acceptance criterion for your product development. The minimal endogenous mortality method also has some disadvantages, which may already have been discussed today a little bit, that, mentioned a little bit that the generic data may include non-applicable cases like abuse and drugs. That means that the current accident rate would not reflect what really is caused by behavior from the humans, by misbehavior or something. It can also reflect abuse, which are cases you may not want to consider, because if you consider the accidents from abuse as well as drugs and others, then you may have an accident rate set as acceptable, which is way too high. Keep this in mind. What is also not reflected in the MEM method defined in the EN standard is that the near crashes and incidents are not reflected, and we highly recommend to also track them to make your products better, because when we talk about level 2 or 3 systems, the human driver is still in charge to take over, and then controllability comes into account that specific cases may not lead to an accident but would be critical for another driver. So this is not included in the standards, but we highly recommend also to keep track on such numbers and also set up the limits for near crashes, for incidents which you want to encounter, or it's you set as acceptable to encounter for your products. The advantages, as some of them already mentioned, is that you can use generic data with limited information, and you can combine and analyze multiple data sets to derive your final acceptance criteria on vehicle level. So when we talk about acceptance criteria, I also talk about accident rates on vehicle level, which are not really related to your developments, because we do not have too many people from OEMs here. But yeah, for OEMs, this would be the starting point, let's say, for SOTIF acceptance criteria. And clearly mentioned within the standard of the EN, this method is technology independent. And if you apply it, you are still compliant to the standard itself. And this is from us the recommendation to start from if you do not have comparable data for the game method available. As mentioned, it's still widely applied, let's say the current methods which are widely applied in the field are representing this method and mostly called game. Based on the definitions in the EN standard, we make the interpretation that it fits way more to the MEM definition than to the game definition. But in the end, we have to come up to a conclusion in which your method is, let's say, reflected in the standard. Let's talk a little bit about crashes themselves and what they can teach us about SOTIF. It is about applicability of accident data themselves, and therefore I set up a very highly simplified example. Let's talk about an emergency braking system with an ODD of the German highway, so it should operate only on the highway, and by definition of the functionality, only frontal and rear end crashes can occur, here shown by this graphics. And this can lead to the case that the sideway crashes which occurred on the streets are maybe not relevant for you. So this can lead to a more specific and reasonable data source you have maybe taken into account to derive your acceptance criteria for your product. Keep this in mind that the accident data itself tells you a lot if it is relevant for your product or not, based on what kind of accidents are relevant even for your product. Not all ODD, as mentioned, not all ODD accidents can be linked to the target function. Cause and type are key to meeting the SOTIF acceptance criteria, and the more knowledge you have will lead maybe to a stricter acceptance criteria, but also will lead to reduced testing, because you do not have to consider these cases by your validation strategy. So it's kind of a balance which you have to think about in your development, what is more beneficial for you. But from our current point of view and experience in the field, the more you know, even the cheaper it gets, even when your acceptance criteria is quite strict based on this kind of sorting process. Let's go on then to the example itself. Again, a simplified example about an AEB, German highway, and the goal is the system shall keep the number of fatal crashes below the level of human driver. So now we take into account the current accident rate. So here we do some data analysis. German highway, there were 2023, there were 302 fatal crashes. There were 4,316 heavily injured crashes and 25,935 lightly injured cases in which the people, let's say, which people were lightly injured. So those can be calculated into the representing fatal crashes, which will lead to 431 fatal crashes for the heavily injured cases and 259 fatal crashes for the lightly injured people. I took this data from the statistics from the official governmental Office of Statistics, and 2023 there were 248 billion kilometers driven on highway, which I took from ADAC, which is a community in Germany, which gathers also data, provides and other services. And based on this example, I would like now to go on with you and derive the possible acceptance criteria. So now we add up first the fatal crashes and divide it by the driven distance. We get the crashes per kilometer, or if we put it the other way around, then we have one fatal crash every 0.25 times 10 to the power of 9 kilometers, which is already quite a strict acceptance criterion on vehicle level 2 proof for your product. So this would be then, based on the MEM method, a good starting point. And again, a reminder, the data I took here does maybe not represent a sufficient database for the real development. So this should just only show you the method, which is more or less defined according to the standards. And So when we go on to the data analysis itself, then specific topics can also be taken into account, which would lead to a stricter criteria. You may have to be better than human for your final product. As this was already mentioned in the AI presentation before, that if there are still 20,000 crashes, fatal crashes based on a very simple reason, then this is maybe not accepted by society. And if you take cases like the Tesla accident with the white truck, it got quite heavily written in the media. Tesla was torn apart, even if the driver was using his or her cell phone and playing around and didn't take attention, even if she or he was, let's say, was supervised to do that. But still, Tesla lost a lot of credibility by this case, even if they were not even, it was not their fault. So take these topics into account, that you may want to even be better than the current accident rate, which you may have data for. And the applicable crash type, as already mentioned, is a crucial topic, that only applicable crash types are counting up for your acceptance criteria, and this will lead to also a more stricter acceptance criteria. What would weaken the acceptance criteria are topics like exposure rate of critical scenarios themselves. They will talk about probability. How probable is it to encounter specific scenarios in which the hazardous behavior could lead to a hazardous event? And when we talk about, let's say, lower automation, then we talk about controllability of hazardous, then we can lower the acceptance criteria. So wrapping it up, from our point of view, from SGS to SAR, we say start with MEM, continue with GAME, because as soon as you have a product in the field, then use the data from that. And the more detailed data you use, the more accurate the acceptance criteria gets. More detailed data is easy identification of ODD relevance of the specific cases. And you always need extensive data for a real project. And that was it from my point of view. Thank you for your attention. I hope you learned something maybe new. It's not that high sophisticated stuff, but it's necessary to comply with the standard. And I'm open for the discussion and questions.
Thank you. Okay, already one question here. Good. And then again online, if we have someone.
Can you hear me?
Yes.
My name is Hari Venkatachalam from Iveco. I had a question regarding the crash rate calculation that you showed.
Mm-hmm.
So do you actually consider it based on the vehicle type, or is it the overall number of fatal crashes? Because here you were considering a passenger car segment. So
there was everything taken into account, and here we also recommend take into account what is related to your product and to your target vehicle. So depending on the target vehicle, maybe the crashes can maybe change, and even the data changes. This needs to be taken into account. So this is just, as mentioned, a very simplified example to show the method.
Okay, understood. But when it comes to, say, trucks or, say, buses, etc., is there a sufficient amount of data that is available which can be trusted?
Hard to tell. We haven't started any studies on this yet, especially when it comes up to trucks and buses. I know it only from our customers regarding normal passenger vehicles. So mostly they use the governmental-driven studies and data sets. Because they have the highest reliability and there's the highest trust in such data. This is what I can tell you, but overall, let's say all the fields as well as homologation are still gathering themselves up and try to come up with a harmonized solution. But for now, I cannot provide one.
Okay, thanks.
Okay.
Thank you. Hi, thanks for the talk. Ioannis Sorokos from Fraunhofer IESE here. Did you talk about positive risk balance and I missed it, or was this?
No, it was excluded here.
Okay.
Yeah. I'd say the most common ones I included here. I wanted to make it simple, also about time reasons. But we also do not recommend the positive risk balance. The current situation is that be as good as a human is one of the best approaches, because you have the most reliable data maybe available, and then you go on with similar topics, similar systems and items. Yeah. So you haven't missed it. It was left out on purpose. So yeah, and we do not recommend it either.
Hi, Alek Prajapati here. In one of your slides, you mentioned one fatal crash is equal to 10 major and then 100 minor. Is there a base for that, or how that conversion has happened, and is that a standard conversion?
This is mentioned in the standard of EN 50126 part 2. And if you do this, you are still compliant to the standard. This doesn't mean that it is maybe a reasonable approach according to societal acceptance, but this is mentioned in the standard and therefore also set as a compliant method regarding the standards of 21448. And I also want to mention that if you apply such methods, always think about, is this reasonable? When it comes up to the differences between SOTIF and FUSA, in FUSA there was a lot of trust, and there is a lot of trust into the values. In SOTIF, the values are not specified for some kind of a like a fit rate or something like this. You have to derive it on available data and on the technology and so on, and you have to come up with a strategy with a reasonable value. So this is an approach which is mentioned in the standard and seen as compliant, but it doesn't mean that you are safe enough in compliance cases, I would say. Because if we go on, let's take the value here. First of all, when it comes up to SOTIF and AI development, you have to accept that accidents will happen. But you have to come up to a conclusion in which the accident rate is low enough and reasonable for society as well as your own company, because each reliable case will cost a lot of money. So in the end, you still have to think about the rationale why you justify selecting a specific number, and if this is also okay for your company. For FUSA, everyone was cool with it, and there was a lot of trust. And now, in my point of view, the companies themselves have to rethink about this topic of SOTIF and think what can they accept. Because something will happen at some point, especially when we talk about huge manufacturers like VW. Then they have such a big fleet in the field, then these numbers are totally reasonable and reachable for them. So yeah, this is what I also want to tell you here, that when it comes up to acceptance criterion, you also have to ask your boss, okay, we are compliant to the standard, but is the company accepting it? You as an engineer, you are safe. You can tell compliant to a standard, so it's in the reliability of the company now. And the company has to decide if this is okay for them or not.
So when companies rely on this data and later on have more stringent levels of their internal data, does that feedback go to the standard to increase the bar? Because this is like just 1 in 1,700 cars. That's very low for like.
Sorry, I didn't get your question. Maybe acoustically, what did you mean?
So you give an example of VW, right? So VW will achieve this fairly easy to be compliant.
Yeah.
But if they want to be more stringent at their company level, does this data from OEM go back to the standard to increase the bar?
So you mean that if an OEM goes more strict, then maybe these numbers will then be used in a later standard? First of all, the standard itself doesn't use any specific numbers yet. That means that if you come up with your own, you just say you are better than the data you have available. That doesn't mean that you are better than the standard. So in this case, I would not even recommend to do so. But at some point, in the field, some kind of values will be established just based on experience. And therefore, we also have this kind of monitoring loops in place in the SOTIF standard, as well as in the AI standard, that those monitoring loops will lead to a better product, which will be in the end, at some point, safe enough for the society, as well as for the standards.
Okay, unfortunately, we need to move on. So, again, many thanks. Okay, next presentation from Dr. Christopher Temple. Is a lead safety and reliability system architect at ARM. But before ARM, he's been busy with Freescale, Infineon, Intel, and he's also one of the active members from the GEMA committee of the ISO working group for 26262. So he was also 2 weeks ago in Prague. So if you have any good or bad comments about the ISO standard, please.
Yeah, thanks for the introduction. When you come to a conference and you want to learn something, then you think about how does learning work? In particular, if it's passive learning, and there are two options. Either you listen to someone intelligent sharing smart things, that's where Phil Koopman and others stepped in, or you watch someone saying something stupid, and then you think, actually, I can do that better, and that's probably the role that I'm filling now. My background in safety is actually quite long. It goes all the way back to 1995. I came from control theory and electric motor control, and our safety desire was simply to survive our own work on the electric machines because they were fairly big machines and they were powerful and scary. And then I somehow fell into a project called X-by-Wire. We mentioned it this morning, and you can see how far it dates back. That's actually me with more hair. We built this by-wire system. We were very proud of it. There was one curious thing, and that was the first lesson I learned. We want to show a variable end stop. So the actuator, you can't see it, it's to the left, but you can believe me, it was developed by Bosch at the time, it was this size. For the variable end stop, that when you turn the steering wheel, you really felt a real end stop, the electric actuator behind the steering wheel is this size. The product safety person from Daimler, who at the time was one of the project partners, had a heart attack when he saw it, and we put cucumbers into the spokes of the steering wheel. It was really dangerous. So in the end, the bigger safety concept probably went into securing the actuator of the feedback steering than into actual by-wire system, and you can see some of the boxes down there. Then life progressed, and I had the fortune to be part of a Daimler project that actually built a real car with full by-wire steering and accelerator, everything. That's just the trunk of the car, and the front of the car has about the same amount of electronics in it. It was the famous junk in the trunk type approach. And we learned the second thing, which is there needs to be a business case, right? Just developing the technical solution is one thing, but actually putting a business case behind it that you become that it's a viable product is the other. The title, I have to admit, is not quite for me. In 1996, I was at a conference and a meeting in Lars in Toulouse with Jean-Claude Labrie, some of you might still know him, and David Powell. And David Powell was sort of the guy who raised the question at one point and said, if we have $1 to invest, where would we put it? Because otherwise safety tends to be endless. You can always come up with more ideas of making it safer, but how does one put the dollar into the system to ensure that it's actually effective? And now in light of ISO, there's sort of two dimensions that I see in which one can spend money. One can spend money in safety integrity. One can spend money in adding more safety-related behavior. And the trick is to do both. Thanks to the ISO standard, I think a lot of focus and effort goes into thinking about safety integrity. And safety experts are typically people who know the standard forward and backwards. I always feel safety expert is someone who actually understands the function they are trying to secure, because if you don't understand the failure modes of what you're looking at, how do you want to mitigate the malfunction, right, if the function isn't known? And with that kind of mindset, before in the early days, we were largely focusing on how do we put safety mitigation into the system. We always thought at the time safety integrity was more of an afterthought, right? Then when in 2010 we certified the first switch lock processor at Intel with an assessor, and I sort of coming from academia, I had a different approach marketing people always told me, show him the nice stuff, but I thought that didn't make sense, so we showed him the ugly stuff. And after 1 year, he said, please stop showing me ugly stuff. So we obtained a certificate, and that was quite nice. So when the way I think of safety, it's all super trivial, and I apologize for that. It's sort of, I just see a control system, right? That's my background from control theory, and there's some kind of a monitor, whether it's a very detailed, an ECC type system, or whether it's a more complex, larger control loop. You typically find this kind of a building block, and I've created some artwork on next slides, and I kind of just use this abbreviation to symbolize this kind of a building block, right? And then there is a safety fault tree, and clearly the idea is to prevent the critical faults from propagating to the top event of the fault tree, right? The curious thing is that if you look in particular in semiconductors, the faults that we're really concerned about have a very peculiar nature, because they have to be benign enough, good enough, that the whole processor architecture still continues to work and doesn't kind of stop and stall, but they have to be malign enough that they actually do something dangerous. And that is actually, if you try to do it intentionally, not always that easy to create this kind of a fault scenario in the system. So what I see and have seen in the past is sort of originally when we started, we had control functions, and then we tried to put monitors around the control functions, and those were fairly high-level monitors. And then as the business progressed and the semiconductor industry got involved, these monitors got smaller and smaller, right? So first it was just system level stuff, and then there was going in towards lockstep and ECC and hardening each part of the processor individually against malfunction. And you can see from this famous systematic capability, I don't like it from the ISO standard, that's why I put it under quotation marks of this we follow the process, and therefore we have avoided systematic faults. You will see in the next slide why I'm a little dubious about that. But you can see the hardware metrics. Definitely, if you have just these huge loops, they become harder to demonstrate and to argue, so having the smaller loops makes more sense. And also, if there are smaller loops, then it's often easier to locate where was the fault and try to mitigate it, like in the case of ECC, rather than just having a big loop and then saying there's one error indication and all you know is the system failed. When we started on the X-by-Wire project, we largely were following this kind of a philosophy, and some of the OEMs then got a little upset, and then later on in the Spark project we were far more diversified and localized in our ability to detect errors. Why don't I kind of like the systematic capability? Because there is one type of fault that I have found in the past to qualify under this category of being good enough that the system continues, but bad enough that it does something dangerous, and those are interaction faults. The ISO standard today doesn't quite address them explicitly enough to my liking, and in the meeting in Prague just 2 weeks ago, there were discussions coming from the software guys who were having the same kind of concerns and saying, we need to think about these faults that emerge when you combine things that by themselves are okay, but then you put everything together, everything by itself is okay, and suddenly strange behavior appears, right? Race conditions are a typical example, priority inversion examples. The software world has a lot of these, but they also exist in the hardware world. When you look at highly complex processors, 32 cores, parallel, weak memory ordering, there are strange effects that occur. Partially the system actually is fault-free. It's just that the person who programmed it never anticipated that it would behave like that, because the behavior is quite unusual, unexpected, right? So we get people coming saying you have a bug and a problem. We look at it, we say actually not. The bug was the understanding of the person trying to program it. And here you can see now, you can see the bigger brackets are actually better because they cover the the interaction folds here, while if you have smaller brackets and you just partition your system down to very, very small entities and then combine them, then you have all these interfaces between them, and the question is what happens if something goes wrong at the interface? How do you capture it? So the solution is quite obvious. We do combine it, right? We say, okay, let's have a lower level safety concept and a higher level safety concept, and that is actually technically great until we start thinking of the $1 problem, and we say, now it's getting terribly expensive. And I had this kind of awakening about 10 years ago. We were looking at early ideas for autonomous driving, and you know, people came along and said, okay, we have a system that calculates the driving trajectory, and then we have one that checks that the driving trajectory actually is okay, and if they disagree, we have a third system that creates and generates an evacuation trajectory to take us into a safe state. And then someone switched on the ASIL alphabet sprinkler and said, let's put ASIL D everywhere, because that seems to be on the safer side. And then people said, ASIL D, it's lockstep. So we start saying, okay, we have a driving system, an observer, we lockstep each one of them, we have an evacuation trajectory, and at the end you start seeing that 15% of the energy and the money is actually going into moving the car, and 85% is going into all this additional redundancy. And then the question is, does that additional redundancy buy that much benefit? Because it's equally possible that you can say, okay, this mechanism here actually isn't that important. It is covered very well by the overarching mechanism, and you start getting a picture that looks more like something the tooth fairy would enjoy, because you start pulling mechanisms out and saying, can we still achieve it? I had one experience where we did that. We were fortunate enough, and that was in 2007. We developed a fault-graded self-test. In fact, it's one that I have in my car today, and I drive around with my own thing, which is quite fun. What we did was we developed the self-test, we fault-graded it. It was a huge pain. It was a total of a 3-year exercise. We were very early in the development curve, talking of functional safety and diagnostic coverages. And eventually we came up with a self-test. It was integrated, and afterwards we said, like a heap of Mikado sticks, how many sticks can we pull out of the heap before the diagnostic coverage really starts suffering? And from the self-test we had developed and integrated to the one that was kind of optimized to the minimum number of self-tests, we were able to actually extract 70% of the tests, so 30% carried 98% of the diagnostic weight, and the others just helped on like an E saturation curve. They only helped the very far end of the E curve, and you could actually take them out and be far more efficient. The problem was it was very painful and engineering intensive work, and it was all handcrafted, right? And by the way, there was another anecdote on this trade-off question. You'll see. So after we had finished with the software self-test and everyone was exhausted and happy that we had concluded, the hardware people came and said, look, we can do this much faster with BIST. And they did. They achieved it a much faster self-test. But then I still remember the BIST design engineer came to my desk and said, we have a huge problem. The power consumption during the BIST phase is astronomical. We need wires this thick flowing into the CPU, because during normal operation, we never exercise so many gates simultaneously as we do during self-test. So in order to get the power budget during self-test into a reasonable bracket, we actually had to slow down and stretch the self-test duration. And that was another lesson I learned. There's always this trade-off, right? If someone shows you a safety solution, the best question to ask is, where's the price I pay? You can always ask that question, because there's always a price to pay, and then if the person did his homework, he can tell you, and if he says he doesn't know, then you say, go and find the price, because there is one to pay. So what I tried to do was just, if this is helpful for someone, I created sort of a first simple cost model, right? It's simple, you can be far more complex, but I said I distinguished the cost in development cost and deployment cost. What do we invest before production to build the system, and then what do we pay per instance to run the system? And unfortunately, there are all kinds of couplings here, right? again, a practical story. When we did the first lockstep process, we didn't have that much time. It was unclear whether it will be a success, whether the market will need it. We went off to a field application engineer. We said, how difficult is it to understand the interrupt control system? The guy said, forget it, nobody understands it. So we said, okay, simple solution, we lockstep it. We duplicated lockstep it. Then we went to someone else, we said, DMA, we lockstep it, right? So at the end, our safety analysis, FMEDA, had about 15,000 entries, and we had resorted to lockstepping. We were fast, but it wasn't particularly power efficient, and everyone was screaming and saying, you're wasting so much die area, can't there be a smarter way of doing it? Later on, I changed company. I went to a company who was very cost efficient, a semiconductor manufacturer, and they had actually done that exercise. They had looked into each IP, understood it, and tried to position the safety mechanisms exactly where they are needed. Was pretty good. The problem was their FMEDA was 150,000 entries, and the guy is still working on it today because and we put plausibility checks. We started running sanity checks over it. We had probabilities exceeding 100% and everything, trying to sanitize it to something that was reasonable and we could believe. Turned out to be about a 2 to 3 year effort. So we traded off this more efficient system with a huge development effort to actually get there and gain the confidence and test it that there wasn't somewhere something that had been missed. And this is kind of sort of a continuous trade-off, right? You make a more complex, more aggressive safety architecture, you find yourself in this huge dependent failure analysis challenge. Or you say, no, I design my system, which I think is the right way to do it, designing it for dependent failure analysis, so the person who gets it actually already is presented with a concept of how it should be done and then proves that the concept works, rather than just getting a system and saying, we assume there is no dependent failure across this interface, you go off and prove it, right? Some of these interfaces are immensely complex in the semiconductor world. I don't envy anyone who wants to do it. I don't do those things at ARM because they're so horrible. And then you can see you get all these cost factors, and it's continuously moving left, right, back and forth. And at the end, there has to be a sweet spot. So this is just a diagram that shows the trade-off. I put it in for completeness. It's fairly trivial. Here you can see sort of, what happens in a semiconductor if you apply different strategies. This is a strategy for random hardware faults at core level. If you do lockstep cores, right, your die power and hardware resources are expensive, but it is super nice because you get a diagnostic coverage irrespective of how the software looks like. Then you can say, no, we do safety flops and software-driven self-tests, and you tune around, and everywhere you tune around, you will always see there are plus points and minus points. You can have it software-centric, and all the semiconductor guys say, hooray, aren't we efficient? We don't have any additional cores, but you're still burning the cycles by the redundant software, plus the uncertainty, and there is no silver bullet if you look at it out of context. I think the solution becomes much easier if you say, I have an idea of where I'm putting it into, because if you say 5% of my workloads actually require this high ASIL and 95% don't, then it makes more sense to say, I will manage it in software, because I can then use the spare resources from the cores and the energy for the non-ASIL, non-lockstep work, while if you say actually 95 or 99% of my workloads, like in electric power steering, are all ASIL-D, then it makes more sense to lockstep the thing and get the effort of having to verify that the software has sufficient diagnostic coverage off the table and pass it down to the hardware guys, right? But the pudding never gets eaten, it never disappears, it just gets moved around, and someone at the end has it at the table and will have to deal with it. So the last slide is sort of an idea. We've been discussing this with different people for many years. The slide itself, the picture of this, I kind of took the inspiration from Rainer Faller from Exeter. And the idea is to say, can we position the different mechanisms at levels where they are most effective and where we get the best efficiency and at a good ratio for the overall system safety. And that is not easy because it actually requires a close collaboration between entities that today don't work that strongly with each other, right? As a semiconductor industry, we don't get these field returns and field data that the car industry has or will have if the EU regulations kick in and help us achieve a more targeted approach. So I think the cost optimization challenge is a challenging one, and we have to utilize the effects of the different layers in the cheese, and the question moving forward is how to do it. I'm happy to have this debate with whoever approaches me.
Excellent, very nice presentation. And questions, again, online maybe, or here, one here.
Hello, my name is Kepin. I am from BogWarner. So the question I have is that you talked about interaction faults. Are you talking about like common cause faults or like cascading faults over there?
This is exactly the challenge, right? You're trying to put it into the framework of the ISO standard. Yes, it could appear like a cascading fault, but the cascading fault has a starting point, and then it cascades down from the starting point. If you look at priority inversion, for example, a very prominent fault because it impacted the pathfinder. So the first robot sent to Mars for Mars exploration 20-something years ago was impacted by priority inversion on Mars, never on Earth. They tested for millions of hours on Earth. It never showed any problems. It came to Mars, it showed the problem, and they fixed it. In a strange way, it's an exciting story for the coffee break. So you have these different components, right? Each element by itself works okay, and you put it together, and you can't really point to a single part of the system that caused it and then had it cascading. It's the conjunction of these elements that interact with one another that create these adverse effects.
Okay, got it. Thanks.
Yeah, but see, again, the usual FMEDA are looking at the single failures. No? STPA is also looking a bit more at this interaction between elements that it could be also interesting. More questions? No? All shy after lunch? All tired? Okay, so I think, anyway, we are 2 minutes over, so I think we can move forward. Okay, many thanks. Okay, we go to the next question, next presentation from Daniel Carroll. He's working as a software assessment quality planner at Porsche. So good to have OEM here. And yeah, he's looking at SPICE assessment and process. So I think it would be also key interesting aspect to cover. Please.
Okay, thank you very much, Ricardo, for the intro. Oh no, this is the wrong presentation.
Yeah, it's coming now. Can we get after a Porsche each? No?
No, but it's a draft,
No.
as it was indicated, and I was sending one later then. Okay, grab a coffee.
We'll come, don't worry.
Yeah. No, because I was sending a draft, and afterwards it also goes through our compliance check with the Porsche group, and then there must be some changes and so on.
I know, don't worry. But we can start with the question, and then we go to presentation. Any questions?
We start with the questions. We can start with the questions. I can. Hopefully you find the right presentation. It was a PDF I sent a few days ago. But I can start on the freestyle because I can take the words from the last presentation from Christopher. So I'm driven. I'm at Porsche now since 6 years. I'm working as an e-spice assessor, so I'm not a functional safety expert. Let's say like this. From this point of view, I have 0 years of experience in functional safety. But I'm working within, in the early 80s, in the last centuries, I was starting my professional career as an electronic technician and working in the electronics, developing some electronic circuits for several years, and then I transformed to an economical engineer, and I'm driven by economies and by quality. And here in Munich, I made my final thesis for my diploma about integration of management system, and this is what's guiding me. Very good, yeah, this looks good. Thank you very much. I'm too big. Thank you very much. This is the good presentation. And I use the time to introduce myself, so we can dive into it. So my role is supplier software assessor. I perform process assessments at the supplier sites, and during my presentations, you will see I will step to several aspects of this. Okay, I can put myself. Is it? Yeah. Well, so to sum up the key challenges, yeah, we heard a lot already until now in the morning and the last presentations. There's a lot of pressure, time to market pressure. We want to develop our cars faster, and there are more and more regularity requirements coming up, and we have to deal with this. And of course, as mentioned, even the things get more complex. It should be cheaper, and we have to control our costs, of course. But, and this is the third point for this slide, there should nothing happen afterwards once a product is in the field, and especially when you see our cars for Porsche, it is our name is very important for our brand. We sell emotions, and quality is one very big issue for us, that it must be perfect. Yeah, so, and I want to go through, because Ricardo, you started the day with quality is not the same as safety and security, and I will show you some common aspects during my presentation. Okay, I will go through the analysis shortly, how to harmonize different ISO standards, but on a very high level, not as the colleagues have shown in a very detailed and in a very good way already. So think about their presentation and imagine doing the same with a lot of different standards. Then in the second part, I will go through some how we perform those assessments and what you find out what is important for us. And in the last chapter, then we go to the benefits of integrated processes. Okay, to make it simple, I will not go, I have a lot of slides now with such tables, and where I made some research. I simplified them all. This is what I learned from the colleague from TÜV now. So make a disclaimer, it is not complete, it's just an example, and I reduce to the complexity by concentrating on some of them. It could be done by all of them. So in my next slides, I just mention now the functional safety and cybersecurity, what could be simplified. Okay, and I'm not so, probably, all of you, I expect, in this first forum have heard about Automotive Spice. Automotive Spice is done for checking the process compliance and the maturity of a project or an organization. And even if, and this is in the first view something you think it's not the same as it is expected from functional safety or from cybersecurity, but if you go through the different aspects, like what is the focus, the scope we learned now is very, in the A-Spice, it's, I will show it later, it's often after, we call it the award of a project, and then the start of production, then the A-Spice usually ends. here, in the life cycle models, it goes much longer, but it is supported, you will see. But the last point, the traceability, it is coming again and again, and this is one of the most important aspects we will see in further slides as well. Good. Often we have quality people, we heard it gets more and more complicated and the monster of documentation is getting bigger and bigger. So the idea is what are the documentation synergies how you can to create those benefits, and I will not go as mentioned through all those aspects, but in all those ISO standards you have to fulfill, for example, very much for verification and validation and set up common test strategies and so on. And also the change and configuration management is also required by all the standards in somehow aspects that it is really important that you exactly know what is built into your project. And later on, whenever you have some failures, even also in the field, you have to jump back and have to know the exact configuration status when you have performed which test on which technical build. Yeah, so there are many documentation synergies that you can use in a standard, in a common approach. Yeah. We call it, when we perform assessments, the quality objectives. So, and this is where I built the bridge from quality. What is quality? And quality is also you have to build in your quality plans. We have quality gates and so on, and you have to clearly define what has to be built when. And when you have a project that is functional safety relevant, this is a quality objective that has to be achieved when you build your product. Okay. In this table, I went through ASPICE and product assessments. This is what I mentioned previously already. So the ASPICE is really checking, have you defined processes, and do you work according to the processes, and do the process achieve the expected work products? So is the purpose of the process fulfilled? And this is what we try to find out when we do our assessments. And the belief in the quality management is that once you have well-established processes, you achieve a good product in the time planned with the specification agreed. So this typical triangle for the quality. And that's what we try to find out when we do our process assessments. And process assessments strongly then support the product property assessments. So for functional safety, you dive deep into the technology when you perform the assessments, but you get the result from such process assessments. So that's the common, what we can see. Yeah. So I will go quickly through it because I see I want to show you a lot of other things, and it's a rough overview of all, and we can discuss, of course, in the next breaks. So now we come to some slides more to understand how we at the OEM, so Porsche is a brand of the Volkswagen Group, and so we have all the common rules within this Volkswagen Group. And whenever you want to get in a selection process to make a project for us, you have to agree on the so-called Formula Q. This is defining, so how for the software, defining some process activities, what will happen during the development cycle. And the group basic software requirements are one of many additional requirements we sent, you have to accept when you want to make a project within the Volkswagen Group. So, and within this collection of different additional requirements, there are always these different standards as well. And these group basic software requirements do somehow put it on a more precise level, several points, where we as Volkswagen Group expect we heard it in previous presentations, the ISO standards are somehow general, and there we put it somehow more precise then. And the most important, I have an additional slide for this red book now. This is this procedure has changed a few years ago now, and we have to apply it now. So this is to achieve the criteria for series production. And this has to be checked. And this production process and product release documentation has a chapter 6, evidence of software, and these 11 points have to be fulfilled at the end. These are my colleagues have to check, has this happened, where are the evidence, and the supplier must bring these evidences, and we make a risk evaluation if it's okay. And as you see, so I highlighted some points of this 11 in red. So determination of the scope of the software product and what is contractually agreed, and also the quality requirements that you have agreed. And there you see coding guidelines and so on. There's a lot of mention. These are all quality aspects that have to be fulfilled. And at the end, you see proof of a process evaluation. This is that you have to show that you worked according to processes. This is especially for this functional safety important when you want to achieve a level of this autonomous driving. Okay, and how do we work to achieve this goal? I want to show you somehow. We have already seen several times in different aspects. We see, let's have a look on the yellow line with the award, then the project itself, and then the approve. And what I heard now in the previous presentations is often things that happen before the award. There you work to find out how to build something. Yeah, so this is often very much more free and engineering style, let's say like this. But in the moment where you come to this award and in the PEP process, it's usually then you know what you want for the specific car, or you should know what you want for the specific car, and you define your quality and technical requirements, and this is the input for your project against which you are going to measure during the project cycle. And then, as mentioned in this red book, this is the blue box at the end. You have to go through this release for the series release step. We have, and the normal measure, you have a normal quality plane where you, for example, define in an early phase when the architecture is defined that you have to perform an architectural review. And during this architectural review, of course, you have to find out, for example, in the early phase, that it fulfills the functional safety requirements, and otherwise you have to adapt it. And we follow up with a so-called software maturity measurement, where we have monthly KPIs that we check. And we have then, these are the gray boxes where we perform different kind of assessments or technical revision, we call. Then we dive deeper into something, and there are different kind of measurement we perform. It's not always this A-SPICE assessment. It's often reduced or sometimes also more technically oriented. I have to speed up. Okay, this is just for those who have not seen ever before how it looks like, such a ASPICE standard. The ASPICE defines a lot of different processes. They are grouped to different process areas, let's say like this. You see a building block for software engineering, for system engineering, or management process, supporting processes. And we in the Volkswagen Group, we have a selection in the previous standard, in the 3.1 standard that is now in the end of its life cycle. There was the so-called VDA scope. And now it's we apply more our Volkswagen Group scope. And there are, I will have a slide later on for the tailoring, because you always have to adapt it to the context of the relevant project. If you only have a software project, of course, you have no system level to be assessed. And as you can see, there's a own block for cybersecurity, and also we heard in another presentation today about machine learning. There are defined processes by the ASPICE to evaluate also these machine learning processes, and these, of course, there is a block also for the operational phase, as well for the cybersecurity in the operational phase. Okay, I will not dive too deep into those things. My time is speeding, going away. So last point is benefits of integrated processes, and I will show you. So this is a screenshot out of the VDA of this ASPICE scope. You see this V model, and probably it's not readable, but it starts in the upper left, in the upper corner with the stakeholder requirements, system requirements, architecture, and it goes down to the software unit level, and then it goes again up to the validation step by step. And this is the logic in all this ASPICE thing. So take something and break it down and make a measurement by reviews for each phase, perform reviews before you proceed with the next step. And the idea is, because of all review findings, you save a lot of time instead of having tests in a very late phase and then changes that are always more cost intensive. So there are a lot of benefits of, I call it shift left. You should, it's also mentioned with traceability and consistency. So the traceability is the linkage between the things. And the consistency is also always the check, is this linkage between these elements correct? So this finding out the correctness. It's not always linked to one to each other, but it's correct. And this is performed usually found out by reviews with, for example, by requirements. There's usually when you architect and the tester performing the review of requirements, for example. Yeah. Okay, and there are many chances to benefit by improving in early phases. And we heard how can we simplify? There was also some a remark in the morning, and simplifying. Let's assume we have now harmonized processes and a process world within your company, and now it comes to a precise project. And this is the most important thing. Then with your concrete project, you can perform a tailoring. So, and this is is it cybersecurity relevant? Is it functional safety relevant? Do I have reuse of code? How long was it in use? And things like this. And you can go through a long questionnaire. So it's not a long questionnaire, but you have to analyze and define the scope of your project, and then you can adapt how you will perform your processes, and this will be verified then by assessments. This is often forgotten because then you must apply those all those standards fitting to the precise project. This is the message. Yeah. We as assessors, we have tools for that, where we can, so I come from this ASPICE world, but we do in our tools now a mapping for functional safety and for our additional requirements that come with, from the Volkswagen Group, and we do this in our assessments all together. So when we plan our assessments and then in the interview, and then those different parties within your organization that is assessed by us, as well in our own organization, they can benefit by these reports. I'm 5 seconds in overtime, so harmonized processes. ASPICE is an enabler for it, and you can, by applying good processes, you will have a lot of synergies and save money. That's the short message. And I get the sign, my time is over.
Many thanks.
I hope it was not too fast, not too much, not too superficial.
I think it was okay, yes. Okay. Let's see now the questions. Okay, one question here.
Thanks for the presentation. I have just one question, curiosity. Based on your feeling and on your experience with the conformity of a SPICE, is fully reached for functional safety or cybersecurity? Is fully reached the compliance to 26262 or 21434, or there are additional activities to be performed, technical or formal activities?
I have to answer differently. So there are requirements that have to be fulfilled for us as a customer. These are requirements, and I measure then in my assessment if you fulfill all our requirements. And if there is a requirement, be compliant to ISO 2626, then I have to find out, is the HARA made in the right moment? So it's not matching 100%, but if the customer requirements are there, I check for the fulfillment of the customer requirements. For each requirement, there must be evidence that of validation or verification. So it's not the ASPICE, but it is fulfilled by the requirements that comes to you.
In terms of process, so the process are equivalent? Or?
The output must be there. So if you do not fulfill a requirement in an assessment, you will fail. You have to be downrated, so that then you will be downrated due to the process is not fulfilling its purpose at a certain point of time. The time is also, at the beginning of a project, it's not important, but at a later phase, it is. I answered somehow the question.
Thanks.
I missed to make a short step to the FOSS where but Sylvain, you have to do it later. So, I have my partner here. He will be in the discussion where we have then later on about the FOSS in the next session, and there we have also some aspects how we deal with this within the Volkswagen Group. Okay.
Okay, one question here, and then we move to the next.
Hi, my name is Kipin. I am from BorgWarner. So I understand that you are trying to harmonize some part of the process between ISO and ASPICE, but do you have a separate ISO 26262 assessment? Because there are things in ASPICE which are not obviously mentioned.
Yeah. So I found out during my assessments in the past years, in all companies, and of course also in my company, these are very isolated departments always. And usually in my ASPICE assessments, they point always to, the colleagues are in a different department and cannot be reached now. But because people think it's something completely different, but it is overlapping. So, and now we are all in a time where we have to save somehow money. And so that's why I started to, where can we find benefits? Because we have discussions, how can we save money by quality, reducing quality targets. But it is, there are more potentials when we have not several departments isolated in silos, and if these disciplines work together.
Yeah, I fully agree.
And
okay, I think we need to move forward. So, thank you. Many thanks. Okay, we move to the next presentation from Sebastian Klaus, that is a senior manager for ADAS and AD functions at FKA. And I see here you also spent a period in Volkswagen. So, floor is yours.
Yeah, so thank you very much, and hello from my side. So yeah, I will try to spend the next minutes basically giving a little bit of different perspective. We heard a lot of theoretical aspects today, so I want to basically give some insights about how we use, or like not use, but how functional safety plays a role if we just speak about the aspect of testing automated driving systems on the road. I will focus on the German part, but I come to this in a minute. So I will just give a brief overview about the activities in this area. We heard already a little bit before lunch about the regulations. I will add to this in terms of testing. And just to already give a hint, I will talk about the role of the safety driver in this case and a few challenges we see there in regards to hazards and risk and performance in testing, and of course hopefully come up with a solution, or propose a solution how we can balance this in the end. Just very briefly, what's my background and where I come from. So FKA, we are a small company with 100 engineers. We are a spin-off of Aachen University, and this is important because what you see on the slides, we love to build prototypes. We do love to basically bridge ideas from the university to industry, and this basically always means balancing innovation with, in this case, safety. So that's where basically we come into play. And if we look at what we normally do, we do a lot of driving simulator studies where we operate our own driving simulators for example, in regards to safety. We do controllability studies. We go out on test tracks, basically, as you saw, like with completely new steer-by-wire systems. And this will be the focus of my topic today. We do naturalistics data collections, basically go out with test vehicles on the road and collect data from it. So basically just coming from our part to basically general history, I basically looked up about a little bit of history. We heard about a lot of challenges we have already today still with automated driving. and we heard that it's basically here as pro and con today. But if we go back, we see actually that automated driving was tested. Just a few examples there. You can even add more from the US. But in the early 90s, there was still already this Mercedes S-Class driving from Munich up to the north, crossing basically complete Germany with minor interventions. So that was really one of the first projects. But what I just wanted to show you, there have been a lot of activities already. And in terms of safety, I would call it, let's not say the Wild West, but of course every system, every prototype vehicle, every testing activity had some own safety mechanisms in place. They already came up with some ideas how to do it. And so basically we did the same. We dived into this. Then already in the 2020s, we built up our own test vehicle, basically to go out on the road testing automated driving functions. So that's where basically we built up this vehicle and equipped it with some additional sensors, some interfacing of steering and braking, of course, to make the ADF function, the automated driving function, be able to control the vehicle. And so then we build a prototype function for this as well. And then we basically, and back in the days, we as, let's say, we are not an OEM, we had to apply for exemption to basically go out on a test with the vehicle because we weren't fully compliant with STVZO because we were driving hands-free. We learned that in the morning about regulations that is now actually coming into place, allowing hands-free driving even for level 2 systems with a DCAS, but back in the days you would needed an exemption to actually do and go out on the road testing this. So yeah, this is how it looks like. This is our campus in Aachen. So as you see, we are driving with a safety driver down around 2.5 kilometer round trip on a campus that's somehow on the outskirts of Aachen. So it's technically still within city limits, but as you see, it's not dense city traffic. So very easy for the function to drive. But in this case, very special function, it had to handle a roundabout without any additional signaling. And you see basically pedestrian crossings and obeying them. And so the safety driver, of course, needs to be there and monitor the system. But the video will go on longer. But I think you see it's a really wide area. And the roads are wide, so that wasn't really a big thing there to drive. If you look at the next video, this is Düsseldorf downtown, pretty much close to the Kö, the shopping center or like the dense hotspot there. And there you see the situation is completely different. The area is really crowded. And on the right side down here, you see basically what the ADF function is seeing and what it's doing. So you see the trajectory, you see all the objects, you see the traffic lights, which we pick up from V2X. So we do see like the safety driver in this case does not need to intervene, but there's way more things he needs to obey and make sure that we stay safe, even though we are driving with this basically unvalidated automated driving function. So this was basically, let's say, the past, and just basically now coming to what is currently the state of the art. As we heard in the talk before lunch, we now luckily have all the regulations in place. So we do have something where we basically, the DCAS regulation, which is now new in place, which regulates level 2 plus systems, even though I don't like the name, but you get the idea. Basically, that's the new one. We have the European or like the European regulations for kind of like this goods mover or this shuttles, even though it's still limited to small amount of cars. And then we basically have national laws basically allowing this. But, and that's the important part, is there's no harmonized standardization for European testing. So you can get the European homologation, but if you want to test in several different countries, you still need to apply for a permit in each country. And basically in Germany, the way we can do it, as we see, we still have this paragraph which normally is used by OEMs, and this is still valid, the 90.6 in allowing normal regular testing of ADAS systems. But, and that's the novelty in Germany, we have this new law allowing automated driving, and there is the let's say, regulation in place how to do it, and this has a special paragraph for testing permits, and this is focusing on higher automation. And we heard it in the morning as well, the new Fernlenkverordnung is in place allowing teleoperation, but again, this has no special testing paragraph. But if we now focus on the IFBGV part, we see actually that we have companies testing around, so there's a list of approvals published by the KBA, so we see the major players from OEMs, well known, BMW and Daimler, which are basically already offering the system, so they basically do the testing there as well. But we do see level 4 testing for mobility suppliers, which got the approval, and for example Moja is testing in Hamburg, Holon is starting there in the next month. So if we look closer to what you need to fulfill for this testing paragraph, you need to hand in a development concept, and this is actually the same for every applicant. So it doesn't matter if you're an OEM or only a university applying, you need to put in a permit, even for a single vehicle, each vehicle gets a single permit. But there are few assumptions, and the KBA wants to see. So for example, normally if we talk about automated driving testing, we have the assumption that we somehow have a base vehicle which is homologated, and we just use it as a mule, right? So we cut it open and put an ADF function on top of it, or we, as we saw it with the mover vehicles, have basically a single vehicle approval, which it's a purpose-built vehicle, but it can drive by itself and got a permission for that as well. The very important part is we heard a lot about Waymo already, but the important part is during testing we always need to have the safety driver or an operator on site, right? There is no way in Germany if you apply for a testing permit you can take this out. At the moment there is a discussion what on-site means. Some say you can run on the side of the car, some not, so this is a technicality. But the most important part is, I want to tell you here, is the safety driver is the fundamental part of the safety concept, and that's asked for by KBA, right? So you need to show how you balance the safety by introducing the safety driver and making sure that you describe the task and duty of the safety drivers, how he's able to override, deactivate the system, and how the system is then behaving, and what kind of interaction in terms of HMI the system has. If we now take a look at what the safety driver needs to do, you saw the videos, and you in the videos only saw the left part, so you only saw basically me and my colleagues monitoring the system, right? So we were observing the vehicle moving, we were checking and making sure that everything is safe, we are not identifying any critical situations, but there are of course the situations where we need to correct, right? And as we basically have an unvalidated system, anything can happen. So we would need to basically counter steer to keep the vehicle in lane. We need to brake the vehicle if it's accelerating unintentionally, or the other way around. And so in even the worst case, disable the system completely. So the way how we basically ensure that the driver can do this, we give him some measures in the safety concept which I want to show you. So of course, the most important part in this case is to basically how we train these safety drivers. Then basically how he's able to override the systems, what kind of limitations we put in the actuators, that we ensure that he's even capable of control the system. And then in the last part, basically, if we still need to do is we need to limit the operational design domain of the system to ensure that we balance basically safety driver performance and vehicle performance with the ODD. So, and this basically the balance I want to show you with this example. So if you take a look at the slide, you, of course, in the end, we are talking about a final product where we want the self-driving system or the automated driving function basically to perform all driving maneuvers, right? So he needs to have full access over the vehicle, and this basically ensures that he can perform the same maneuvers as a human driver can do. So if we think about the actuators, we don't need to think about basically ensuring that the system is controllable by a driver, but we just need to ensure that whatever the SDS sends or the ADF, basically the actuator will make sure that this control is executed properly. But in the testing phase, we do have the challenge that the safety driver somehow needs to be able to control the system. So we basically need to balance his performance with the kind of limits we put on the actuators, and then basically limiting the scenario coverage we can achieve when we limit the actuators. So this is basically the balance, and just to show you how this is as an example for a system with a lane, just basically what you see on the left, it's a little bit blurred, sorry for this because it's customer data, but as you see basically you have, is it pointer? No, wait, no, sorry, no, I'm completely off. Sorry, there it was. Oh, how do I go back? Sorry, my mistake. Yeah, now I understood it. So what you see basically down here, you see a blue line and a yellow line. So if you basically... yeah. All right. Yeah. So the blue line basically indicates lateral movement of the vehicle if we have a steering error and nobody's correcting it, and what you basically see is lateral displacement in lane over time, and then the yellow line you barely see here indicates basically leaving the lane for the vehicle, and so this is something, if we don't interact with a safety driver, then of course we leave the lane and crash into whatever is there. And then basically down here we do the same with the safety driver intervention. And what we see is basically at a certain point, it's really tough to see, but here we basically, oh, sorry, we change from a steering failure to counter steering of the safety driver, and he makes sure that we stay in lane. So this is basically just, let's say, as an example from the HARA, just to show how we mitigate steering errors. And then on the other part, on this side here, in terms of performance, we of course want to make sure that we come up with these limits, and that's the left side. So here we basically limit the steering angle over velocity. So for higher velocities, we don't allow that much steering angle, or we limit steering rate down here as well to make it controllable. But then we need to ensure, and these are the lines here in the middle, to ensure that the vehicle is actually capable of performing the scenarios. So as you see, basically these are recordings from drives we have done manually there to ensure that normal driving can happen with this ADF. So, and if we stay within this lane, then we basically can balance performance and safety. So we can ensure the controllability with these limits, but on the other hand, make sure that the system is capable of driving there. Yeah. So Basically, so now I come back here. What I'm just saying, so for this safety goal, we do need all these safety measures I already introduced. So we need to basically train the safety driver. We need to ensure that he somehow is able to override it. We need to have some actuators in place. And in the worst case scenario, we even need to basically limit lane width or even the type of scenarios where he's able to drive. But if you, like in terms of controllability, look at this data, and it's random data, I had to change it a little bit, but in general, that's the idea. For example, general controllable 5 Newton meters, that doesn't come together. So normal drivers can basically control 2.5, 3 Newton meters as a steering error, and even the reaction time is faster than a normal driver would be able to. So the way we are doing this, we need to at the end train the safety driver and then make sure that the safety driver can basically pass this test. The way we are doing it is basically we have a software which basically can reproducible introduce the errors while driving to the driver, and then basically we measure his reaction time, reaction speed in terms of counter steering, and basically map these performance measures from him to the requirements we came up with in a safety concept. And so this is basically what we have put in the software, and the way it looks like for kind of like this training. We built the training vehicles which you could use basically for this kind of scenarios, where we basically use the production vehicle, used in this case the interfaces which were already in the vehicle to basically introduce the errors in the system. Yeah, it's just my colleague checking everything. But as you see, you have the computer and you can introduce the errors. The trainer on the right side can even steer the vehicle with a stick, basically doing the Wizard of Oz driving. You can even use an automated driving mode, which then is able to reproducible trigger special scenarios at a certain situation. So you will see in a second, they're in automation mode and you have fault injections triggering here on the right screen, and the driver needs to steer, and then you can basically check the data in the end and basically make sure that the reactions you require in terms of your safety concept, you put on the burden you put on the safety drivers, you make sure that you basically test them and document it at the end, that you can hand it in to, for example, KBA for your validation of your safety concept. Okay, yeah, that basically brings me to my conclusion. So still, that's my key message. We heard about of AD testing in Germany. Still, it requires human supervision, and what we call it the safety driver intervention concept is one key aspect for the safety argumentation still. And so just if you do that in Germany, make sure your training is up to date. And yeah, hopefully you took some away from my presentation, and otherwise there's another video playing for the coffee break now. Thank you very much.
Okay, coffee break or question? Oh, 2 questions. No coffee.
Thank you. Yeah, it's Siavash from AVL. Can we say that integrating the driver in the vehicle for the validation purpose and training it, of course, it's like that you have developed a prototype safety concept that is at least capable, or let's say its compliance is approved for level 2, and then it is used to develop the higher level autonomous driving?
Well, yes and no. I mean, technically it's still, if we go test, it's a level 2 system because we have the safety driver. But the problem with this, basically, we cannot use the argumentation from level 2, because the argumentation from level 2 would assume general controllability. So if you look at it, a regular car nowadays, if you drive with lane assist, you can easily grab the steering wheel and just override it, right? This is the 2.5 Newton meters I was talking about. That's a controllability testing that was done, let's not say millions of times, but plenty of controllability studies already performed showing this is somehow the limit for the general controllability. The problem is if you take this performance from this kind of steering system into, like, let's say a situation like this, urban driving, then the performance of the steering system is so limited that you can not perform all the scenarios out on the road, right? So every time the system, the actuator would hit a limit and cannot perform the driving task by itself, or the SDS. So this is why we need an extensive concept, which then allows more steering force to be applied to the steering system. But then we lose the argumentation for general controllability, and then we need to basically from base to base or from case to case argue, look, we have the higher performance in this test vehicle, and we lose general controllability argumentation, but then we do for this kind of test vehicles, we have a limited set of drivers either way. So when we put all the drivers through their testing with the fault injection software, and then we can at the end argue, okay, the general controllability is not given, but all the drivers who are driving these vehicles have performed this kind of tests, and I can prove it to you. Here's the data. And I can actually show them recordings from counter steering. You can even accumulate these data over different drivers because it's reproducible. So then you can actually tune your safety case in the end because you know the average performance of the drivers, and then you can even allow more performance in the actuators or less depending on the data you collected during your testing. Does that somehow?
Yeah, what I understood is that perhaps some performance limitation would be different in this vehicle in compared to the final one, because here the driver is an expert. He needs to take over the control differently from the normal driver. I understand.
Yeah, that's right. I mean, just saying that the final vehicle wouldn't probably have no limitations because it needs to take over the full driving task. That's the problem.
Okay, maybe let's move quickly to the next question, and then you can talk also now in the coffee break. So very quickly, the last one.
Hi, I have a question regarding the ODD limitation. So you mentioned that there is some kind of ODD limitation that you put on top of driver instructions plus also steering, basically actuator control, etc., etc. So how do you control? Because most of the times these kind of road testing, on-road testing operations might involve, say, for example, low mu surfaces or some kind of things like that. No, so for example, if you say ODD is limited only for, say, high mu surfaces, like that there is enough friction in the road or something like that. So how do you control that this is being really used for that particular purpose? Because most of the times it's good to write it on a piece of paper, but in reality it might not be executed in exactly the same way.
Yeah. Good point. So that's the second part of the safety driver training, which I didn't put in the presentation, is basically preparing for testing. So I mean, the concept we are using here is mainly for like these shuttle systems. They go on specific route. If we look at the Hamburg case, the Moya cases, and the Holland cases, they have specific areas where they drive. So they basically, then you come up and say, okay, you have a catalog, look at this situation, look at that situation, here you need to be careful, you take over driving, so be really defensive here. So this would be then just, but in general you can just say, I mean, this is really, if you go into urban driving, then you need to do it on case to case. If you do highway driving, then you don't need to exclude that much, because for steering, normally the road is wide enough.
Okay, many thanks. Okay, so coffee break. Let's try to be here back in 20 minutes. Okay, thank you. moving, use this microphone, otherwise this.
Yeah, yeah.
Okay. Are we ready to start? Last part of today. Sad but true. So, next presentation, we have Dr. or Professor Gordon Helger. He's the head of the Fraunhofer Applied Research Center for the Connected Mobility and Infrastructure. Yeah, you can point at it. You will be slow, but yeah.
To try it out.
Okay, the floor is yours.
Yeah, thanks a lot for the introduction. I want to demonstrate one use case, state or condition monitoring of automotive cameras. Actually, we are working in Ingolstadt very close together with former Continental, today Aumovio, and in especially focusing there on research and reliability engineering for that automotive cameras. Okay, sorry. So what is the content? I will give a brief introduction about the research we're doing in Ingolstadt. I will talk about automotive cameras, manufacturing, and reliability engineering. Then I will discuss the condition monitoring or state monitoring, and especially optical features like sharpness, but also then operation monitoring. So means is the window damaged, is the camera covered or blocked, and a short conclusion. So in Ingolstadt we have medium-sized University of Applied Science. The Fraunhofer Society usually locates at research-strong universities application centers, and so we have founded that application center for connected mobility and infrastructure in Ingolstadt. Ingolstadt is in Bavaria the center for artificial intelligence application in automotive. Means in any range, whether object detection, whether manufacturing, so all field of artificial intelligence research for automotive. So the application center focus really on connected mobility, state monitoring, condition monitoring, optimization of traffic flow. So they are, in the end, by artificial intelligence reinforcement learning, the traffic situation is judged, and then traffic lights are controlled. Traffic dependence or in independence of the amount of traffic to optimize the traffic flow. Yeah, one major point of the research which we did in the last 3 years was to set up test field for connected mobility to investigate autonomous driving function and investigate the usefulness of infrastructure supported maneuvers or safety functions. And I'm pretty convinced that in certain domains, the support of sensor systems for environmental perception from infrastructure will help really to foster autonomous driving, and especially in the urban field. Here we have built up from the A9 to Audi Carriot in campus, an urban test field containing in the end 22 masts equipped with camera, radar, and LiDAR. So for research application, all sensors are applied or used. So the topic for today is condition monitoring for automotive camera. Here you see, an old camera, a stereo camera, 10 years ago, where the optic modules, you see 2 optic modules in the camera, and then the main part is the data processing. So object detection is done by the camera, and in the end, just object lists are provided by that stereo camera to provide driver assistance systems.
the development went on. So you see nowadays so-called satellite cameras from the respective Tier 1 suppliers, which are small cameras which are distributed over the car, surround view, but also the front viewing camera, where really the data processing is transferred from the sensor to central processing units. And that is in the end generalized. You have sets of a certain number of cameras and a driver computational unit where the data processing takes place. So let's look into such an optic module, which is in the end the heart of the camera, where you have just an imager chip. In front of the imager chip is mounted the objective. The mounting of the objective is quite challenging. The objective has to be mounted in the range of 2 micrometer accurate in front of the imager chip. You see that in automotive, the optic is quite complicated. It's a 7-lens stack system, so a lot of cost of an automotive camera is within the optic system. Typically manufacturing system, it's an active alignment. It does a through focus scan by collimators. Cross sections are projected onto the imager chip, and then the complex lens system is aligned. And that's in the end due to the requirement that the front viewing camera has to have to recognize object from 2 meter to long distance, and therefore the requirement of the optical system is quite hard. And that reflects really that in the end of line test, the camera module is tested with respect to the sharpness, and there is a very hard limit on the sharpness distributed on different test fields on the chip. So sharpness is in the end measured in the modulation transfer function. You see here a stripe pattern, and it gets closer and closer, measured in the end in stripes per millimeter, and then the modulation function is calculated. In principle, the intensity black-white is calculated, and clearly here at the end it goes to 0 because there you see just gray. Here you have really a intensity of 1 between black and white. So and then you observe that function which is changing or which is reduced when the optical system is not working well, which can have in the automotive camera when I quickly, no, step back, sorry, wrong direction. No. Wanted to quickly to step back. In the end, there are, from optical point of view, there are 2 main drivers for the degradation of the camera. It is the mounting itself, and it is the objective. So here you mount with a compensating adhesive. So the specification of that system is in about, or the focus distance is specified with 0.1 millimeter. So you compensate by some additional glue, by a glue interface, the variation of the focus of the lens stack. So with respect to reliability engineering, typical physical simulation, co-simulation is done, where you see that when the system heats up, bending takes place, expansion takes place. In the end, the camera is optimized on operation condition. So in the end, when the camera is called, the image will be not as sharp as when the camera reached operation temperature. And you see that there is a bending of the printed circuit board due to the thermomechanical mismatch, which is also displacing the chip. Reliability engineering in the different states, the bending and the expansion is measured, and here some simple test bench for single camera measurement for the respective modulation transfer function. then an automated larger test bench where a KUKA roboter is moving respectively the collimator and measuring then on axis and off axis with respect, and projecting this kind of cost onto the imager, and the transfer modulation function is calculated on those slanted edges or slanted lines. Now, reliability engineering, condition monitoring. In the end, you can design a system which will in the end degrade. No system will really stay for infinite if you do not put really infinite money into the system to make it robust. However, when you design a system for the respective lifetime where you end your lifetime of the car here, the system would be robust because degradation, just in this case temperature driven, takes place and reduces the lifetime. So you might have a system, reliability engineering, which you do not need to monitor because it is robust over the lifetime, or if it is safety relevant, you should monitor it. So when we come to monitoring or condition monitoring, we talk about the key indicators which are used to measure really the state of the system, and then the aging drivers, which are really the drivers for degradation. Okay, key indicators are, in our case, sharpness, dead pixel, noise, failure rate in communication between imager chip and the control unit. Drivers, temperature, current, moisture, radiation. We tested radiation because we wanted to create dead pixels. And then the key indicators can behave differently. They can degrade in a slow way. They can spontaneously, catastrophically fail. We can have all different root causes. They could recover. Then we have to look into the failure, into the key indicator again when it behaves randomly. But failures can also occur arbitrarily, and those are the most critical. Then we need to define a failure rate, and we need to try to measure them. So if the system or if the key indicator really degrades slowly, we can, based on models, calculate the remaining useful time of life. Catastrophic failure we approach with anomaly detection, and then we are able in real time to estimate the state of the system. So I'm talking about our cameras. So we have them here with ASLB for the camera systems. When we look onto the system, we have a lot of different fields. We have the electronics in the optic module, the imager. We have the communication interface. Then we have the optics itself, the mechanical damage. We have environmental effect and communication between the camera and the control system, and so on. So we are focusing now on the imager chip. Let's start with dead pixels. An imager has usually from factory coming 30 to 40 dead images, dead pixels, which are covered here. You see them marked, but I have to admit that you hardly see it, those 30 pixels. And in the usual camera software, they are anyway covered and interpolated between the good pixels. So we tested, but under the typical test condition, there were not many new dead pixels. Therefore, we just created synthetic data from created dead pixels, and the point is the pattern recognition or the object detection stays quite robust. We have really to increase an large amount of dead pixel, which is not occurring. We can debate when we have a certain distribution of dead pixels where we should detect small objects, how much is then really the impact of the dead pixel. Noise is the next one. So amplification of the different imagers. There we see that we need to increase the noise really dramatically to obtain really a reduction in detection of the object. Next failure are communication failures where the image is distorted, and by then when we just run an object detector on that distorted image, we get definitely mistakes. So distorted images we should really filter out. We were interested in what is really the impact of the sharpness on the object detection confidence. So therefore we created a system which, where we could defocus the camera and investigate on a static scene what is really the impact. And our observation was that until 40 to 60 meter, we can really unrealistically large defocus the camera before changes occur. Starting from 60 meter, we really see an impact. You can observe it here. Cars are detected as one car, and the bicycle detection degrades because bicycles are detected having their really fine structure, which is not visible anymore when the camera gets unsharp. So let me continue further. So how to measure sharpness in field? We are following the way that we detect traffic signs where we have nice slanted edges, because on those traffic signs we can then calculate the modulation transfer function on an edge. We, in addition, fit kernels which are producing the so-called point spread function, because when we fit a point spread function by convolution to the measured transfer function, we are able to get more information and separate between influence of sharpness from the optical lens stack and the imager position. And here you see then the degradation for a couple of cameras. You see here the key indicator, which is for us the calculated transfer function and the fitted point spread function. You see for the cameras that they designed in a typical way that due to the shrinkage of the glue, one adjusts the system that in the beginning of the lifetime, the camera gets better, gets sharper, and then it degrades. But the degradation we see here in that image is within uncritical sharpness degradation in the end. It is nice to monitor it, but for the functionality, this amount of decrease, which is then stabilizing, is actually non-critical. So the next more critical situation for monitoring is to monitor whether the camera is functional, whether it is, for example, dirt or covered, whether the images are correct. Okay, what to do is at first to select really the data set based on commercial or available data sets. Then a couple of different models were trained with a result that we get, based on that data set already quite a good F1 score. That is a typically fast or easy process to get to the 95, 99%, and then we have misinterpretation, which we can observe here. So that is a driving scene where we see that defects are detected spontaneously, where we have further to dive into why suddenly on such an image and what is actually detected as a defect, as a kind of crack. We can see it here, what happens. You see it already here. We detect a defect, which is just a small sun reflection, which is in the end not very critical. I mean, here in this area, there is a degradation of detection, but not really critical. Static covering, that's in principle an easy case to detect, where we see here that the car should start. Here is a leaf placed onto the image, on the imager, and this kind of failure in the image is simple to detect it. But cracks in the window, small gaps that are much harder things to detect. In the end, condition monitoring for automotive camera has been demonstrated, sharpness and the damage of blockage. Condition monitoring enables to ensure that, that the system operates within the required specification. Camera design is already very robust and is going to be further improved, but mainly cost-driven. And the other thing for condition monitoring, which I in the end didn't discuss much about it, is that we obtain really field data to optimize systems by having data in field to really cross-check and evaluate our acceleration factors. Thanks for the question and answers.
Very interesting. Questions, again, online, or one question here.
Hi, Alek here from AVL. Thank you for the presentation. So my question is about the sharpness monitoring you said. The sharpness calculation, does it differ, the method of calculation for day and night vision?
I have to admit that the method we are using needs to detect the traffic sign, and that we did during day. So for checking the sharpness, which slowly degrades, I would use best condition, day condition, use then defined objects, which I can recognize like traffic signs, and then I calculate the sharpness. I mean, I need certain algorithms which are clarifying that the traffic sign is not dirty. And then I have also to average and look for good traffic signs which I observe on my way. In the end, really observing traffic signs, storing them, and then evaluating it is a method for monitoring. And in the end, when we do that, we might save a lot of cost again, because then we can reduce manufacturing costs for the cameras, which are definitely over-engineered in the moment.
Thank you.
More questions? Okay, two questions.
Thank you. It's Siavash from AVL, Italy. We are colleagues actually, but from different plants. The question is simple. In one of the slides, I saw that you talked about communication issue of the camera and some issue that was created on the image. Maybe we can also move to the next
okay.
slide.
So the communication. So when the communication pass, the timing is distorted, and then distorted images are here. That distorted images are transferred, which might happen. That's, from my point of view, a problematic failure due to certain reason. The communication timing is distorted or has a failure, and I get this kind of distorted image.
Yes.
Yeah.
Communication between what exactly you mean? If the PCB is there and everything is integrated on that PCB, I suppose in this case,
so in principle, I have two communication protocols. I have the CSI, which is between the image, which reads out, is a serial interface reading out the imager. And then usually when I use now the so-called satellite cameras, which are separate simple cameras, and then they transfer the video stream, the images to a central processing unit. Then I change to Ethernet, and then there is this the gateway from CIS to Ethernet on the small board, and then it's an Ethernet cable which you plug in.
Okay. So it's not the case that we have everything integrated on that PCB, but it is centralized processing that.
In the moment we are focusing on that, because then we have the algorithm in our own hands. The algorithm would otherwise run on the stereo or mono camera, But from my point of view, those systems will get more and more outdated, and really the data are transferred and processed centrally. That's a big problem for the tier ones in the end.
Okay, there was one more question. Yeah, the last one, yes.
Alexander Grimm from SGS TÜV Saar. I wanted to ask you if you think the sharpness checkup on daytime is enough, or should nighttime also be considered?
I think during daytime it is enough because it's a slow degradation process.
I thought so too. Thank you.
Yeah. And
your thoughts.
Yeah.
Okay.
Let me one comment. In the end, for the TÜV, I would always say we should integrate, or we could integrate a simple sharpness test in the garage. Just having there some object which is detected, and sharpness is then part of the Hauptprüfung.
Thank you. Okay, let's change now chapter. We move to more open software. And we have now Dr. Alexandre Matausz, Chief Expert Software Architecture at Electrobit.
Okay, thank you very much.
Okay, please.
So now again for something completely different, we're going back to software, and I've been talking about safety, security, and open source, how this fits together and how they actually support each other. And actually, thank you to Christopher Temple for mentioning the cost factor, because this is also one important aspect I will address. So therefore, let's first start with why actually do we need open source software? We have lived a long time without, so why is this coming now? Then we have a look at open source software and security, what is done there. After that, we'll have a look at open source software and safety. How can we make open source software safe? And combining this information, how can we then build a system out of this? And in the end, I'll conclude how this fits together for the software-defined vehicle. The shift to open source software, and this is actually a paradigm shift which started already, so there are cars on the road that use open source software like Linux and everything you can imagine. And why are car makers doing this? It starts with the SDV, and I don't like this buzzword which is currently going around, but SDV means software defined, and this means that you can change the key function or the nature of the device by changing the software. This is the idea behind SDV and not what is going around on LinkedIn at the moment. But it really means you can redefine the value of the device, and this is what car makers want to achieve. And therefore, we need a paradigm shift in the development. Let's have a look how we developed ECUs so far. So this was requirements driven. So most here know these huge lists of requirements that have been given from an OEM to you to develop your software or your ECU. It was kind of a waterfall approach. And it was repeated over and over again. So every time a new generation was developed, you received new requirements again. The reuse was limited. So you had the requirements, and then the objective was build it like this. Idea of the OEMs was, of course, they can switch suppliers, and the knowledge they had, their IP, was in the requirements. This is totally different with open source software. Actually, here it's you look around what you have, you analyze the existing components. This is an iterative, community-driven development, so when someone needs something, they add it to their software. And basically, this allows you to evolve with your software, what we would call here standing on the shoulders of giants. And this is working quite well. I mean, most of the internet is working on this software. And therefore, the idea is, let's analyze what is out there, and then we build on top of this, which gives us a much shorter and much faster development cycle. But the question here is now, how do we get safety and security into this approach? And this is a challenge. But nevertheless, the idea is really that we take the proven automotive software, the foundation that we have in the automotive world, and enrich it with open source. So extend the concepts, and we adapt our engineering, safety, and security paradigms to achieve this. And therefore, let's have a look at what we have. Let's start with security and open source software, and to be frank, this is nothing new for them. Open source software and security fits together for ages. For automotive, we have a couple of standards that we have to look at. We have things like the ISO 21434, the EU and ECE 155. We have to create TARAs, so threat and risk analysis for our systems. And what actually is the implication of this for the software? We need to have a security management. So we have cybersecurity management systems, risk assessment, incident reporting, customer notification monitoring, and not to forget, updates. You have to plan this. This has impact on the software architecture. You need to identify the critical elements using a threat and risk analysis, a TARA. You need then adequate protection measures that you implement, basically by separating the critical elements via a proper software architecture. You have onboard monitoring, and you need to have a rigid freedom from interference implemented. And of course, it has impact on the implementation. So you have language and coding guidelines similar to safety actually. So there's CERT-C, there's CWEs, there's MISRA. There's Rust coming up as a programming language. You have to perform vulnerability analysis, either via dynamic analysis or penetration testing activities like this. And of course, you have a thorough testing using fuzzing or penetration testing. So, but this is something we know for quite some time for security. And this is no difference if we do a commercial development or if we do open source development. So this is no change. In both cases, we have to do it. Now, how does the work split look like here between the open source community and commercial companies for development? So let's start with security management. So the open source community, depending on the project size, they have some support and some activities going on, but it's usually rather poor. And this is then where the commercial companies jump in. Like, for example, Linux distributors. They have a business case around providing the security updates and managing the software. And this is how the open source community and commercial companies play together. One providing the software, the companies providing the security. Same for software architecture. I mean, typically open source components are designed with security in mind already. So this is good. We have components like Linux, systemd, OpenSSL. They are designed with security in mind from ground up. The commercial companies then build the systems with this, with their own system architecture. And usually they also influence the components with this by either contributing or by giving requirements. But also from the implementation perspective, we have with the open source community, it's not security by obscurity. Everyone can see the code and read it and analyze it. And you, at least in the high quality projects, you have a high implementation quality. And therefore, the commercial companies benefit from this, build on top of this, and even contribute to the projects themselves, because that's the business model. They use the software. So therefore, and actually to ensure security in an open source environment, you need to have an ecosystem around the components. And therefore, the automotive domain can actually reuse this ecosystem and build on top of this. So security is well established in the open source world, but let's have a look at safety. How does this work? First of all, safety is not a quality level. You need high quality to build safe software, but it's much more, as we heard also today. And the good thing is, many of the popular open source projects actually have a high code quality, high implementation quality. But what they are missing is, for example, safety requirements. No one has written safety requirements for an open source component. Why do they need this? It's not defined. It's also a system property, so these component developers don't care. The development process typically is totally unrelated to any safety standard, to any safety regulation. Sometimes it's even contradicting and therefore doesn't fit. And also, you don't have any safety documentation. You don't have safety manuals. You don't have any evidence that your safety is implemented. This is our starting point. Now the question is, how can we make it safe? There are various approaches. Let's put number one is what we call the full project qualification. This means the open source project develops everything it needs for safety argument within the project. All the safety artifacts are available in the open source repository, and it's really from the owners of the project. There are actually some example projects that do this, like from Ferris Systems, the Rust compiler. There all the safety evidence is available in the project, and you can take it. Eclipse, ThreadX, Xen, they all are working on this, and actually all commercial open source safety products, all commercial safety components are developed like this. They have all the evidence. So this means there is no difference actually between an open source project and a commercial project. It's just the way of distribution. Then you can also take a snapshot. You take a snapshot of your open source component and qualify it and retrofit the safety. So we did this, for example, for our hypervisor, this approach. We're working closely together here with a company called Concept. Therefore, this is okay. But also from Red Hat, that's here still the libm, but now they have more. But they also take a snapshot and qualify it. And the next is something, also again, we have seen earlier in the presentation, a decomposition between ASIL and QM, meaning we're having a QM functionality and take it as is and build a monitor around it. So this is what we have done here, for example, for our safety Linux here, we build a monitor around Linux kernel to make it safe. Having a look at a closer look at the various approaches here, they have pros and cons. From a technical perspective, a full project qualification is basically the best. You can apply it for everything. You can have a single entity. Maintenance is guaranteed, but we all know it's high effort, and all contributors have to follow this approach. There are some commercial implications with this as well, and this is also something we really need to consider. We all know safety development is expensive, and then who is paying for this? So yes, everything is under the project's control, this is right, but also everyone can take it. Everyone who has sufficient knowledge can take this repository and qualify it themselves. So therefore, so this is technically the best approach, but commercially difficult if you put everything into the open. Let's have a look at the snapshot qualification. Also, again, this has some technical implications. We built on a robust foundation, which is good. We can do it for any open source project, but we have to retrofit it. So we have to do some reverse engineering. It's high effort. We may have to adapt the existing baseline, and maintenance gets difficult. This is the same for commercially. Yes, of course, we have reduced development efforts because we are starting from a solid foundation. And ownership is possible of the safety artifacts, but it's still a big invest. You have to do reverse engineering, and it's really complicated and costly to do the maintenance. So therefore, yes, this approach is technically possible, but you have the risk of a commercial dead-end road. And one further approach is the ASIL QM decomposition. We separate the safety, the functionality, and the safety monitor. So we have only development on the safety function. Safety function is usually simple. And this is an established approach in the safety community. We have also seen this approach in Christopher Temple's presentation. And you can actually update function and the monitor simultaneously. Disadvantage, it doesn't always work. And the integration and validation of multiple components can get difficult. Commercially, it has quite some advantages because you have reduced development efforts just for the monitor. You can own the safety-related functionality and have improved maintainability. But sometimes for some open source projects, the license model doesn't support this. This is what you have to consider. So this approach is technically challenging, but commercially feasible. And to have a closer look at it, how such a system would look like, I can show it here in this approach here. So when looking at the safety integrity requirements, this is how safety and security actually match together. When you have safety integrity, you have the requirement that you need a reliable execution environment in which you execute the software. You need spatial FFI to separate QM components and safety components for mixed criticality. You typically need only write protection for safety for this. This is totally fine. You need temporal freedom from interference to detect if something goes wrong and if something is delayed. And for communication, you need to ensure that you don't have errors in the data. This is something we know here. This is mandatory for commercial as well as open source components, and this is what we know because these are actually the requirements from the ISO 26262. Now let's have a look at what security demands. Again, reliable execution environment, of course they need it. You need a high-quality code base because in order to reduce the risk of vulnerabilities due to implementation errors. You need spatial freedom from interference because you want to prevent malicious data corruption and extraction. So this is different to safety. Safety, you have random faults. When it comes to security, you have intelligent attackers who want to fool your system. This is a different level of analysis. You need this definitely for open systems, which can integrate additional applications. And you also need read protection, because you might have to protect sensible data like keys. Even temporal freedom from interference gets much more complicated within security, because you want to have constant execution times, because otherwise you could have something which is called a side channel attack. So an example which went through the press are these vulnerabilities called Meltdown Inspector on the desktop PCs. These were actually side channel attacks which used the execution time. And of course, we need to prevent malicious changes in the communication. So it's not just detect, it's about prevention. And therefore, we see that security requirements are actually even stricter than the safety requirements. And therefore, here they really support each other. So looking at operating systems, this is basically how we do it there. We're having QM components and monitoring components, like, for example, communication. We have an end-to-end library protecting the communication stack. We're having execution checkpoints monitoring the OS scheduler, or the memory management is developed as a safety component itself. You see this here at the items at the top, at the pictograms, which approach was taken. In general, we see that the mechanisms we need for security need to be much more rigid than for safety. The difficulty we have here is that these much more rigid mechanisms that are developed for security are often hard to analyze for safety, like, for example, a cryptographic functionality. For Linux, we have done this as well, this approach here. We have put a monitor during the Linux kernel. I presented it in more detail last year. We have a safety-related application, Linux kernel in between, which is QM, and the safety monitor and the hypervisor, which ensures that the Linux is safe. This has actually the advantage that we combine here safety and security. You need to update continuously, but updates are kind of the enemy of safety. So here we can update the Linux kernel, but keep the safety monitor constant. This is in short, again, as a repetition how it works. We are monitoring the memory management unit, making sure that any malicious access via the from a malicious application is actually protected. Therefore, the safety is actually on the monitor, which we have down here in the hypervisor, on the SoC, of course, because we trust the SoC that the peripherals and the protection mechanisms are working properly, and of course, the hypervisor, which executes the safety monitor. From a security perspective, we don't have any safety allocation in the kernel and can exchange it and replace it. So this is basically how we can separate the components here to make sure that we separate safety components and QM components. It's a virtual network that we have here using VLANs. And with this, we can actually create a multiple independent layers of security. We protect the critical parts, these are the red and the blue networks, from the other components using intrusion detection and prevention systems. And therefore, make sure that the safety components can stay constant while we update the QM components. Just briefly, I've also shown this last year. This is how such a system would then look like. We have safety components using traditional components here to the left. This is a classic AUTOSAR stack. We have open source components, which are qualified according to the various different approaches that we have here with Linux, the hypervisor, safety monitor. And these systems are now actually built and on the road. So what does this mean as a takeaway message? Safety, security, and open source for the SDV nicely fit together. And actually, they support each other. Many safety and security requirements are similar. Even security is stricter. And the most difficulty is that the stricter requirements may get an ASIL. When you want to qualify for safety, you need to find the right qualification pattern. Not each pattern works for each component. You need a high quality basis, but actually all the safety standards allow a retrofitting if you do it right. And then, of course, this is basically my last message here, the business aspects are crucial for the success of open source software, because someone has to pay for it. And it's not getting less effort when you do open source. This is something some people think. No, it's not. It's the same effort as with commercial software development. And of course, this needs to be refunded, and you need to have suitable business models for this. Thank you.
Any questions? Otherwise, we have after the panel as well. But okay, first question.
Hello, Chaitra from Continental. So when you plan to use open source software, do you think the Tara needs a much more conservative approach in, let's say, rating the threats? Or do you think the normal approach would be okay because the source code, part of the source code might be known? Something like this? Or?
So in any case, this is also valid for open source software. You need to have safety requirements. You need to know what actually you want to protect or make safe. And this is the same for software developed yourself as well as open source software. And then you have to verify your software accordingly. So this is exactly the same. So there is no difference if it's open source software, if it's commercial software. It's just the case that for open source software, the community is not doing this because they don't want to take the liability and no one is paying them for this. So this is basically the task that we as a company do then and add on top of the open source software, or as an open source projects like Sen, who are also currently going towards safety. It's currently retrofitted by the open source community itself, but funded by big commercial companies behind.
Okay. We are a bit out of time, so maybe we should move to the next presentation, and then anyway we have a panel. Okay? Thank you. Okay, the next is actually changed from the agenda. We have a Dr. Ioannis Sovokos. He's a senior research project manager. Understood is still from Fraunhofer. Yeah, the stage is yours. I don't have your more information, so please.
Thank you. Slides should be coming soon. So in the meantime, just to stimulate everyone, and I hope you take this in the right way. So how many safety engineers do you need to screw in a light bulb? None, but if you do, the electrician will have very good safety requirements to work with. So today we'll be talking about a very similar topic to what you just heard, but I'm going to be covering some different angles, so hopefully it will be a complementary image to what you heard before, and not redundant. So, I'm from the Fraunhofer Institute for Experimental Software Engineering, and this is part of the Fraunhofer network, and our overall goal is to transfer research to industry. We're a nonprofit, and personally, I'm coming from the safety engineering side of things with 10 years of experience roughly, and having done my PhD in the University of Hull in the UK. And yeah, my background is not so as focused on open source, because that was my colleague's responsibility mostly, but I'm going to cover for him and cover some aspects new, hopefully. So we'll be talking about, let's say, some high-level points on the context. I'll skip over them quickly because you mostly heard about them already. And then we'll be going into some more, let's say, regulatory-specific aspects of what is involved that could be used in the terms of OSS certification. And then I'll show also a brief, very limited scope abstract example of how you can use our specific model-based approach in order to reason about certain properties when you're integrating systems, including modular systems with open source. So, context. I tried to look online for recent research that kind of tries to document what kind of state the open source community is in with respect to automotive software. And the most recent one, I found this review from 2022, covering roughly 12 years, so quite extensive. And they did a big documentation of quite a lot of repositories, about 600. And as you can see from the side of the graph here, the interest in automotive repositories on GitHub has been increasing quite significantly. And these are active repositories. So there's definitely a support for the narrative that there is increasing interest. And for safety specifically, 60% of these repositories involve open source software for in-vehicle use in comparison to tools. And now this depends on the classification, but between, let's say, 3.5% to 40% is categorized as safety critical. Strictly speaking, 40% is safety critical based on the application, so it's not dedicated necessarily, but you could adapt it based on the author's opinion. So anyway, not to split hairs, but the open question still left from the authors is whether this is still in a condition to be used in safety critical systems as the bulk of the software there. And the other limitation of the study is that it focused on traditional software repositories and not including other repositories which focus more on like machine learning systems, for example, which are another big community of open source in a way, and a big source of potential AI models that you could draw from. So this is not covered. So to summarize, let's say, results from the study is that, while not conclusive, there does appear to be an indication that there is growing interest in open source usage, and other great literature seems to agree. We also heard from the previous presenter that this is the case, And Electrobit and Red Hat are also major players that are entering the space, the Rust-Ferrocene project as well. And there's a recent initiative from the VDA to bring together different manufacturers to also contribute in a way. So basically, there are indicators that this is going to happen in some form, and it's already been happening, as mentioned from the previous talk. And the increasing, let's say, cost considerations and recalls based on software defects are also pointing in the direction of increasing software, and therefore OSS will be playing potentially a larger role here. And key factors were already mentioned in the previous talk, so I won't go over them again. Software-defined vehicle, cost-cutting, and outsourcing software competency to open source. These are all motivators for doing so. So, therefore, this is not, let's say, confirmed by any definitive proof, but it seems that this will be the case moving forward. And cross-cutting concerns here are very important. We have cybersecurity. Firmware over-the-air updates are also a concern when you're dealing with, continuously asynchronously updated software, and machine learning operations on software that you might or might not trust are also key related concerns. So, what does the existing certification landscape tell you? I won't go over everything that was covered before, but I'll address some new parts that you didn't hear before. So, this was already covered previously, so I'll just briefly fly over it. This might not be very well readable, but basically part 6 is dealing with in-context software development, and this is the case when you're trying to also include the open source development as part of your project in some way. And it depends on the technical and functional safety concept coming from parts 3 and 4. And parts 11, 12, and 14 cover different cases for where you could have different, let's say, handling of the open source software depending on the context. 11 is for tools, and 12 and 14, if I remember correctly, are for qualification of software components themselves and proven in use arguments where this is possible, in theory. Another part that is relevant is part 10, where you have the guidelines for safety element out of context, which were already also mentioned in the previous talk. So hopefully all that's clear. In recent developments, there's also a relatively new standard, ISO 18926, which covers pre-existing software architecture elements, and it does have also dedicated coverage for open source cases. Of course, this isn't a silver bullet on its own, but it does give you a process with which to start from the point where you have safety requirements, mapped to the software stack, and then you do an analysis of the pre-existing architecture element that you want to include. In our case, it would be the OSS component. You do an impact analysis, and you try to determine whether your current safety plan needs to be adapted or not to the target, based on the target design. And then this process is, of course, iterative, and as we saw from previous presentations, this is always anyways the case, even when you're developing your own software. So the main point here is to focus on this section, because this section is what, let's say, assesses whether the software under consideration to be integrated needs to be taken care of with respect to the provenance of the software, meaning are you taking it from an organization that's open source but has good community standards, or whether you're taking it from an unknown source, or what's the situation. And number 2, with respect to the complexity of the software, which is measured in more traditional terms such as cyclomatic complexity and other static and dynamic analysis methods. So in either case, the main point here that you need to be able to control is to understand which requirements have been carefully allocated to the OSS under consideration, and what would be the impact on your target system based on this allocation, so that you can plan ahead this into your safety validation plan. So, the key challenges I'll just summarize briefly. They were already given very well in the previous talk. So the point I would start with is that you're bringing in potentially foreign code into your supply chain. Therefore, your IT security protection team needs to stop you the moment you think about this, and they need to carefully evaluate what you're about to do, because if you just copy paste the code, there's no guarantees anymore. So you need to be very careful before you do this, of course. Second point is, of course, the development process across the community is not uniform. Some places have better standards than others, but safety is generally, as mentioned, not the primary consideration. Therefore, you need to be carefully analyzing what you're getting. The process guidance given in the recent ISO is there, it's available, it's helpful, but it doesn't do everything for you. You need to be doing the homework, you need to be doing your due diligence, basically. I've seen some comments on the internet and approaches mentioning proven in use arguments. In principle, theoretically, this is, let's say, one approach that has been used also in the past for other systems. But given how few cases of open source code there are compared to the larger, let's say, ecosystem there are, this is not a guarantee to be tracked. And there will be many cases where you don't have enough information to make this kind of claim. Therefore, if you can find such data, that's good, but if you cannot, this is unreliable. So, safety element out of context is always challenging because you're trying to make assumptions about an integrating system you're targeting without having it in place necessarily. And therefore, whoever is integrating your system will have to evaluate, let's say, the interface points between the assumptions you're providing and the assumptions that you need to have onto the integrating system. And with respect to the tool qualification point, of course, you need to look whether there is documentation for this given tool, what are the test results, what kind of validation has been done for this, and then need to cover the gaps where there is none. And finally, this is going outside the scope of the talk. There are upcoming standards for AI model assurance, but they do not deal with, such as ISO 8800, but they do not deal with open source software considerations specifically. So this is a little bit of a gray zone still, and in any case, the main points remain that you always need to be very careful when integrating these things, as if you have developed it on your own. So, in the next part, I'll be simply discussing a little bit a very limited scope abstract example of how you can use R2 in order to reason about the kind of properties you want to look for and test for in a given component, such that you can modularly integrate it into your own system. So R2 is called Safety Box. It's built upon the Enterprise Architect modeling framework, so another tool. It supports this kind of system modeling, let's call it a little bit based on UML style. And additionally, HARA, component fault trees, safety argumentation, dependent failure analysis, and system theoretic process analysis. So the general idea here that I will be demonstrating today is that we're a supplier in this scenario, and we're trying to implement an airbag system. And there's different sensors that are providing inputs to our electronic control unit. And we're trying to control the actuator. And the point here is that based on the design that I have made already, I have clearly defined what are the kind of input ports and output ports that I expect my system to be receiving inputs and outputs from. And the question here is when I drill down into my ACU component for the software that I'll be deploying within it, if I want one specific module in the ACU to be using open source software, I need to carefully assess and assign which safety requirements to map to the ports of the module, such that I can, for example, determine whether this module needs to be able to report a crash within this amount of time with a specific level of integrity. And the same for other types of failure modes that I will want to protect against. Again, this is coming after the HARA stage and after any additional situation space analysis you may have done in order to carefully engineer the safety requirement expectations based on your safety goals beforehand. So at this point, what we need to do to be able to consider this is apply a modular version of fault tree analysis, which is called component fault tree analysis, where this specific component only can be represented in its failure logic through a component localized fault tree. And this could look something like this, for example. So the little component module that you had seen before, where we're considering to switch it out for an OSS module, can be mapped to its interface failures, meaning, for example, the omission of the crash reporting that I mentioned before, the false negative, for example. This can be defined here, and it is linked through a binary logic to different input ports where the OSS software functions would receive inputs from your sensors or other parts of the system, and then you would be able to carefully design, based on your analysis of the OSS, how the logic within the code works in order to link these things together. Once you've done this, and this might be quite complicated because you don't know the complexity of the open source component to begin with, you can then use automated analysis solutions. We have a built-in in the tool, but you can also use the industry standard Isograph Fault Tree Plus to do so. And then you can get a qualitative cut set of the minimal and necessary and sufficient conditions that can lead to this failure event happening. And this is completely independent of any detailed, let's say, implementations happening within the open source software that you're considering. And the analysis results come up quite quickly here. And the point here is that you can quickly look for example, single point failures that are critical in the open source module that you might want to protect against, but also dual point failures if that's of relevance. And therefore, this gives you already a clear indication before you do any kind of integration test of what kind of testing and what kind of additional requirements or additional safety measures you need to introduce in order to protect your system from this new open source module being integrated. And another aspect I wanted to mention, I won't be going into a lot of detail here because I didn't include it in the scope of the talk, but dependent failure analysis is also quite relevant. What was mentioned before is that you need to also consider, for example, the integration environment with the hardware-software interface. And dependent failure analysis can also reveal other causes, for example, cascading failures or other coupling factor-related failures with which you can annotate flows within the system to indicate, for example, power or shared resources that are being used by components, and then automatic flow analysis can reveal to you a list of possible causes that can constitute common causes failures. And then you can quickly filter for those and introduce additional safety requirements or measures to combat them. So we recently published also a paper and a conference to discuss this in more detail, if you're interested. Good. So, to summarize, as was mentioned in the previous talk, we both agree that open source software poses a lot of cross-cutting challenges, and today, in the last part, I only talked about very few of them, and in very little detail. There's a lot more to consider. But the key point I'd like to drive today is that the types of analysis that you need to consider when you're integrating are not fundamentally completely different than what you actually do when you're developing safety software. It's just that you need to apply them in a more modular way, for example, in the example that I showed you. And my argument is that effective tool support, such as the one we're offering here, can be quite useful in leveraging your ability to analyze and to do so. So this is quite important, and it's also very important to be able to build an understanding and argue to others, including in your safety case, with respect to why you believe your system is safe. Great. So if you're trying to integrate OSS, or for that matter, anything else into your functional safety engineering, please reach out to us. We're very happy to help you. And we have expertise in different standards and different safety analysis and other concepts that we can be very happy to help you with. Thank you very much. Are there any questions?
One question already.
Yes, Alex Madros from Electrobit. So thank you very much for your presentation. Liked it very much. It really showed the problems and tasks you have to do. And it also showed that there is no such thing as a free lunch. one comment regarding your ISO 26262 Part 8, Clause 12. This actually doesn't help you at all.
Okay.
This is why PAS 8926 exists. But then I have a question. So you're basing your tool on Enterprise Architect, which is a proprietary database-driven tool. While most open source projects are completely text-based.
Yep.
How do you ensure consistency and updates and so on based on these two different approaches?
Oh, okay. So, so the approach that I showed you here is a simplistic approach where you do a manual representation of your own system, and there is no, let's say, automated code transformation into this yet. Okay. However, we have another technology called digital dependability identities, and what we're trying to aim with that is to provide seamless integration interfaces into the tool, such as this problem specifically can be, let's say, facilitated a bit so that you don't have to invest a lot of time linking it to code analysis or static analysis tools that can extract the architecture from open code databases. Does that answer the question?
Yes, it's interesting because we are currently internally doing exactly the other way around. We are transforming our enterprise architect models into text-based approaches.
Mm-hmm. Okay, the reverse, huh? Okay, I think we should talk more than we have a lot in common. Thank you.
More questions? Looks like you're all tired already. I mean, we can start already with the panel anyway, that is still on the same topic. So, okay, for now, many thanks.
Thank you.
Okay, and I would like to call here on stage the panelists. So, again, we have Helen, that was already presented. We have Costa. Oh, yeah. Okay, so Nori, I made a mistake. Okay, so it's different from what I had here, sorry. No. Oh. Something wrong, yes. So the panel should still be on
yes.
Open software, yes. Okay, now it makes sense, yes. So, okay, we have Costa, Andriotis. Please, he will be the moderator of the panel, and yes, he's a verification, validation, and functional safety manager at Robotech, that is a NIDEC company. Again, Alexandre Matausch from Electrobit, and we also have here Sylvain Yevo-Zekeyo, hopefully I pronounced correctly. Is a founder and CEO at Sanyon in France. Sanyon.
Ricardo.
You are the moderator, so now I can sit and relax.
And we have
1, 2.
For sure. No further introductions, right? So, as you all understand, it's a follow-up on the previous discussions, and mainly the topic is to discuss more on the open source software, as we started previously, and we'd like a lot the collaboration and the questions that are coming from the audience. This is the part of it, okay? So I think we can start on the first one, and this is mainly starts with Alex's presentation. So can open source software be as safe as proprietary solutions in safe critical applications? And before answering yes, I think I'm going to translate a bit the question. So we are all discussing about open source, seeing that as a very transparent system, right? But at the end, yes, we can use them, but this transparency is a liability or a great asset to use. How about that?
Oh, that's a good question. Actually, it's definitely not a liability. It's actually a prerequisite. You have also the ISO 26262 in principle in this mentioned part 8, chapter 12 considers also qualification of binaries in principle, although this is not really done and not really feasible. you need to have the source code to analyze it thoroughly, to retrofit the things that are missing. So if you take an open source component which is not developed according to safety standard, many artifacts and many analyses are missing. And this is also what this PAS 8926 tells you. You have to retrofit this, you have to redo this, you have to add this. And for this, you need the source code. And therefore, it's not a liability, it's a prerequisite.
Okay. Are there any arguments on the use of open source software from the audience? Just to have a contradictory here to discuss? Then I think it's nice to have a follow-up. So who is taking the responsibility for the open source software? And then is another thing, how to track things that are coming from the field, because we know that the common use software, let's call them like that, are already existing and they have been tested in the field. So therefore you can have data about them. I don't know. Would you like to answer, or Ricardo to follow up? Sylvain, practically?
Yes. In my personal point of view, the person that takes the responsibility of the open source software is the person that integrates the open source software in his product.
Yeah. Oh, okay. I think there's an argument there.
Okay, there are some couple of questions.
That's great.
Let's start the fight.
Thank you. Luz Garcia from Nebusco. I need to think and who is the responsible in case the open source code is hacked? Is the OEM that have delivered the bus, in my case, that will create buses? Or is the, how to manage that kind of things? Because in general, what we do in the normal development is create agreement with our suppliers. And for the open source code, I see it challenging.
Well, you want to answer?
Go.
Well, in my personal point of view, if a software is integrated in a car and there is some issue, the car manufacturer has a responsibility, but what will he do? He will transfer this responsibility to the person that had delivered him the software. It means, I take just an example, if Electrobit had developed the software and has implemented by BMW or something like that, and in this part of the software we have an open source software and there is a problem, the responsibility will be BMW, then Electrobit. That is my point of view. I don't know if someone has...
Yeah, I think it completely depends. So the functional safety standards define what we call usually the development interface agreement, the DIA. Now the question, if you're getting some open software from some community, can you get a DIA? If yes, okay, we should question if then the responsibility can be met and what you get is actually okay. But if we don't get a DIA, okay, now you're on your own. If you want to use it, yes, potentially you can, and potentially the software is even safer than a new software you want to develop. But it's up to you to demonstrate it. So, as we mentioned before, I mean, it's not a shortcut that you're taking some open software, okay, everything is done. No. And especially if it's not coming with a proper safety package, a safety case, the effort could be much bigger, and potentially the risk could be also bigger that you get at the end and say, oh, actually, was a wrong way.
Actually, this is the business model behind all these open source software distributors. So they take the open source software, they qualify it, monitor it, do the security management. So we have a cybersecurity management system in place for our software. This includes our commercial products as well as the products that are based on open source software. So if something is found in there, either it comes in via our communication channels, we have to inform our customers that something has been detected, and by the way, here's the update, please download, integrate, and distribute, as it would be in any other case, and as it would be also regarding safety. If a safety incident is found, it's the same. We have to fix it, we have to inform our customers and provide an update. And this is actually the business model for us, but also other Linux distributors, as we have them out there, like Red Hat, SUSE, and so on. You pay for this maintenance, that they monitor, that they fix found issues, and that they provide updates, either for bugs or even for security incidents.
Thank you. I agree that you need to have an agreement, that the challenge here is if the agreement will be in CIA or DIA. That is the challenge we have also.
Didn't get you acoustically?
I was saying the challenge
CIA.
is to understand if is the CIA the point or the DIA, because if you need to have both agreements and it's
You should have
becoming
both.
challenging.
Yes, you should have both theoretically. Then whatever you don't have, you have to compensate. And then you need to check, can you do it or not?
Yeah, it's the same as with safety and security here. And yeah, it would be actually, from an effort perspective, beneficial to combine the two. I think this is a topic we will address tomorrow then.
Thank you.
We have another question.
Yeah.
No? Okay, pass.
No more? Okay.
Okay, so the next big thing is that how can actually automakers manage the risks associated with OSS components? And then is there a playbook to play with? Is there a specific guideline that they need to follow? Practical examples of that, Sylvain?
Yes, maybe I can say something.
Yeah.
Well, that is a really good question. It is a good question that I can answer because we are working closely with Volkswagen, with Porsche, with Daniel. That is the reason that he mentioned me. Well, in the framework of Volkswagen, there is a lot of requirement. You have to follow the functional safety requirement. You have to follow the cybersecurity requirement. And they have created a kind of framework as a group, consent group software, where you have a list of requirements that go from functional safety, automotive spies, machine learning. There is everything inside. Well, if we consider why are the reason why someone want to use the open source software? Well, he has maybe a platform that is already mature. He want to reuse it. He want to save the time. Sometimes he say, okay, I want to learn from this platform because there is some transparency inside. Well, and there is, when I take only these two examples, there is two risks. The first risk is that someone say, okay, I want to use the best part of this open source software and I make copy and paste. That's not good for safety, and that is also a requirement of the K-gas from Volkswagen. There is the requirement to say, okay, well, I don't know if this supplier wants to use the super software of Electrobit, or he wants to use something that he has taken in the market, and I cannot forbid him to take it. And then I say, okay, if you want to use a third-party software, then you have to encapsulate it. You have to demonstrate me for each release when you test the interface, when you test the resource consumption on the target, that what are your value, that you are able to show me that you avoid some freedom of interference. And that's for each release. And that is, for me, a good approach, not only because he has made a summarized of some requirements that should be taken consideration for functional safety, but he has added the approach of the quality assurance. If someone of Porsche come to you and make a SPICE assessment to a specific release, these requirements must be fulfilled for this specific release. That means if you have planned to fulfill this requirement somewhere later because you wait to have a safety assessment, you wait to do only what you need to do to pass the safety assessment, you will have a problem with Porsche. That is, for me, a good approach to ensure that the people implement all these requirements from the beginning in the development life cycle.
Thank you, Sylvain.
I can add something here also from the Volkswagen area. I mean, we can publicly tell it because there's been a press release. Together with Continental, we have built ICAS 1, and ICAS 1 is Linux-based. It's not safety, but one of the biggest efforts and tasks to do was actually the license check. Really look at all the components. Are the license fine? Are the license obligations fulfilled? Are the license obligations documented? Do you have a proper SBOM, as it's called, the software bill of materials? This is a major task and a major liability, and make sure that no one somewhere in the supply chain introduced somewhere in your open source software code, which could, for example, lead to a patent infringement or so. These are things which have nothing to do with safety, but are a big liability for the automakers, which is probably even worse than any safety and security, because the software is available. Everyone can take it and scan it. And this happened already, so there are these so-called patent trolls around which actually look for this and try to sue the vendors of these products for such infringements. And therefore, this is something which is also something you have to take into account when you use open source software.
Yeah. Any questions? Any additions to that?
Hi, this is Senthil, Functional Safety Manager from Sensor Technologies. For the third question, we have the open source repositories, in which we'll be taking the source and we'll be using it in our functional safety project. Do we have any repository which holds the SEOOC software component ready-made available in place?
Question
I would ask the same.
Yeah.
No, do we have any readily available safety element out of context open source softwares?
As a safety, I will say today, no.
Well, you can actually download our Linux for safety applications. That's available. Of course, not the safety evidence, but the software itself is available.
Okay, but we need to qualify that particular component into our system, isn't it?
Well, it's the software as would be going to the target. Of course, the safety evidence that is the necessary is for this you need a license. But the software itself is available.
Okay.
And there's also from Ferro Systems, the Rust compiler, which even has the safety artifacts in the repository, so you can download it and have a fully certified compiler, ASLD certified, with all the artifacts necessary. Again, we come to the business discussion here. How do they actually fund it? This is what I learned later. In order to really use it, you need a library that you have to buy from them.
Okay.
So what are the challenges? We've said about the work that needs to be done, but it's important to understand what are the challenges of certifying OSS, and what's the ISO 26262 has to do with it. How does this is typically supported? It needs to be adapted. Is there a gap? How to manage it? I think this goes to you, Ricardo.
I mean, for sure, if you're taking some open software, is not developed based on the Part 6 of the ISO standard. It may be, maybe if you do a gap analysis, maybe you don't find gaps, but the starting point is that it is not compliant to the Part 6 of the ISO standard. Then the ISO is only giving one option, that is the qualification of the software. But now we know that if the software is relatively complex, maybe this clause also is not sufficient. That's why the community prepared a new PIS, 8926, that is covering these kind of more complex softwares. And one of the topics is the provenience of this also software. Who developed this? How much information do you have? If you got enough information, maybe, yes, you can also do something. If really you have no information, the risks are very high. So I would say, yes, today ISO 26262 doesn't really give us so many options. unless you want to say, okay, let's retroactively do a kind of gap analysis against the Part 6, understand what are the issues. But again, unless you have a cooperation with the community, the open community, there is probably not much you can do, because you will not get all the documentation, you will not get the coverage in MCDC or whatever. The community has to give to you, or you have to start from scratch, but then it will be very challenging.
Yeah. Do you feel that since the discussion started for the next revision of the standard, something needs to be considered?
For sure, the 8926 will be integrated into the third edition, but I don't expect now a full magic solution for open software.
Okay. How about in general intellectual property? That's a part of it to consider. Is that something that should the standard be involved, or it's something for the integrator to consider only?
Intellectual properties, I will say, should be different role, yes, should not be part of the ISO.
Okay.
My view.
So regarding IP, I can say, as mentioned, this is the crucial aspect when it comes to the commercial topic here. IP is the one the companies want to sell, they want to earn money with. So what we see from most open source projects is that the evidence that you need is actually proprietary. So you have the software, which is in principle qualified, which is in principle safety capable, but all the evidence you need, this is what the companies sell. This is what we do, this is what other companies do, this is what Red Hat is doing, and this is actually how you get the refund of the high invest you have also for open source software. You mentioned, Ricardo, about the community support. The community is actually nowadays accepting this challenge, because exactly right now at this, also in Munich, there is the ELISA workshop taking place at Red Hat. A colleague of mine is there. But they are focusing on Linux, how to use Linux in safety applications. And this is an open source forum where all the companies, like Red Hat, Electrobit, are meeting and discussing how to employ Linux in safety use cases.
Right, and I mean, Linux is one of the examples, but we also have a hypervisor like Xen or others. I mean, I believe that today we don't have any open software user for safety, or at least qualified for safety. But yes, as you mentioned, this is a trend. Now, I think there is a strong interest from the community, and potentially we can even discuss why. But there is a strong interest, and we see that many companies and many open community are now trying to work together in this direction. So it will happen. The question of potentially could be up to which ASIL can we achieve this kind of acceptance.
I think that's nice to hear what the people here have to say.
Okay, we have one there.
Yeah, thank you. Maybe in this direction, but not exactly. So obviously, one of the, let's say, storylines of open source was that you could even have individual lone actors being able to contribute to a big project and not have to be bound within a specific organization structure necessarily. But when you consider that applying all this process and all this level of quality at the minimum, then this becomes really hard for a solo developer to just enter into a project, give us some code, and then call it a day, right? Without jumping through a lot of hoops. So in your view, is this something that could be better incentivized in some way? Could there be some kind of community level standard specifically for maintaining safety and security compliance? Or is this something that only large open source communities can be able to satisfy?
That's a good question, but let's put the question the other way around. What incentive does an open source project have to do this? To safety qualify an open source project. So if I would be an open source developer maintaining such a project and say, okay, now I need to buy and read ISO 26262, probably also the other related standards. And then I have to add this. This is a lot of effort. And it doesn't do anything to my software. It's just a lot of paperwork. And why should I do this? Who's paying me for this? So they simply don't do it. So, and in the end, when you do this, you're actually taking the liability, because you also have the fact that safety always comes with a liability when you do safety development. So you need to probably do this, and typically open source software comes without any warranty. This gets difficult when you add the safety stuff. You cannot say here, okay, this is the safety stuff, the argumentation, but I don't take any warranty and liability. This is hard. So therefore, you will need commercial companies that basically transform this risk into money, because this is what they get paid for then. And then therefore, it's for them, for the companies, the question, why should they donate this to the community? They invest a lot of money to get this, and why should they give it away for free? You also have to explain this to your investors and everyone. So this is the model behind this. You have the companies adding on top of the open source software their contributions and selling them. This is the business model that is currently establishing.
Yeah, I guess at the end there will not be really the open community to enable this, but will be some of the members of this open community that they have some strong interest to bring this software into their product. And
These are companies usually.
Yes, yes. Yeah, companies are really part of the community, but as you mentioned, what is then the motivation to upstream and make this public available with potentially, no benefit in terms of cost, no ROI? It's a big question, yes. And the question, what is the benefit of enabling open software for automotive as well? That I think is also the key question. If you're talking about Linux, of course you have a much bigger pool now of developers that can contribute to your software, and then you don't have to maybe retrain and so on, so it can be some benefits. So yeah, I think what are the benefits? This is something we need to also discuss.
Yeah, it's also funny when you currently look at what's currently probably read it about the Eclipse S-Core project, which is starting. When you're involved in the discussions, they are less about technology. The critical discussions are currently, what's the business model? So if companies like Electrobit, Vector, or whatever go in there and contribute the software, what's the refinancing? And these are discussions that are currently taking place. And this is really the business model on the success of open source software and safety is really crucial. When you have this, I think there's no problem even making it ASLD when you're having the technical software architecture on this open source project. But that's what you need.
Yeah, before the question, just a note. I don't know if you are aware, but we have already jumped to the fourth question. Okay, so we are already discussing how the industry manages things. And I'd like your approach on that. You might have to add something important here, right?
Oh, Chris Tempo. I have one counterexample, which is true. A good friend of mine gets sponsored by an OEM, not automotive, I admit. And he receives like 5 to 6 digit dollar values to reimburse him to write open source code. The liability problem is resolved because he is indemnified, and they did have a security attack through a code and nothing happened to him. And the motivation for the OEM is to seed the market and to facilitate an infrastructure on which more applications can be built through which the OEM benefits. So it is, I think the automotive industry isn't that far, and we see it because there is not that much OEM attendance here, but in principle it's possible.
Yes, you are actually hitting the nail on the head here. So this is really putting a crucial point for the automotive industry. Other industries are ahead here. For the automotive industry, it's very much open source is what can we take from it, and it's not what can we give back. This part is missing. This understanding is currently missing in nearly the complete automotive industry, actually. And unless this is resolved, we will have issues coming to such collaborational financing models.
So I guess we have touched a lot of things. And how about the future? What's going to come to us? It's open source is going to be balanced between the regular approach. Is that something that you see that happening?
I believe yes. I mean, probably up to maybe a couple of years ago, we were not discussing at all open software. So it was really a taboo in automotive. No way. I mean, not even, I think it was a topic. I think with the introduction of ADAS, AD, computer vision, I mean, you have now many things that are coming from a world existing, let's say, existing world, not only open software, but even other IPs. And of course, we need time to market, we need cost reduction, so you don't want to reinvent the wheel every time. So I think we need to enable how to use this. And again, following a process, it will minimize the risk to bring you something, to have a product that can be used. But even not following the right process from the ISO, maybe you have a perfectly safe product. The question is how to show. And but if you can, you will reduce cost. So I think I can see this trend changing over the years. I mean, even AI. Before AI, no way. I mean, now AI is used in automotive, even too much. So we can see that the trend is changing completely. And I expect in the next few years, more and more open software will be used in automotive, but it will not be an easy ride. So it's not a free ticket. There will be a lot of effort to spend.
Do you feel that this will reduce the cost rapidly, or we'll see it in years? And if the cost is actually going to be reduced, because there are a lot of things that you can consider. It's the effort, validated, for sure. It's a cost, right? But the effort exists even in the non-open source software. So it's a cost reduction, or it's a dream?
I would actually say I call it standing on the shoulders of giants. So you start at a much broader functional level, and you can add to the software whatever you need. So let's take the Linux kernel. So Linux Torvalds doesn't reject anything that comes from a company that stands behind this. It's going in, even if it's other people say, oh my God, it's getting in. And so this is taking place. Linux is on the road. It's on the road with European OEMs, with Asian OEMs, with American OEMs, currently for QM systems, but there it's already distributed, it's standard. For safety, there is currently some reluctance to adopt these new approaches because that's also what the colleagues from Red Hat see, because it's new. And new things and safety, well, we all know this takes some time. But I'm really confident that this will work out, and also in safety use cases, we will see open source software in the future.
Thank you. So do we have any examples of open source software use from automakers, software developers in general? No?
It's Siavash from APL. One of the examples, let's say, is when we have the cybersecurity and cryptographic algorithm. There are libraries and open source libraries that are widely used for the cryptographic calculations, and they are actually highly recommended. It's true that we know that the source is known to everybody, but the advantage is exactly that one, that during the time the persons has found the bugs, resolved it, and it's more reliable. If a company is going to redevelop those libraries from scratch, it's very probable that there would be some implementation issues or something that they have missed it, and actually it is widely used in automotive. So from one side we have operating systems that are highly used, but in the other side, in very little microcontrollers, we could have still some cryptographic libraries. So this is the point. I just want to ask also, just one other point to know your idea about it. In open point software, to me, it seems that we have kind of problem that we have for machine learning and artificial intelligence. When we have machine learning and artificial intelligence, we have a system, unit, software that works, but we don't know how. We know what are the inputs, we know what are the outputs, kind of outputs, but we do not know inside it how it is working. Like a neural network, we do not know what are all the combination, and we do not have that precision inside it. There, when we talk about SOTIF, we talk about how we can ensure that it is safe enough. And there are some methodologies that are defined to address this point. Could it be used also for the open point software? I mean, we have an open point software, it is working, but how can we say that it is safe enough without exactly following and qualifying it according to ISO 26262? Would there be such kind of methodology, perhaps, that could help to avoid requalifying all the open point software, but focusing on the validation, verification, and so on?
Yeah, I can add, we tried it. It's difficult. So when you could say that, for example, any software that is sufficiently large and sufficiently complex behaves like a faulty hardware, for example, and you try to calculate fit rates on your complex software. This is something you can do, and actually, so the IEC 61508 actually has this approach documented. So you can do it, but what happens in automotive in reality, this means you have to do this on the complete system. You need to run test drives with it, with a certain amount of kilometers and so on, to ensure that you can actually calculate the fit rate for this. And you have to redo this again for every update. This is not feasible. And so it's basically a maintenance issue. So that this approach is really hard. This is actually also something people will be facing when they take AI models and want to qualify it like this. As soon as they update it, they need to show the same evidence again. They need to show the same test data, the same, and so on, the same data collection, that the update is still safe. And this problem isn't solved yet.
Maybe I can add something about it. In the upcoming version of the ISO 26262, we will have some requirement that handled open source software. And most of these requirements are what we have shared today. Additionally, some proven in use, proven in the field. Well, you see, the standard try to take it seriously, to force the person to have a framework, to have some consolidated requirement to make it feasible. But at the end, well, today we have this standard, but we have some products that are not safe. That means it is in the responsibility of each of us to identify all the measures that we need to make our system safe.
Yeah, and I would like to also maybe to add, sorry, question?
I wanted to comment because you added a magic word to your question. That was the word enough. You said safe enough, right? And I don't think you can. I think unless you know the context in which you want to use a safety element, the enough question is open. And now there are two options, either, which I haven't seen yet, there is an assumption on the design external to the safety element. So the software says exactly, we need hardware that has this safety capability. We assume your application will be structured like this. We assume, which I haven't seen yet, that your application cannot share certain resources as a constraint of our safety concept. Unless those assumptions aren't there, all you can say is there are some safety properties, but the integrator has to ensure that these safety properties are adequate for his use case and have survived the integration process. So there is still a lot to do, even if it looks like the open source software has a safety story attached to it.
Correct, yes.
Just to correct, so we have these assumptions actually in our not open source safety OS, where we document what we expect from the applications. But, yes.
For the whole environment?
Not for the whole environment, just for what we need.
Yeah, but and you have confirmed that that is feasible, because you'd have to share it with, because you say it's not part of the open source package, which I understand, but someone has to go off now and say, yes, this is a feasible assumption on the hardware, and the hardware brings sufficient safety integrity.
So yes, we actually take the safety manuals from the hardware, analyze them, and put them as a basis for our safety manual, so that we ensure that it fits.
The same for the software, right? And unless you do that, you can't answer the enough question.
Yeah. But
just for clarification, the word enough, if we look to SOTIF, refers when in some point we should arrive to the point that say S is 0, severity is 0, or we have the vehicle controllable in that scenario, and it would be the endpoint. The methodology would be game methodology that there was a presentation by other persons this morning, and it was reasoning for say, okay, for SOTIF when it is enough. In ISO 26262, we have the failure rates. The failure rate could not be 0, but then there is a threshold. Under that threshold, we say that it's enough. Or let's say we do not have unjustified risk. By enough, I mean that one. Yeah.
To add here to the safe enough argument, also for open source software, we are not using part 5 or something like this. This is just standard development according to part 6, part 8, a little bit part 4 and part 2 what we need here. So we don't have the enough question. We just say for the target ASIL, we have certain requirements, and then the part 6 tells us from a quality perspective what we need to do to verify these requirements. And this is what we execute. And therefore, this enough question is basically answered by the standard. You follow this, you do your, you check at the recommendation methods, have your argumentation, why this fits for the target ASIL, and why you follow this, have your check mark, and you're done. Still a lot of effort, but...
Let's have a quick comment on that. Yeah?
Because you said you apply the ASIL, but the ASIL is the attribute to the safety requirements, so you need to impose safety requirements on it.
Yes.
With the ASIL, right?
Yes, even for open source software, you need to have safety requirements, yes. And it may be that you are the ones, not the creator of the open software, but we who do the qualification. We need to write them ourselves and then qualify the software according to these safety requirements. This is what the PAS 8926 basically says. This is what in a very limited approach is part of part 8, chapter 12. But without safety requirements, you won't qualify open source software.
Okay. I'd like to thank you all for the input on the topic. I think we can all state that it was enough of a discussion, okay? and close it. I think it's going to open a lot of discussions out of this, right? And it's a topic that all been involved and know how this will reach in the future.
Yep.
Yeah? Thank you all. Ricardo, it's for you to close it.
Yes. Okay, I guess you're all very tired. And unfortunately, a few guys already left the room. But okay, I don't want to keep you long, so you can enjoy your evening. Actually, you can enjoy also a bit of drink. But I think it was a nice first day as a kind of appetizer. Hopefully tomorrow will be even better, let's say. But I think we touched very interesting topics from AI, I mean, it's kind of common topics, common challenges we have. Something about systematic faults like a spice that tomorrow we will touch even more. And of course, open software that was just discussed. So I think, yeah, many interesting topics. I enjoyed personally today. Yeah, usually we say these kind of conferences, I was also talking during lunchtime, they're not conference, they're therapy. Because we see here that we all share the same pain. And we can talk about it. So when you go back to the company, yeah, safety, of course, you have to do it, but you have to do it with a cost-effective mindset. So yeah, again, I hope you enjoyed today. Please provide comments, and I look forward to see you here tomorrow again. Thank you.
Okay, and one last word from me. Thank you very much, everyone, for joining us today. Thank you, speakers, for the commitment, your presentations, engagement, participants for all the questions and activity. And also, of course, I want to thank our sponsor, SJS2SAR, and as the nice touch, let's have a round of applause for our chairman for this beautiful day.
Thank you.
Okay, since I have a microphone, I need to remind you that evaluation forms, it's very important for us. Please submit them before you leave or in the end of this day, if it's the only day that you join in us. And also, if you have any questions and we can assist you with anything, please come to us or my colleagues at the reception desk. And for further networking, we invite you to the main hall where the networking break was, because there will be an evening reception. Last drink will be served at 7:30. And hopefully see you tomorrow for more engagement conversations. Thank you.